A very good afternoon. I now request N. Sri Kumaran Nair, Jawaharlal Nehru Institute of Postgraduate Medical Education and Research, Puducherry, India, to chair the contributory session. Speakers of this session are Sudhi Bapat, Indian Institute of Management, Indore, India; Maria Isabel Garcia Planas, Universitat Politecnica de Catalonia, Spain; Lawrence Emily, University of Douala, Cameroon; Pawan Kumar, Aligarh Muslim University, Aligarh, India; David Raj Michael, Sikkim Manipal Institute of Technology, Sikkim, India. Over to you, sir.
Thank you very much. Thank you very much, Dr. Prasad, for giving you this opportunity. And it is always nice to connect with the Mahe, Manipal. And I think it's before we start the session, I should put my disclaimer very clearly. If any presenter or participant think that I'm an expert in this field, sorry, I'm not. I'm not an expert of anything you are talking or this. In fact, I would say humble, I am not in the conference. Probably the only reason I can find Prasad thought I should chair a session is, yes, I happen to be a good friend of him, and some reason for founding the department where at present Prasad is there, and department getting, and importantly getting Prasad to the department. Yes, I think it's a initial discussion I had with him, and finally we worked together for 10 years in the department. Okay. And beginning, it's definitely I supported conceiving this idea and developing these conferences, and a couple of conferences I was there heading the department. And probably that is why he thought, okay, Dr. Nair should chair a session. Thank you very much, Dr. Prasad, inviting me for this. I've been chairing this session and giving the opportunity. Otherwise, I am totally with the biostatistics and related areas. It's linear algebra. I think it's during my MSc program or PhD program. Yes, I would have used, but after that, nothing. With that, it's I welcome again all the presenters. We have 5 presenters, 5 people. It's presenting. It's and we have hardly 55 minutes to it. Then I request each person, please make sure that within 10 minutes you are finishing your presentation, so that it's at least we have time for 1 or 2 questions. Okay. With that, it's that note, I move to request first presenter is Dr. Sudeep Bapat from IIM Indore. Please, Sudeep, over to you.
So first and foremost, I'd like to thank Dr. Prasad for giving me this opportunity to speak in this very prestigious conference right here. All right, now coming to the title of my talk, so it says Middle Censoring in the Multinomial Distribution with Applications. And by the way, this is a joint work with Professor Srinivasa Rao Jamala Madaka, who is again currently very much active back in UC Santa Barbara. And as many of you might know, Dr. J.S. Rao is one of the many students of C.R. Rao also. So this would be another connection between this entire theme of the conference and the current talk right here. Okay. All right, so if you jump into the outline, there'll be a very brief introduction of the actual problem. And I'll probably just provide some background on the entire middle censoring idea right here. And then next, I'll be taking upon one actual practical scenario to sort of motivate the problem under the setting. And then estimation under a very special case. And then a bootstrap example. So I'll be showing you one output table in which you sort of bootstrap a large number of similar samples and so on. And very brief conclusions towards the end. All right, so moving on the introduction. So the highlight of today's talk involves estimating the parameters of a multinomial distribution when the data is middle censored. So you have a connection between a certain multinomial distribution and middle censoring scheme in general. Okay? And then obviously, like I said, even before, we'll be taking one practical data to sort of analyze this entire estimation under multinomial using middle censoring scheme. All right. Now, again, a very brief background on what exactly one means by middle censoring. So of course, right and left censoring are kind of widely observed and studied censoring schemes. And then, so one usually observes real data in terms of right censored schemes or left censored schemes and so on. But then middle censoring is kind of slightly different. So middle censoring occurs if a data point is not observable, when it sort of falls inside a random interval. So when someone talks about middle censoring, so a data point is not observed if it sort of falls inside a random interval. And again, just to sort of describe it briefly, so I'll be taking this random interval here. So let's say Li and Ri is the random interval. Okay? And then the problem is as follows. So let's say n identical items are put on test whose lifetimes are, let's say, T1, T2, T3 until Tn. Right? And then for the ith item, let's say Li and Ri with the random interval following some bivariate distribution. So depending on that bivariate distribution, we have to construct the appropriate estimates using appropriate techniques. Okay. All right. Now, generally speaking, if you move forward and construct this entire middle sensing scheme, so this is exactly what one gets. So let's say for the ith item, the Ti is observable only if Ti does not belong to the interval, which is Li Ri. Right? So very simply saying that so if Ti belongs to the interval, then Ti is not observed. And on the other hand, if Ti does not belong to the interval, then one observes the actual life point there. Okay? So if one talks about the construction of the actual scheme, so this is the construction of the scheme. So by the way, you have to involve two variables here. So let's say yi and delta I. Now, obviously, in this case, delta I is just a usual indicator variable. So this collection here takes two possible values. So the first collection could be Ti, 1 if Ti does not belong to the interval. So clearly one observes Ti. And then on the other hand, if Ti belongs to the interval, then one does not observe Ti. So one observes the interval itself. Right? So this is a very straightforward scheme. And then probably I'd like to point out that the middle censoring through this connection right here, or more like through this construction right here, becomes different from interval censoring scheme. So on one hand, you have interval censoring scheme. So I would say the major difference here is the construction of the actual data. Okay. And a very important point that both left censoring schemes and right censoring schemes are kind of derivatives of middle censoring. So depending on how you construct this interval right here, you can actually reduce the scheme to either left censoring or right censoring. All right, so I'll be taking a very practical problem and then sort of motivating the actual scheme or actual theme of the presentation here. So let's say assume that a group of people are told to provide satisfaction ratings, say between 1 and 5 stars, towards a product which they have purchased. This is more like you go on Amazon, you purchase a product and then provide some stars for the product. Okay. So further assume that these ratings can also be in the form of intervals. So this is a small twist here. So rather than actual ratings, one can also go and give interval ratings. So let's say 1, 2, 1, 3, 2, 5, etc. So in this case, let's say 2, 5 is an interval rating where the person is not fully convinced to provide a single rating, and hence he or she thinks that can be any number between 2 and 5. Okay. So this is the idea of bringing in some interval ratings. Okay? And obviously, once you have interval ratings and once you have non-interval ratings, the entire problem can be boiled down to a certain multinomial distribution very easy. All right, so I'll be briefly talking about estimation under one special case. So let's say assume that there can be only a single interval rating. So this entire construction of the problem. So let's say I, j is the only interval rating which is allowed, and then let's say Fij individuals opt for that. Okay. Then if you want to write down the actual multinomial scheme, it should boil down to this. So let's say Pij plus summation Pi happens to be 1. Right? So by the way, the only added part here I would say is Pij. So what is Pij? So Pij is the probability that a person gives the interval rating, which is I, j. Okay. And one writes down the likelihood function very carefully. It should boil down to that. And then once you have the likelihood function finding, MLEs is not a difficult task. So it so turns out that the MLEs for all these values happen to be these. And then MLEs of all the in-between values, so when I say in-between, you mean between I and j, happen to be these. Okay. So I would say this is the only difference here. So if any value falls in between I and j, the MLE is kind of changed. And for all the other values, you get the usual MLEs. Okay. All right. So again, if you refer back to our paper, we have many other cases, many other scenarios also. For example, what would happen if you assume 2 non-overlapping intervals? So let's say instead of just one interval, let's say a person can give, the idea is that if you assume, let's say 2 non-overlapping intervals, so maybe something like I1, J1, I2, J. Okay? Or on the other hand, you could have a case 3, which says assumes that two overlapping intervals are also possible. So let's say I1 J1 and I2 J2, where you have an overlap of I2 comma J2. Here. Okay, you have an overlap of I2 comma J2. Here. Okay. All right. So by the way, just for the sake of this presentation and time factor also, we are again taking an example only pertaining to case 1. Okay. Now again, as seen in the practical example earlier, so let's say we fix some value. So let's say I is 1, J is 2, and K is 5. So a person can give stars between 1 and 5, and then he or she can also give an interval rating which is 1 comma 2. Right? So the interval in this case becomes 1 comma 2. Okay. So in that case, the likelihood becomes that, and then all the MLEs become that. Right? Now again, the striking difference here is since you have an interval rating between 1 and 2. So MLEs for P1 and P2, which is P1 hat and P2 hat, is slightly different, and all the other MLEs stay the same. Okay. All right. Now, yeah. So I'll be taking up the same example for table here. So we've kind of bootstrapped some probabilities and some actual multinomial settings here. So what we've done is, let's say n is 500. So you have 500 people in the scheme, and then let's say we first fix some frequencies. So let's say number of people giving 1 stars equal 90, number of people giving 2 stars equal 70, and so on. And the number of people giving interval ratings is 200. Now again, if you notice here clearly, so we've kind of deliberately put this number to be higher than all the other frequencies, because if you give a person choice that he or she can also rate in between an interval, then probably what he or she will do is, rather than giving a single rating, he or she will give an interval. So chances that a person gives an interval rating, if he or she is allowed, is slightly more. Okay. All right. By the way, corresponding to all these frequencies, you get these Fi by n. So Fi by n's are the usual what do you call them, relative frequencies, by the way. And by the way, all these Pi hats are the actual estimates of all the probabilities. Now, what we've done here is, assuming all these are the actual probabilities, we kind of bootstrap a large number of multinomial settings, basically, and then from each of those we again found out the actual estimated probability. So we have two different rows here. So pi hat MLE stands for the actual MLEs, and then pi hat R stands for the actual estimates from the bootstrap samples. Okay. Now again, couple of points to note here. So one of them is, if you compare pi hat MLE for 1 and 2, they'll be slightly higher than the actual estimates or the actual relative frequencies. And why is that? Because if you're kind of bringing in the added interval rating in here, right? So the only interval rating allowed is 1 comma 2. So if you add that, then obviously the estimates for 1 star and 2 star are slightly higher than the actual numbers. And again, all the other values are pretty much the same. So all the other values are kind of compared. All right, so we come to the conclusions now. So we sort of developed a middle censoring scheme under a multinomial setup, which also allows outcomes to fall in an interval. Okay? And then we took a practical example of providing interval ratings towards the liking of a certain product to support our methodologies through Bootstrap. Okay, so this is a very brief conclusion of my talk here. And then if one looks at all the references, now again, so I just like to point to this reference right here. So by the way, Jamala Madaka and Mangalam back in 2003. So this was the paper where the author sort of introduced the idea of middle censoring. And then all that was done through some non-parametric approaches. Okay? Now, of course, after this 2003 paper, in literature, there have been like extensive works on middle censoring pertaining to different distributions. And ultimately, if one is more interested in the current work right here, so by the way, the current work is already published in Statistics and Probability Letters, and then this would be the actual reference for that. All right, so again, I'd like to thank all the organizers for allowing me to speak here. And again, I'm happy to take any questions if anything you might have. Thank you.
Yeah, thank you, Steve. Hello. Yeah. Any one or two questions we can take. Please, if you want to ask any question. I see that it's not issue to come to our field, medical field. Okay.
Right.
What we is especially cancer trial. When we deal, we deal with the cancer trial, cancer data, and censoring is always an issue with that data trial.
Correct.
And what we do is follow up, last follow up, this follow up, and event happening between that. But this follow up the event, and that is the way or we were able to follow up. We call it as censored at this today time point. But actually, the event happened between last follow up and this follow up.
Right,
And,
right.
and that is what you were talking about middle censoring, what I understood. Now,
Right,
my
exactly.
question is, did you look at that? If I look at it as middle censoring or censored at today, how much difference it make in terms of inference or in terms of estimates? Any major thing?
Yeah, I mean,
make
right. Yeah, so maybe according to me, I mean, both are different designs. I mean, this is my personal opinion. I mean, if, like you said, if the person fails to come up for the follow-up and the event is happening, that would be fit under the middle censoring. And then there's one more thing, which is double censoring. So maybe all the estimates and all the estimation techniques might differ there. So if you take both right and left, that would be an entirely different problem. But then through the practical problem I took up, this fits more into the idea of middle censoring.
Okay, okay. But you haven't looked at its. What I lose if I middle censoring, I take it as it's right censoring.
Right, maybe not. So this is not what we considered as of now. It's a good point.
Okay.
Yeah.
Okay.
Yeah.
Thank you. Thank you.
Thank you.
If no, thank you, Sudeep. But if no other question, we move to the next speaker. It's we have Maria Isabel from Spain. Maria, please go ahead.
I am Maria Isabel Garcia Planas, and I am going to talk about the bundle structure of the set of simultaneously diagonalizable and tuples of matrices. I start this talk showing the reasons that have led me to do this job. Then I introduce the elements for a well understanding regarding the concept of fiber bundle. To introduce the matrix bundle under the study. Next, you present the bundles obtained by restricting the group structure, and then you construct some invariants. And finally, we present some conclusions and some reference. You are interested in distinguish the M tuples of simultaneously diagonalizable real matrices from another within a differentiable variety. A good tool may be to try to identify it from the zeros of bundle section built on the variety, and then the characteristic classes allow to identify its instructions. First of all, we define what you mean by simultaneously the similarity. You say that two M tuples of square matrices are similar if and only if each matrix of the first tuple is similar to the corresponding matrix in the second one through the same matrix action. We are interested on the simultaneously diagonalizable M tuples of matrices, that is to say, M tuples that are similar to M tuple formed by M diagonal matrices. Now you introduce some notations used in the presentation. You denote by E the total space, by B the base space, and F the fiber, and by P the continuous succession of E over B, called the bundle projection. A fiber bundle is a structure formed by the total space, basis space, projection, and fiber, satisfying local triviality condition. That is to say, locally can be seen as the Cartesian product of the base and the fiber, what you show with this commutative diagram. The set of all opens and corresponding maps is called a local trivialization of the bundle. And for any P in the base space, the reciprocal image of the projection is called the fiber over P. Some particular cases are subbundles. A fiber bundle is a subbundle provided in the where E prime is a subspace of E, B prime is a subspace of B, and B prime is the restriction of the P to the E prime. principal bundles defined in the special case where the fiber is a group G. The fiber bundle is called principal bundle. In this case, any fiber is a space isomorphic to the group. More specifically, G acts freely without fixed point on the fibers. And in the case where all spaces participating in the bundle are smooth manifolds, and all the functions above are required to be smooth maps. You call that the bundle is a smooth fiber bundle. It is possible to induce bundles in the following manner. Let P a projection to the fiber bundle with fiber phi, and let if a map over B prime to B requires a continuous map, and you can construct a fiber bundle over E prime in the following manner. The total space is the Cartesian product of B prime to the space total of B, and you define the projection in the following manner. The projection over the pair of points B prime E is B prime. Defining if prime so that the following diagram is commutative. You have that the F E B prime P prime is a fiber bundle, so that the fibers on B corresponds to the fiber of the pre-image of B. An important concept in fiber bundles theory is a cross-section. That is a map to the base space to the total space, such that the image of a point P is then the fiber of B for each B in the basis space. Let's consider now a subbundle of our bundle, and you consider a cross-section of our bundle. Then this cross-section is also a cross-section of the fiber bundle. One of the main goals of studying cross-section is to account for the existence or not existence of global sections. When there are some problems to construct a global section, one says that there are an obstruction. Now we will try to apply all the concepts presented to the case where the total space is the set of m tuples of n squared real matrices, and the main tool is to consider the equivalent relation defined that can be seen as the action of a Lie group over the space. Analogously, you can define an action of the group over the Cartesian product in this manner. This bundle verifies the following properties. The group action data is free, transitive, and its orbits are diffeomorphic to the group. The set of m tuples of matrices is identified as the set of orbits class over the set. The group action preserves the fiber if T, and the Cartesian product with the product action gives the principal bundle. We will ask if this bundle determines a principal G bundle. For that, it is sufficient that the action G of N is to be free. This is obviously a necessary condition and proper. Remember that a group action is called free if it, in the case where there exist fixed elements for the action of a particular element of the groups, this element is necessary the identity. And a function between two topological spaces is proper if the pre-image of every compact set in final space is compact in the origin space. Our main interest is in simultaneously diagonalizable matrices that in terms of the group action are defined in the sense that the action for the sum element is an n tuple of diagonal matrices. As a consequence, you have that all equivalent m tuples of a simultaneously diagonalizable m tuple are also simultaneously diagonalizable. So you can restrict the action to the simultaneously diagonalizable matrices obtaining a principal subbundle of the bundle. Now we want to try to restrict the group structure in order to obtain more properties. For that, you consider the manifold M tuples of distinct points of Rn. The group of permutations acts over the seed, reordering in the same manner the elements of each point. The seed C can be identified with the set of M tuples of diagonal matrices with distinct M tuples of eigenvectors. Remember that the set of the diagonalizable matrices with different eigenvalues is generic in the space of all matrices. The natural representation of a permutation in a matrix form permits us to conclude that the map phi preserves the equivalence relation, so you have this commutative diagram. Now you consider the set defined by this relation. And you have that the subgroup sigma n acts over this set in this manner. From this action, you can induce a sigma n bundle over C, represented by this diagram commutative. And all you have a complete diagram commutative as in this manner. Related to the existence of global sections are characteristics classes that are global invariants that measure the deviation of the local product structure from a global product structure. The theory of characteristic classes generalized the idea of obstructions to construct cross-sections of fiber bundles. A characteristic class is an element of a cohomology theory defined over topological spaces. Now we are going to define invariance. You consider the M tuple of matrices and a homogeneous polynomial of m square variables, that is to say, by monomials of the same degree, and that degree of this monomial will be the degree of the polynomial. This polynomial is an invariant in the space of M tuple of matrices if it is the same of all equivalent M tuples. Obviously, every polynomial terminates a function of the space and F tuples of matrices to the set of real numbers, and this function is only determined by said polynomial. Given an M tuple of matrices, you can associate the polynomial product of characteristic polynomials of each matrix in M tuple. This polynomial is invariant in the set of M tuples of matrices. You can consider an M tuple of simultaneously diagonalizable M tuples, taking into account the invariance of the characteristic polynomial. You have that the polynomial is written as polynomials sigma that are called now you consider M tuples simultaneously diagonalizable M tuples, and you can write in this manner, and these polynomials are invariants, and these polynomials for product of permutations. Now let us consider an invariant polynomial where xg are n matrices with elements x, e, k, g in a space of two differential forms in the space of M tuples of matrices. And since the outer product of forming of an order is commutative, then the polynomial PDT is in the variables x, e, k, g belongs to this space of forms, defining a characteristic classes where if curvature is curvature chart of the variety. As a conclusion, you want to say that this work, a review of the simultaneous diagonalization of n tuples of matrices for its applications in science has been presented. This kind of family of linear operators have been analyzed using geometric constructions, such as the principal bundles, and associating them with a cohomology class defined from invariant polynomials that permit measure the deviation of local product structure from the global structure. Some references used for this work are these ones, and thanks all for your attention.
Thank you very much, Maria. For yeah, any question or any queries? Anybody want to respond? I don't see any hands up, any question. Thank you very much. So we move to the next presentation. It is by Lawrence Emily from Cameroon. Lawrence, for yes, please go ahead.
So hello everyone. Thank you so much for having us being a part of this ALAPS 2020 event in Meher, India. My name is Lawrence Emily U, and I'm currently a lecturer at the University of Douala, Cameroon, at the Department of Mathematics and Computer Sciences. The work is done jointly with Professor Maria Isabel Garcia Planas, which is currently lecturing at the Universitat Politécnica de Catalunya in Spain at the Department of Applied Mathematics. So here, our work is structured as follows. We first go through an introduction just to present the concepts and content of the work. We present the topics of steganography, convolutional coding, and convolutional coding under the linear systems theory, just some definitions, introductions. And also we'll talk about the relationship between steganography and coding, and probably show out some examples and protocols, and insist more on the steganography and convolutional coding, which is our main point of interest. We have a conclusion and give out some references. Okay, so for this work, we introduce an application of the convolutional coding theory in steganography. As is known, block codes are largely used for the simulation of information using the steganography process. Here we suggest a steganography protocol based on convolutional codes defined under the linear systems theory. So what is steganography? Steganography is a science used to protect some information to be exchanged by hiding its original existence. A classical example of such is called the prisoner's problem, and in that scheme, A and B are two prisoners imprisoned in separate cells that need to plan their escape. Because they can only communicate under the surveillance of a warden, they need undetectability imperatively throughout this process. So a steganography process scheme is characterized by a message to be embedded, secret message M, the choice of a communication support, which is the cover object C, an embedding function M for our specific case here, an asserting function rec for recovery, and sometimes, occasionally, an optional steganography key management. So a digital steganographic scheme S of type Kn over an alphabet A is a pair of functions embedding and recovery, such that the recovery of embedding of secret message M into the cover C gives us back the message M for all cover vectors and all possible secret messages in respective spaces. So we need to keep in mind also the length, N being the cover length and K being the embedding capacity. So if we define S, our steganographic scheme made of those two functions, embedding and recovery of type NK over the alphabet A, then the recovery map needs to be surjective and the embedding map needs to be injective. So convolutional codes are a type of...
Dear all, there seems to be a technical issue. We are sharing the window again. Just a moment.
Yeah, slides are not moving, I think. It's
error correcting codes in which each KB information symbol to be encoded is transformed into an n-bit symbol with K over n being the code rate. So more formally, we define a convolutional code of length n and dimension k as a k-rank submodule of FQNZ. So given a convolutional code C with its encoding matrix J, there always exists a quadruple of matrices ABCD associated to J given by this equation, with A, B, C, and D being constant matrices over the field F, and keep in mind that U, X, and Y are the input and output vectors respectively. So the output observability, which is a control property of the linear system, is defined such as is defined by this definition. A system ABCD is said to be output of observable if the state sequence X0 to XL is uniquely determined by the knowledge of the output sequence Y0 to YL for a finite number of steps N. So we can call TL ABCD the matrix given as such, and we denote that the system ABCD is output observable if and only if this matrix TL has full rank. Some interesting steganographic protocols have already been defined from coding theory using block codes. A popular method used for steganography with coding theory is called the syndrome coding. From a steganography point of view, the idea here for this syndrome coding is to find a flip pattern AX of minimal support to decrease distortion on the cover object. So here we talk about the SCIGO scheme from convolutional codes. Here is the embedding part. So for the embedding, the idea is to consider the protocol based on the output observability matrix, considers as the parity check matrix. And we decide to approach it in a sequential fashion, of course, with convolutional codes. At each step, the protocol embeds the secret message sequence by altering lightly the cover sequence. As well as for the recovery process consists of the encoding of the SCIGO sequence. So we define the quasi-syndrome S. This is a notion that we define here, which is the value from which we choose the estimated perturbation E for embedding M into U. And we also consider the variable tau as the minimum number of linearly dependent columns of T. So here we show our own embedding algorithm for embedding function M. The input is the secret message M and the cover sequence U. The output is the SCIGO sequence at each step. And here we also have an extracting algorithm for recovery function. So of course we output our original secret message. So we give out here just one example with convolutional codes given by the quadruple of matrices ABCD. Okay, and at the end, after all the process, we realize that we have an average number of embedding changes given here as much as an average distortion. From this protocol that we have defined, okay, for this implementation, we can give out some conditions on the sequence of the flip sequence used for embedding. We give out some information on the weight. This is the weight of the flip sequence here. As much as we give out some conditions on the embedding capacity, okay, of the secret message, and here the possible modification. So in conclusion for this talk, we suggested a steganographic scheme based on the representation of convolutional codes within the linear system theory. So the big idea here is to consider these procedures based on the output observability matrix, and that method revealed interesting results, such as an ability to hide a tremendous amount of information and better computing complexity with very little distortion under specific conditions. So yes, so here are some references that we use for our work. So we would like to thank you very much for your attention, and we are open for any interrogation. Thank you very much for having us.
Thank you very much, Lawrence Emily. Now, any clarification? Anyone would like to please? Any question or the thing is, it's yeah, with the Prasad, her email will be available and you can communicate to her. If that is the case, thank you very much, and we move to the next presenter. Next presenter is Dr. Pavan Kumar from Aligarh Muslim University, India. Yes, Pavan, over to you.
This is Pawan Kumar, a research scholar at the Department of Mathematics, Aligarh Muslim University, Aligarh, India. I am here to present my paper entitled A Class of Linear Codes with Their Complete Weight Enumerators over Finite Field. These are the outlines of my presentation. Introduction and preliminaries, main results, references. Introduction and preliminaries. For any positive integer m and or prime p, let Fpm be a finite field with p to the power m elements. Definition 1. An NKD linear code over Fpm is a k-dimensional subspace of Fpm and with minimum Hamming distance d. Weight of a code word C in a code C is the number of non-zero coordinates of the code word C. In definition 2, we have defined weight enumerator of the code C. Let Fpa be any subfield of Fpm with m upon e strictly greater than 2. In definition 3, we have defined complete weight enumerator of the code C. We define the cyclotomic number to be the number of solution of the equation 1. An additive character chi of Fpm is a mapping from Fpm into the multiplicative group of complex numbers of absolute value 1 with chi of g1 plus g2 is equal to chi of g1 to chi of g2 for all g1 g2 belongs to Fpm. Equation 2 defines additive character of Fpm. Equation 3 defines multiplicative character of Fpm. Multiplicative character of Fpm is the character of multiplicative group Fpm star. Equation 4 defines quadratic Gauss sum of Fpm, and equation 5 defines quadratic Gauss sum of Fpe. The lemma 1 describes explicit values of g and g bar, where g and g bar are quadratic Gauss sum of Fpm and Fpe respectively. Lemma 2. If s greater than or equal to is even, then eta y is equal to 1 for each y belongs to Fp star. If s is odd, then eta y is equal to eta bar y for each y belongs to Fp star. Lemma 3 tells cyclotomic numbers for n is equal to 2. Let D be a subset of Fpm star. A linear code CD of length n over Fp is defined by equation 6, where Tr is the absolute race function from Fpm onto Fp. This construction is proposed by Ding et al. Yang et al. In their paper published in Finite Field and their applications constructed linear codes and their complete weight enumerators over finite field Fp. Main results. In the present work, motivated by the results of Yang et al., we construct linear codes over Fpe, where Fe is a subfield of Fp. We define our linear code by equation 7 and then determine the complete weight enumerator and weight enumerator of the linear code CD. Moreover, the presented code is optimal with respect to the Grishmer bound, provided that m upon e is equal to 3. In fact, it is MDS when m upon e is equal to 3. NC tells us the frequency of C in a given code word. Theorem 1. In Theorem 1, we determine the complete weight enumerator of the code CD defined by equation 7 under the condition 2 divides S and P divides S. Corollary 1. If 2 divides S and P divides S, then the weight distribution of the linear code CD defined by 7 is given in table 1. This is the example 1 for the theorem 1 and corollary 1. Theorem 2. In this theorem, we determine complete weight enumerator of the code CD defined by 7 under the condition 2 divides S and P does not divide S. This theorem has large presentation, so we have divided it into two blocks. This is block 1 and this is block 2. Corollary 2. If 2 divides S and P does not divide S, then the weight distribution of the linear code CD defined by 7 is given in table 2. This is the example 2 for the theorem 2 and corollary 2. Remark. In this remark, we have shown that our code determined in example 2 has improved relative minimum distance compared to the linear codes obtained in 6 and 2. Theorem 3. In this theorem, we determine complete weight enumerator for the linear code CD under the condition that Q does not divide S and P divides S. This theorem also has a large presentation, so we have divided it into two blocks. This is block 1 and this is block 2. Corollary 3. If 2 does not divide S and P divides S, then the weight distribution of the linear code CD defined by 7 is given in the following table 3. This is example 3. In this example, we have constructed a MDS code with complete weight enumerator and weight. This is the last theorem. In this theorem, we determine complete weight enumerator of the linear code CD under the condition that 2 does not divide S and P does not divide S. Due to large presentation of this theorem, we have divided into two blocks. This is block 1 and this is block 2. Corollary 4. In this corollary, if 2 does not divide S and P does not divide S, then the weight distribution of linear code CD defined by 7 is given in table 2. This is table 4. This is the last result, that is corollary 5. In this corollary, we have shown that our constructed code CD is optimal if S is equal to 3. These are the references. Thank you.
Thank you very much, Pavan. It's any queries or any suggestions, any advice, or anybody senior members it's listening to it. It's want to give any suggestion. Okay, I think it's there is nothing even you can think about it. It's after because we are on time. It's so after next presentations. If we have few couple of minutes, it's anybody need to give suggestion for anyone, it's you can do that. Okay. With that note, I move to the last presentation. It's David Raj, yes, from Sikkim Manipal Institute of Technology, India. Yeah, David, over to you.
Hello everyone. Myself David Raj. I am an assistant professor in Department of Mathematics in Sikkim Manipal Institute of Technology, Sikkim. Today I am here to give a contributory talk on a new characterization of Drasin index. First things first, what is a Drasin index? Drasin index of a matrix A is the smallest positive integer d such that the rank of a to the power d is equal to rank of a to the power d plus 1. As a preliminary, we'll see what is the generalized inverse first of all. We say a matrix G as a generalized inverse of A if AGA is equal to A. Similarly, we say a matrix G as an outer inverse of A if GAG is equal to G. Prasad and Mogna have considered square matrices over real or complex field to define and study a new kind of outer inverse G of A, which they call that as co-reap inverse of A, which is a matrix G such that it satisfies the column space of G is equal to row space of G is equal to column space of a to the power k, where k is some positive integer. As a preliminary, first of all, we'll check what is the bordering technique, because this is what we're going to use as a tool to define a new characterization for Drazen index. Okay, we have a rectangular matrix over here 0 1 1 1 1 0. So what we can do here is we can append one more row below that or above that and then make it as a square matrix and check whether it is invertible or not. So bordering technique is usually defined for a matrix which is given in the form of rectangular or even a square, and appending a suitable number of rows and suitable number of columns and make them into a invertible matrices, right? For example, you have a rectangular matrix over here as well. By adding 1 0 0, that becomes a invertible matrix. Similarly, you have a square matrix over here. You can see that the last two columns are identical, so the matrix is singular. But now by appending one more row and one more column appropriately, I get a matrix which is a non-singular matrix, correct? Okay, how does it going to get this bordering technique for us? In 1980s, Namaguchi has actually shown that any generalized inverse of a real matrix A of rank R can be obtained by looking into a suitable bordered matrix. Similarly, in 1991, Egambram has proved that given any outer inverse of GA, there is always a suitable border T such that G is a block corresponding to A in the inverse of T. In 1996, Prasad and Rao has considered the matrices over commutative ring and related the existence of such bordering with the rank factorizations of I minus AG and I minus GA, where G is the generalized inverse of A. So these works have helped us, these works have motivated us to come up with a bordering technique to find a co-repeat inverse in that regard, right? So for that reason, we define a suitable bordering for finding the co-repeat inverse. In that way, we introduce a new type of bordering called k-invertible bordering. The definition goes like this. You take in any n by n matrix over real or complex numbers and keep the k as 0 less than or equal to k less than or equal to minimum of m comma n. Then the matrix A is said to have a k invertible bordering if there exists a matrix P of size m by m minus k, and there exists a matrix Q of size n minus k by n, and also there exists a matrix R of size n minus k by m minus k, such that this particular block matrix is invertible. Now let me explain one procedure to find the co-repeat inverse, and I'll try to understand what's going to happen here, and also I will give it as a theorem later. Let's consider this matrix A, and if you see that matrix, this matrix rank is 3. Now let me define some numbers like Q, 1, 2, 3. I define that K of Q as the rank of A to the power Q, corresponding to the matrix TQ with the help of P of size 4 by 4 minus K of Q, given by the basis for null space of A to the power Q to the power T. You can see that for Q equal to 1, we have A to the power 1. For that, K of Q should be the rank of A to the power 1, which means K of 1 should be the rank of A to the power 1. As I have already mentioned, A to the power 1 is A itself, and whose rank is already 3, therefore 3. Now, who will be the P? The P will be the basis of the null space of A to the power 1 transpose. So you can see that A to the power 1 transpose, of course, you can compute it, that this one will be the basis for the null space. Now you can find T1 from this, because you know that P is already given here, is over here, and now the Q and R should be there. I give you the Q as the P transpose. Take the P transpose and put it in the place of Q, and then take the 0 matrix and put it in the place of R. Now I have a new T1. It's a singular, as determinant of T1 is equal to 0. Similarly, for Q equal to 2, what we can do, we can find A square, and that looks like this. And the K of 2 is the rank of A square, which is, you can say that this is also 2 here. And the P value would be the null space of A square transpose, which is means the basis of the null squares of A square transpose, and that P is actually, you can compute that this would be the basis of that. Now what we are supposed to do, we have to find the T here. So let's find T2. So the T2 is X, this is A square, and this is P, and this is P transpose, and this is my R over here, right? And if you can compute the determinant, this also gives you a singular matrix, which means the determinant is 0 over here as well, right? Now for the Q equal to 3, we can do the same process. Now A cube will be computed, that is 16 times of such a nice matrix, and then K of 3 is equal to 3, K of 3 equal to 1, which is null space would be rank of A to the power 3 will be 1 for sure, because everything, all of the columns are scalar multiples of each other, and P value is actually equal to the null basis of the null space of A cube transpose, and that is 1 0 0 0 1 0 0 0 1 and 1 minus 1. Further, if you see the T3 is actually the matrix A cube and then the P and then the P transpose, correct? You can check the following. Q equal to 3 is the least positive integer such that TQ is non-singular. If I start with 1, 2, 3, then I reach 3 as the least positive integer. This is that TQ is the non-singular, and of course TQ belongs to B3 of A, which means that is 3 invertible bordered matrix, right? And the index of A is also 3, which could be easily verified by rank of A to the power 3 is equal to rank of A to the power 4. Means if you compute rank of A to the power 4, it cannot change better. And also rank of A to the power 2 is equal to 2. Therefore, rank of A square and rank of A cube are not same, right? That gave us this theorem. Before that, we'll also find the corresponding inverse of the matrix given over here using this border here. Now you can see that the corresponding inverse of A is sitting inside the block, which is exactly corresponding to the matrix A, which is in T3, right? So you can say that this is the place where the matrix was sitting in terms of A, instead of A. Now the matrix corresponding to A is been taken care, and that is the corresponding inverse of A. You can verify it by your direct computation, that it is an outer inverse GAG equal to G, and you can observe that it is a whose column space and row space, all of them are same because they have their same multiple. Everything is a scalar multiple of each other. Means you take any column and you take any row, that you can realize that. And it's also equal to column space of A to the power 3, because A to the power 3, let me show you, A to the power 3 is exactly similar to this, and that is nothing but the span of 1 minus 1 1 minus 1, that I have just written. What is it? Here's a theorem which confirms all these computations will lead you to the corresponding inverse and also lead you to the Drasin index new characterization. For 0 less than k less than or equal to r, if you take t is APQ0, then if T inverse is G, X, Y, Z, then the G corresponding to A over here will be an outer inverse with rank A and with rank K, and column space of G is equal to row space of Q transpose here, and then row space of G is equal to column space of P transpose. That gives this theorem, which is the new characterization of Drasin index. As we have noted in the example, by the time we reach TQ belongs to P K of Q of A, then the matrix corresponding to A in T inverse K of Q was giving the corresponding inverse of A. And moreover, the value of Q, whichever we have obtained to compute the T inverse K of Q, was the Drasin index of A. This is a certain theorem. It has been already proved. I'm skipping the proof of the theorems just for the sake of time constraints. So at the end of the day, what we got here is the new characterization of a Drasin index. Here it goes once again. Is let A is a matrix over C, then D is to be a Drazen index of A if D is the smallest positive integer such that A P transpose 0, where column space of P is equal to column space of A to the power T perpendicular means orthogonal complement of column space of A to the power P is invertible. These are my references for the presentation, and thank you.
Thank you. Any question? Thank you, David. Thank you. Congratulations for your PhD as well as your marriage.
Thank you, sir.
Yes,
Thank you so much. Thank you so much.
Thank you. Yes.
Nice to meet you, sir. After a long time I'm seeing you in the screen.
Yes, I never thought I will be chairing a session like this.
Thank
Okay.
you so much.
So, any question to David as well as other speakers also there? 1 or 2 minutes. That because it's the next session is it's 1 o'clock. It should be on. I think no. Okay. So with that, it's end this session. Thank you very much again for all speakers. And thank you very much for the organizers for giving this opportunity. And it's thank you very much, Dr. Prasad. Over to the MC back.
Thank you very much, Nair sir, for joining us with us today.
We have our next session on contributory talks, which will be shared by Dr. R. Balaji, Indian Institute of Technology, Madras.
And the contributory speakers are Miriam Simone from Madras Christian College, Chennai, India; Nayan Bhatt K, Manipal Academy of Higher Education, Manipal; Patricia from University of Beira Interior, Covilhã, Portugal; Raju Dasari from KITS Warangal, India; Ramesh Renukunta from KITS Warangal. I now request Professor Balaji to take over the session.
Yeah, thank you. Thank you very much. Can you hear me? Can you hear me?
Yes, sir. Yes, sir. Yes, sir. You're audible, sir.
Yeah, okay, fine. Okay, so this is a contributory session, and we will be having 3 + 2 5 talks. Okay, so 5 talks. I think 9 minutes. Professor Prasad. No.
Sir, he is a little outside, sir. He just moved off.
Okay, okay, no problem. So 5 maybe 5 into 10, 50 minutes. Okay, so and in between there may be some questions. So I request all the speakers to stick to time. Okay, so we will start the session. Okay, Mr. Simon is here. Simon. Okay, so he'll be talking on evaluating technical efficiency and the ranking of decision-making units, DEA and super efficiency DEA approach. So Professor Simon comes from Madras Christian College, Chennai. Okay. And,
Yes, I'm
so welcome, Simon. Okay, welcome, Simon.
Yes, I'm here, and I've sent the video already. I think they would be playing the video now.
Fine, no problem.
Yeah, thank you.
Yeah, please start this talk.
Good day to all. I'm Miriam. I work as a faculty of statistics in Madras Christian College, and my co-author is my research supervisor, who is the head of the Department of Statistics in Presidency College, Dr. V. Prakash. And my topic is evaluating technical efficiency and ranking of decision-making units, DEA, and super efficiency DEA approach. Abstract. Performance or efficiency evaluation is an important aspect in production process. Both parametric and non-parametric methods are available for performance efficiency evaluation. Data envelopment analysis is one of the most popular non-parametric techniques based on linear programming approach used for measuring efficiency of similar type of organizations, generally termed as DMUs, with multiple inputs and outputs. DEA provides efficiency score for each DMU and benchmarks inefficient units. Then the decision-making units could be ranked based on peer counts, but tie may occur among the ranks. So to break the tie, the super efficiency model by Anderson Peterson is applied in this study. In this paper, we have considered manufacturing industries pertaining to dairy products in India with 3 inputs and 2 outputs, and the empirical investigation and results are outlined. The objective of my study is India is the world's largest producer of dairy products and has the world's largest dairy herd. It is a requisite to measure the performance of the manufacturing units of dairy products in India. The tool that I've employed in the study is DEA. What is DEA? Data Envelopment Analysis. DEA is a mathematical programming based technique to assess the relative performance of individuals or organizations which are termed as decision-making units. It has been successfully employed for assessing the relative performance of a set of firms that use a variety of identical inputs to produce a variety of identical outputs. The principles of DEA date back to Farrell, 1957. DMUs. We've been talking about DMUs. What exactly are DMUs? The term DMUs refers to the units whose performance are evaluated. Possible examples range from production facilities, supermarkets, banks, schools, hospitals, and government agencies. DMUs perform essentially the same task using similar inputs to produce similar outputs. Inputs are the source consumed by the DMUs, outputs are the goods and services produced by the DMUs. Okay. To start with, in DEA, we have the basic model, which is the Charnes-Cooper-Rhodes model, CCR model. And here we try to find the efficiency score of the DMUs. Okay, it is a maximization, output maximization problem. And when this model is run, it gives the maximum value of the objective function and the weights of the inputs and outputs of all DMUs. Then, to solve this, what we have done is the original problem that I showed you was the primal problem. So we've converted into the dual problem because dual problem has lesser number of constraints and it has been solved. So this will give me the efficiency score and the weight of each DMU. And then Banker-Charnes, another model, Banker-Charnes-Cooper model, has also been applied to my data. And here, similarly, we find the efficiency score as well as the weight of the jth DMU. So, but when we apply the Banker-Charnes-Cooper model, what happens is there is a tie. So to break the tie, super efficiency model is being used. So we read that traditional DEA models commonly evaluate multiple units as efficient in case of large number of inputs and outputs. Hence, when we try to rank the DMUs, tie may occur. To overcome this weakness, super efficiency DEA models were developed and applied. So this is a super efficiency CCR model. This is a super efficiency BCC model. So these are all models which have already been developed. So I applied it to my data, and my data is the secondary data taken from annual survey of India 2017-18. The data considered comprises of 3 inputs and 2 outputs pertaining to manufacturing industries of dairy products in 23 states of India. The input variables studied are number of factories, number of employees, gross value of addition to fixed capital, and output variables, total output and profits. Okay, this is a result that I have obtained after applying the CCR, the first model that I was talking about. And if you look at it, you will see the first column as the DMUs, the 23 states. First the serial number, then the DMUs, and then you have the efficiency scores. In the efficiency scores, you can find value 1. Wherever you find value 1, it means that that particular DMU is an efficient DMU. So in this case, you will find that Delhi, Himachal Pradesh, Sikkim and Uttarakhand turns out to be efficient DMUs. And when you identify efficient DMUs, here it is not only self-efficient, it also serves as peers for the other inefficient DMUs. So if you look at Andhra Pradesh, they have the benchmark. So what are the efficient DMUs which serves as peers for this Andhra Pradesh is the 4th one, 7th one and the 18th one, which means Delhi, Himachal Pradesh and Sikkim serve as peers for Andhra Pradesh. And that 0.33 means that only 33% inputs have been used. Remaining 67% outputs, 67% could be reduced. 67% of inputs could be reduced to obtain the same output. So the efficiency score
they are less, they are not equal to 1, they are not 100%. CCR model. So here we rank the efficiency scores. The efficient DMUs, you have 4, 7, 18, and 22. Based on, if you look at the previous table, you will see that the fourth value, it is occurring 19 times as peers for other inefficient DMUs. Similarly, this Himachal Pradesh occurs 18 times as peers for the other DMUs. So based on that, we rank them as 1, 2, 3, 4. Similarly, we also apply the BCC model, and we find that BCC model is a revised version of a CCR model, and we find more number of DMUs which are efficient here. That is Andhra Pradesh, Delhi, Gujarat, Himachal Pradesh, Maharashtra, Sikkim, Uttar Pradesh, and Uttarakhand. All these have efficiency score 1. All these are efficient, and they also serve as peers for other inefficient DMUs. So we see that Andhra Pradesh serves as peer for 3 inefficient DMUs. You find the value 3 here. So like that. Next, Delhi serves as peer for 15 inefficient DMUs. So based on that, we try to rank them. When you try to rank them, you see that first value, peer counts, highest peer count is 15. So that is ranked as 1. But when it comes to the next one, you see that 8, there are 2 8s here, which means there is a tie. To break, I've not broken the tie here. I've just ranked them as 2 and 2 here. But generally, we need to break this tie. To break this tie is what we use the super efficiency model. So the BCC super efficiency model has been applied to the data, and this is the result that I get. And in super efficiency model, you will see that the efficiency score will be greater than, if it is greater than or equal to 1, it means that that particular DMU is efficient. You find that Andhra Pradesh is efficient, and then coming down to Himachal Pradesh is efficient, and then you have here Sikkim as efficient, and Uttar Pradesh and Uttarakhand as efficient. And based on their values, the higher value is given rank 1 and rank 2 and so on like that. So we have ranked the efficient DMUs here. So finally, we were able to break the tie here. But one problem that occurred here is we have big. You can find the value big in 2 states. That means those states, there is infeasibility problem there. So my research is progressing on finding a solution for this infeasibility problem. So this is what I have done. So conclusion, I've applied both CCR and BCC DEM models, and when I applied BCC model, there was a tie which was broken by the super efficiency model. The problem of dealing with infeasibility and super efficiency model is being attempted as per the study. These are my references. I express my heartfelt gratitude to all the organizers who gave me an opportunity to present my paper in this conference. I also thank the chairperson and other members and participants for their patient listening. Thank you very much.
Any questions from the audience, please? Any questions from the audience? Okay, I think if there is no question, then we will pass on to the next talk. Okay, so next talk will be by Mr. Nayan Bhatt. I think he is a student of Professor Prasad. Okay, he will be talking on inverse complements of a matrix and generalized inverses. No, it's Nayan Bhatt.
Yes, sir.
Okay.
Yes, sir.
Nayan Bhatt. Okay. Okay, Nayan Bhatt, please start your talk.
Yes,
hello everyone. I am Nayan Bhatt, PhD scholar in the Department of Data Science, PSPH, Manipal. Today I will be presenting on inverse complements of a matrix and generalized inverses. It's a joint work with Professor K. Manjunatha Prasad. These are the contents of my presentation. These are the notations I am following throughout my presentation. We say that 2 matrices are space equivalent if column space of A and column space of B are same, and row space of A and row space of B are same. Index of matrix A is the smallest positive integer k such that rank of A power k is rank of A power k plus. We use the following notations. Direct sum of subspaces S and T is denoted by S direct sum T, and if subspaces S and T are orthogonal complements of each other and direct sum of S and T, then we denote it by S orthogonal direct sum T. Two rectangular matrices P and C of same size are said to be disjoint if intersection of their column spaces and row spaces are zero space. For disjoint matrices B and C, the sum is denoted by B direct sum C. We often call it as weakly bicomplementary matrices. For more information, inverse complement of a matrix and inverse complemented matrix of a matrix is introduced by Igambara in 5. Given a square matrix B, a matrix C disjoint with B such that B plus C is invertible is called an inverse complementary matrix or inverse complement matrix of matrix B, and B plus C is known as inverse complemented matrix of B. Set of all inverse complementary matrices is denoted by K of B, and set of all inverse complemented matrices of B is denoted by C of B. Let me introduce different generalized inverses. Given an m by n matrix A over real field, consider an n by m matrix G satisfying these 4 conditions. Whenever the matrix A is a square, that is m equal to n, the following matrix equations are considered in addition to the above 4 equations. Matrix G satisfying equation 1 is called generalized inverse of A, and an arbitrary generalized inverse of A is denoted by A minus. Matrix G satisfying equation 2 is called as outer inverse of A, and an arbitrary outer inverse of A is denoted by A equal. Matrix G satisfying equations 1 and 2 is called reflexive generalized inverse of A, and an arbitrary reflexive generalized inverse of A is denoted by A r minus. Matrix G satisfying all the 4 equations is known as the Moore-Penrose inverse of A, and the Moore-Penrose inverse of A is denoted. Matrix G satisfying equations 1, 2, and 5 is known as group inverse of, and the group inverse of A is denoted by A sharp. Matrix G satisfying equations I, J, and so on K is known as IJK inverse of A, and set of all IJK inverse of A is denoted by A by this. Let A be a square matrix over real field. A matrix G is said to be a core EP generalized inverse of A if G is an outer inverse of A with column space of G is identical with row space of G is identical with column space of A, and it is denoted by A sharp, A circled sharp. A matrix G is said to be a star core EP generalized inverse of A if G is an outer inverse of A with column space of G is identical with row space of G is identical with row space of A, and it is denoted by A star circled sharp. In fact, core inverse of matrix A is introduced by Buxelry and Trenkler in 1, and later it is rephrased as a core EP inverse by Prasad and Mohana. For more information regarding core EP inverse, one may refer to Prasad and Mohana 7. Theorem 1.1 is discussed in Bapat et al. 2. Given m by n matrix over R, real field R, if G1 and G2 are outer inverses of A such that they are space equivalent, then they are equal. Theorem 1.2 is discussed in Igambaram 5. Given a square matrix A with a complementary matrix C, there exist unique pair of reflexive generalized inverses GA and GC of A and C respectively, such that A plus C inverse is GA plus GC, and C into GA, GA into C are equal to 0. In the above case, GA and GC are given by these expressions. The matrices G and GC are conveniently denoted as AC minus and CA minus respectively. Lemma 1.3 is discussed in Butt et al. 4. Given n by n matrix over real field R and reflexive generalized inverse G, and rank of A is R, which is less than n size of the matrix. There exists a non-trivial matrix which is inverse complement of matrix A, such that G into C, C into G is equal to 0. In fact, G is equal to AC. CA is non-empty. Theorem 1.4 is discussed in 4. That is again in but et.al. For square matrix, n by n matrix over real field R and inverse complementary matrix C, we have the AC minus is invariant for all C with the same row and column spaces, and set of all generalized universes and reflexive generalized universes are given by the expression provided here. Theorem 1.5. In fact, the 1, 2, 3, and 4 of this theorem is already discussed by Igamaram in his paper on disjoint sections and generalized universes of matrix. But here we provide a different proof for the same, and along with that we also give proof for the results 5 and in fact we have provided the proof using space equivalent properties of matrices without an inverse. So I will skip the proof because our main intention is to discuss on the computational procedure to find different classes of generalized inverses. Given a square matrix A, of course on real field, from theorem 1.2 and lemma 1.3, given inverse complementary matrix C, we can find reflexive generalized inverse of A, that is G, such that C into G, G into C equal to 0 and vice versa. In other words, G is AC minus. In the following, we shall discuss procedures to obtain different classes of generalized inverses given an inverse complementary matrix. Initially, obtain G is equal to AC minus is equal to A plus C inverse A into A plus C inverse and rank factorizations of I minus AG and I minus GA. Let that be E1 F1, E1 into F1 and E2 into F2 respectively. Then the class of all generalized inverses and reflexive generalized inverses are given by these expressions. To find the class of all 1, 3 inverses and 1, 2, 3 inverses, first obtain D is equal to F1 transpose F2. Then one may see that column space of and row space of column space of D and column space of A are disjoint, and row space of A and row space of D are disjoint, and A plus D is invertible because rank of A plus D is rank of A plus rank of D, which is again rank of in fact it is size of the matrix n. So D will be inverse complement of matrix A. So now by using part 2 of theorem 1.4, we have AD minus in the set of all 1, 2, 3 inverses. So just compute AD minus, then set of all 1, 3 inverses is given by this expression, and set of all 1, 2, 3 inverses is given by this expression. To find the set of all 1, 4 inverses and 1, 2, 4 inverses, first obtain D is equal to E1 into E2 transpose. Then one may observe that A and D are disjoint matrices, and A plus D is invertible as like we have observed earlier. So D will be inverse complement of matrix A, and from part 3 of the theorem 1.5 we have AD minus in the set of all 1 to 4 inverses of A. So just compute AD minus, then set of all 1, 4 and 1 to 4 inverses are given by these expressions. To find the Moore-Penrose inverse of A or 1, 2, 3, 4 inverse, first obtain D is equal to F1 transpose E2. Then one may observe that A and D are disjoint and A plus D is invertible. So D will be inverse complementary matrix of A. So from part 1 of the theorem 1.5, we have AD minus is equal to A plus D inverse A into A plus D inverse, which is 1, 2, 3, 4 inverse. That is Moore-Penrose inverse. So just compute AD minus. Thus we have A plus. To find the set of all 1, 5 inverses and group inverse, we have to follow the similar kind of procedures. First, we have to obtain the decomposition, but one should remember that index of the matrix must be 1 in order to discuss about group inverse. Whenever the index of matrix A is 1, group inverse, co-repeat generalized inverse, and star co-repeat generalized inverse always exist. And by the equivalent definitions of index, we have if index of A is 1, then intersection of column space of A and null space of A is 0, and intersection of column space of A transpose and null space of A transpose is 0. So using that, one may observe that A and D are disjoint and A plus D is invertible. So D will be inverse complement of A. So from part 4 of theorem 1.5, we have AD minus as the group inverse of A. So just compute AD minus, then set of all 1,5 inverses is given by this expression. Similarly, we can obtain co-repeat generalized inverse and star co-repeat generalized inverse. Let me illustrate this with an example. Consider the matrices A and C as given here, where rank of A is same as rank of A square. In fact, that is 3, and rank of C is 1. Since rank of A and rank of A square are same, index of matrix generalized inverse and star co-repeat generalized inverse of the given matrix A exist. Now observe that A plus C is invertible because rank of A plus C is 4, which is 3 plus 1. That is nothing but rank of A plus rank of C. So and C are disjoint matrices such that A plus C is invertible, and hence C is inverse complement of matrix. Now just find out A plus C inverse. We see that this is the matrix. Now take G is equal to AC minus to observe that G is this matrix, and then find out AG and GA to obtain I minus AG and I minus GA, from which we get rank factorizations of I minus AG and I minus GA. Let that be E1 F1 and E2 F2 respectively. Then the set of all generalized inverses and reflexive generalized inverses are given by this expression. Set of all 1, 3 inverses and 1, 2, 3 inverses is obtained by just following the procedure what we have explained earlier. That is, first to obtain D is equal to F1 transpose F2. So we have that in our hand. We'll just find out D. Observe that D is inverse complementary matrix of A, as A and D are disjoint and A plus D is invertible. Now just find out A plus D inverse and AD minus. So set of all 1, 3 inverses and 1, 2, 3 inverses are given by this expression. So that's how we get all this. Similarly, just following the procedure, we can find out set of all 1, 4 and 1, 2, 4 inverses. So to find more Penrose inverse, first to obtain D is equal to F1 transpose E2 transpose. Observe that D is inverse complementary matrix of P, as AD are disjoint and A plus D is invertible. The reason is same as discussed earlier. Just obtain A plus D inverse, and then more Penrose inverse of A is given by this expression. Similarly, one may find group inverse, set of all 1, 5 inverses, and co-repeat generalized inverse, and also star co-repeat generalized inverse. These are the references. Thank you.
Okay, fine. Okay.
Yes, sir. Yes.
Any question? Anybody wants to ask something? Is there any question from the audio, from the participants? Okay, if there is no question, we'll thank the speaker. Okay, so we'll thank and we'll move on to next speaker. Okay. So next speaker is Patricia Antunes, University of Beira Interior from Portugal. She will be talking on Edgeworth expansions in additive models. Okay, welcome, Patricia. Welcome, Patricia. Yeah, please go ahead.
Hello, my name is Patrícia Antunes from University of Beira Interior, Portugal. The other authors in this work are the Professor Dr. Sandra Ferreira, Professor Dr. Dário Ferreira, and Professor Dr. João Mexia. Today I'm here to talk about expansions in additive models. In this outline, represented by these points: objectives, introductions, pre-results, conclusions, and some reference. In this work, we consider additive models, and your main goal is to show the power of independence in defined general models in the good statistical behavior. We intend to present the use of cumulants in the adjustment of models. We show how to use edge expansions to obtain confidence ellipsoid for the observations vector and predictions interval for the future observation. For this, we want to estimate the parameters of a model by giving this way, where x0 beta 0 is the fixed effects and xi zi is the random effects. Vectors corresponding to a random effects are part of the model are given by this, independent with this independent identically distributed components with cumulants up to first order. That we assume that these have the moments until the first order. The Zi vectors have cumulants of the order R given by this, where the R is equal to 2, 3, and 4. The expected value of Zi is new. The moments are used to describe universality or multivariate distributions, and there is a relationship between them and the cumulants. If a distribution is determined by its moments, they are also determined by their cumulants. In these sections, we start with the definitions of moment generation functions. Given a random value u, the moment generation function is given by this, where this is indicates expected values. This function is defined for values of t, with this is finite. So the cumulant generation functions are given by the log of the moment generation functions of the random value u, and the Hertz moment relative to R and cumulants are given by this, where this indicates the order derivative. With the mean value variance and the Hertz center moment of u, we have these results. The first cumulant is mean value, the second variance, the third cumulant is equal to third central moment, but you can see in the fourth cumulant are not equal to a central moment. The fact that we have this will be arranged to work with a pairs of independent and identical distributions models. We consider a pair of observation vectors, this, which model of the pair will give and be as estimator of the variance. As this estimator will be independent, this product will be an Bayes estimator of the square of variance. To obtain the Hertz cumulant, the value u, obtain these equations. Let's now consider a particular case where we, unlike the previous case, will not need a pair of models. This is because we will show that if we have a pair of parameters, we'll be able to estimate the cumulants and order to the central moments. Using the derivatives of order R, a product of functions given by this, where the derivative of the R plus 1 moment is obtained this way, and the R plus 1 order cumulants given by these expressions. Consider this expected value. We have these expressions for Hertz central moment of variable u. So we see that the cumulants with the central moments and moment relatives to orange are mutually determined. We now admit these dense allocations and dispersions parameters for distributions U. In this case, we will show that we don't need a pair of models. Thus, we admit the random variable U follows the distributions dispersion 0, location 0, dispersions 1, given by this. And you obtain the moment generation functions by these parameters given by this, and the cumulant generation functions by these parameters given by this. So we get these expressions for obtain the Hertz cumulant and the dispersions parameters given by this. If the Hertz cumulant, the location 0 and dispersions 1 are assumed to be null, there is no need for a pair of models to estimate the fourth order cumulant. Since 1 second cumulant these parameters is estimated and consequently the cumulatives any order. For false approximations for the distributions, we resort to Edwards expansions. If the U random value has moments, mean value, variance, third central moments, and fourth central moments, we have the skewness and kurtosis conflicts given by these. We have the Edwards expansions given by this equal. This expansion gives approximations, these distributions. In these sections, adjustments will get a least square estimators of the cumulants the order 2, 3, and 4 of component Zi. We have seen that estimator for the fourth cumulant, we need a pair of observations vector independent and identically distributed. And these metrics be the same for this pair of vector. We assume that matrix S is this, and there's the orthogonal complement of this. With this, the range of space of matrix X will by these dimensions. Consider this vector an orthogonal base of orthogonal complement. We have this random part of vectors for the orthogonal complements equal the combinations of these and these, where these vectors have these components and consider by this way, with endpoint equal n minus q. The Hertz cumulant of the rainbow part of vectors for the orthogonal complement is given by this, and these linear combinations obtained by this. We consider independent distributions vectors by these components. So we obtain the estimator the order 2 and 3 by this, and the order 4 by this. Now let's go a study of confidence ellipsoids. For that, take a vector U of normal 1. We can analyze the problems, and for that we write the inner product follows this way. The inner product is the linear combinations by this and this vector represented by these components, and this vector represented by mean of this pair of the vectors. We have the mean of the linear product is 0. It's because the mean of Zi is 0, just as the linear product is the linear combinations of Zi and your mean is 0. In this equal to a null vector of components Ci. Consider the last expressions. We have the Hertz central moment of the inner product like these equations, and this combination linear represented by this. Consider the last equations. We'll have these estimators for Hertz cumulant, skewness confidence, and kurtosis confidence. Take for approximate distributions of inner product. We have these expressions. for the estimator of second or cumulant obtained by this, we have these expressions for these approximations by the winner product. By this, we use the estimators of cumulants, the order 2, 3, and 4, as well the estimator of skewness and kurtosis. So we get the peak quantile estimate by this of the address expansions given by these equations for inner product. We will now obtain the implicit center on the order social with the quadratic form this, given the vectors minimized by this equal. You can see in picture present the ellipsoids that pass through the center in the direction given by the vector u at distance by this for the center. So you get a new weight adjustment collapse ellipsoids and that adjustments. We use address expressions. In predictions interval, these intervals are construed for a set of values of control values correspond to columns for this matrix. Given this vector, you can get this, and the estimator of skewness and estimator of kurtosis confidence, we get the address expansions for these distributions. In the last equations, we get this and this in the order to construct the 1 minus p intervals, predictions intervals given by this, where this is just approximate value of the probability contained the future observations. Now you referred some conclusions. In these presentations, only assume inadditive or two independence of the vectors of the random effects with components that have moments until the order 4. It was shown that in order to obtain the components the order 4 is necessary to work with independent identically distribution pairs of observations vectors. The constructions of confidence ellipsoid based on the use the expansions of these distributions, and from the empirical quantiles of these distributions we get the predictions intervals. You can see some reference, and thank you for your attentions.
Okay, thank you. Thank you. Thank you very much. Any participant who wants to ask some question here? Any participant who wants to ask some question here? Okay, fine. Okay, we'll pass on to next speaker. Okay, so, next speaker is Rajaya Dasari, AITS Varangal. He'll be talking on triangular and symmetric splitting method for the steady state vector of regularized linear system, block, circulant, stochastic matrices. So I welcome Mr. Rajaya to present to proceed give his talk. Okay. Yeah, welcome, Mr. Rajaya. Yeah, please proceed.
Morning to all. Myself, Dr. Rajaya Dasari. I am working as Assistant Professor in the Department of Mathematics, KITS Varangal, Telangana. First of all, I thank to the organizers for giving the opportunity to present my research paper in the said conference. Today, I will present a talk on the triangular and symmetric splitting method for the steady state vector of a regularized linear system, block, circle, and stochastic matrices. The schema triangular and symmetric splitting method developed during my research work under the guidance of Professor Pimala Reddy. So that is at the time of my PhD work, I developed this schema. So with my professor, now I can extend this schema to the black circle and stochastic matrices. Next, we can classify the well condition and ill condition of that particular pertinent linear system using the condition number. The flow of my presentation is motivation to my research problem, so some introduction, the problem undertaken, that is the particular schema, next numerical results, conclusions, references. Nowadays, every physical system, it can be converted into the mathematical problem, particularly in engineering science, confined to the internet traffic. So nowadays, the internet traffic is very busty in nature. It is the major challenge to the traffic engineers to develop and manage that particular traffic. So internet traffic that can be modeled as the system using the matrix geometric solutions. We can find out the state probability vector and steady state vector. So once we can find out the steady state vector and state probability vector of that particular linear system, then we can find out the performance measures, packet loss probability and mean waiting time. So based on the performance measures, we can conclude the remarks and give the suggestions to the traffic engineers to develop that particular system. And we can also conclude that the stability criteria of that particular linear system. So here we can consider any particular physical problem, it can be converted into the linear system. Now our aim is to find out the solution of that particular physical system. So already there exist the several direct and iterative methods to find out the steady state vector of that particular pertinent system. In most of the cases, the network nodes are modeled as the queuing system. Now the problem of finding the performance measures is reduced to that of steady state vector or state probability vector of that particular linear system. So therefore it is the key importance to investigate that particular linear system. So already Hermitian, skew Hermitian and positive definite skew symmetric methods are developed for the complex matrices, and triangular and symmetric splitting method is developed and discussed for solving the positive definite linear system of stochastic matrices. Triangular and symmetric splitting method is developed by our team with my professor Vimala Reddy sir. Now we can extend that particular method to the black circle matrices. So here we can consider the stochastic rate matrix, that is stochastic matrix Q. So here we can consider the Q. So Q is called as a matrix, and Q1, Q2, so on, Qn, that is, it is like a cycle. So Q1, Q2, so on, Qn, Q1, Q2, so on, Qn minus 1. So it is a repeated cycle. So therefore this matrix is called as the circular matrix. But here each Q1, Q2, so on, Qn are the matrices. Again, the matrices are circular matrices of order n by n. So that is the sum of each row and each column of each matrix, or the total matrix, is 0. Therefore, this matrix is said to be the doubly stochastic matrix. Now our aim is to find out the steady state vector pi of the pertinent linear system, pi into q is equal to 0, where pi is the steady state vector which satisfies the condition pi into e is equal to 1. So that is this system that can be possess the either 0 solution or infinitely many number of solutions. In some cases maybe no solution, but we are interested to find out the unique solution. For that we can use some pertinent linear system. So that is nothing but we can use the sum attribution, and it can be converted into that is the homogeneous system, which can be converted into a non-homogeneous system. So before that, first of all, we can define some basic definitions. That is, any matrix is of the form Si into B where S is greater than or equal to spectral radius of the matrix B, then that particular matrix is said to be the M matrix. If S is greater than spectral radius of B, then the matrix is called as the non-singular matrix or positive definite matrix. So again we can define the definition of the M matrix, that is a non-symmetric matrix A is a matrix if its symmetric matrix is symmetric part is a matrix. Similarly, we can define the positive definite, that is if the symmetric part is positive definite, then that particular matrix is said to be the positive definite matrix. Now our aim is to estimate, that is evaluate the steady state vector. For that we can define some lemma. So here also we can consider Q is the any black n by n matrix. So we proved that, already we proved that this matrix is called the M matrix. Now our aim is to find out the solution using the modified and symmetric splitting method on the block circulant matrix. For that we can convert the given linear system into, that is the homogeneous linear system into non-homogeneous system by introducing the small perturbation, that is epsilon. So that is based on the epsilon, the system that is either ill-posed or well-posed. So that can be defined at the time of the numerical results using the condition number. So now we can consider some theorems which can be used to define the convergence criteria of that schema, that is triangular and schematic splitting method. So this theorem, this can play an important role in convergence criteria of that particular system. That is, we are always looking for finding the steady state vector, find which is the unique. So that's why we can consider this particular theorem. That is, for any non-symmetric stochastic rate matrix, there exists a constant epsilon greater than 0 such that A is equal to Q transpose plus epsilon into In is the positive definite if all its real eigenvalues are non-negative. That is, if the matrix is the positive definite, then only we can conclude that iterative process that can be converges. So that is, we can define with the help of the spectral radius of the matrix. So we will define later. So here we can consider our schema, that is, you can define the matrix here, that is, it can be converted a linear system to the non-linear system, and the schema that can be defined as A is equal to diagonal lower triangular and upper triangular matrix, and it can be converted into the triangular and symmetric method as follows. That is, A is equal to, the first part is the triangular matrix and the second part is the symmetric matrix. Here also first part is the triangular matrix, second part is called as the symmetric matrix. Now we can use the schema, that is the iterative schema, as we can consider the initial guess x0 and we can apply this particular schema for finding the steady state vector of the given matrix. So now our aim is to find out the unique solution of that particular system. For that we can consider the schema is that schema that can be possessed, the schema that can be possessed the unique solution based on the following lemmas. That is nothing but with the help of these lemmas and theorems we can conclude that particular system that can be possessed the unique solution. So for that here we can consider lemma 3 and lemma 4 and lemma 5. So lemma 6, from the lemma 6 we can conclude that, from the theorem 6 we can conclude that this particular regularized linear system that can be possess the unique solution. Then if the spectral radius of the matrix is less than 1, that is, if the spectral radius of M of alpha is less than 1, then only that particular system is converges and the system that can be possess the unique solution. For illustration purpose, that is for well condition and ill condition, here we can consider a stochastic probability matrix. From this we can find out the stochastic rate matrix. So that is the stochastic rate matrix Q that can be obtained as, so Q is equal to P minus I or I minus P, and we can find out the condition number. So based on the epsilon, that is on the y-axis we can take the condition number, on the x-axis we take the epsilon. As epsilon is increases, so that is nothing but if epsilon is very small, the condition number is very high. If the condition number is very high, we can conclude that that particular system is ill-conditioned system. That is, the matrix is the ill-conditioned matrix. If epsilon is increases, that is, if epsilon is very high, then the condition number is very low. In that case, that particular system is the well-conditioned system, and the matrix is called as the well-conditioned matrix. That is, if epsilon is very high, then the system possesses the unique solution, and the solution is the solution gives the, that is the stability criteria of that particular system. That is, if the epsilon is the some suitable value, then only we can get the stability criteria of that particular system. That is, we are always looking for the stability criteria of the pertinent system. So these are the conclusions. That is, we can find out that particular unique solution of that particular system. We conclude that the method is unconditional convergent to the unique solution, and the convergence rate is rapid when compared to the existing method. We prove that the regularized matrix is positive definite under specific condition. From the numerical results, it is clear that the system is ill-conditioned if epsilon is very small. So ill-conditioned system of attribution system converted to the well-conditioned attribution system if epsilon is increases. So these are the references. Thank you.
Okay, so this is the end of the session. Okay, so anyway, the speaker is not available for answering the questions. Anyway, we will thank the organizer and especially Professor Prasad for organizing this conference. Thank you very much. Okay, for attending this. So back to the organizers. Thank you very much. Okay.
Thank you, Balaji.
Thank you, sir. Thank you.
Thank you very much, sir, for chairing this session. The next contributory session will start at 2 o'clock.
Dear all, for the next contributor session, we are looking for Raksha Pujari, Romeo Prakhal, Chandra Ferreria, Savita V, Saranya CR in the lobby. We are requesting you to be online. If we are not finding any of the participant online in the lobby, we might have to drop your presentation. Sorry for the inconvenience. ಮ್ಯಾಮ್ ಮ್ಯಾಮ್ ಸ್ವಲ್ಪ ವಿಡಿಯೋ ಆನ್ ಮಾಡ್ಬೋದಾ? ವಿಡಿಯೋ ಆನ್ ಮಾಡಿ ಮ್ಯಾಮ್. Wait, don't right now. Good afternoon, everybody. Good morning, everybody, for whoever, wherever they are. So this is next contributory talk session. I request Professor Arati Pat, Department of Mathematics, MIT, to chair the session. I request the following speakers to be online for the contributory talks. Raksha Pujari, Manipal Academy of Higher Education, Manipal, India. Romeo Prakhal, Department of Mathematics, CUSAT, Kochi, India. Sandra Ferreria, University of Beria Interior, Portugal. Savita V, Manipal Academy of Higher Education, Manipal, India. And finally, Saranya CR, Bharatiyar University, Coimbatore, India. The session is over to you, ma'am.
Thank you, David. We'll begin this session by the first talk by Raksha Pujari, Manipal Academy of Higher Education, Manipal. Title of the talk, Ferenc Theorem and Eigenvector Centrality.
Hello everyone, I am Raksha Pujari, research scholar working under the guidance of Dr. K. Manjunatha Prasad, Coordinator CARAMS, Mahi Manipal. My presentation topic is Eigenvector Centrality in Graph G Corona K1. These are the contents of my presentation. Throughout this presentation, we will be considering only simple graphs. Some basic definitions I have listed here. Let G be a graph with vertices V1, V2, so on up to Vm. Then the adjacency matrix of G is denoted by A of G, is the n by n matrix whose ijth entry is 1 whenever Vi is adjacent to Vj and 0 otherwise. In a graph G, if A of G is the adjacency matrix and if rho is the largest eigenvalue, and if x is the corresponding unit eigenvector, then the eigenvector centrality of the vertex Vi is given by the ith coordinate of the eigenvector. Given two graphs G and H, suppose G is a graph with vertices V1, V2 up to Vm, then the corona graph, that is G corona H, is defined as the graph obtained by taking n copies of H and for each I inserting edges between the ith vertex of G and each vertex of the ith copy of H. A real square matrix A of order n is said to be reducible if there is a permutation P of the entries such that A can be represented as P block matrix given here P transpose, where B and D are the square matrices. Otherwise, A is said to be irreducible. Let me now state a very famous Perron-Frobenius theorem. If A is a non-negative matrix, which is an irreducible matrix, and if rho of A is its spectral radius, then the following properties holds. That is, rho of A is always positive and rho of A is an eigenvalue of A with multiplicity 1. The left and the right eigenvectors associated to rho of A are positive. For any other eigenvalue lambda of A, mod lambda will be less than or equal to rho of A. Also, related to the eigenvalues of the graph and the corona graph, in the literature, we can find this relation. That is, if ρ1 is the eigenvalue of graph G, and if G1 is a graph obtained by taking G corona K1, that is, for every vertex of a graph G, we are adding the pendant vertex. Then the relation between the eigenvalues is given here. That is, if ρ1 is eigenvalue of G, then ρ1 plus square root of ρ1 square plus 4 by 2 and ρ1 minus square root of ρ1 square plus 4 by 2 will be eigenvalues of G1. And therefore, if we have k eigenvalues for A of G, then there will be 2k eigenvalues for G corona K1. Similarly, the relation between the corresponding eigenvectors can be seen here. That is, if x1 is an eigenvector corresponding to the eigenvalue ρ1, then x1, x1 divided by ρ1 plus square root of ρ1 square plus 4 by 2 will be the eigenvector corresponding to the eigenvalue ρ1 plus square root of ρ1 square plus 4 by 2. Now, if we consider a graph with adjacency matrix G, and if rho is a spectral radius of A, and if X is the corresponding unit eigenvector, then the eigenvector centrality of Vi will be equal to Xi. Now, if I take G corona K1, that means we are adding the pendant vertices. So I have named them as U1, U2 up to UM. Suppose A1 is the adjacency matrix of G1, and if ρ1 is the spectral radius of this adjacency matrix A1, and if this is the unit eigenvector corresponding to ρ1, then eigenvector centrality of the vertices of G corona K1 can be seen here. That is, eigenvector centrality of Vi in the graph G1 will be equal to Yi, and eigenvector centrality for Uj will be equal to Yj dash. But in the previous slide, we have certain relationship between the spectral radius of, that is, eigenvalue of a graph and corona graph. So by looking at that, we can make that is, the spectral radius of the corona graph will look like rho plus square root of rho square plus 4 by 2. And therefore, by this, we can say that the unit eigenvector, that is the corresponding eigenvector, will be of the form x, which is nothing but the eigenvector corresponding to the spectral radius rho, x divided by rho plus square root of rho square plus 4 by 2. And therefore, observe here is eigenvector centrality of Vi in G1 is Yi, which is nothing but Xi, which is nothing but eigenvector centrality of Vi in the graph G. Also, from the Perron-Frobenius theorem, the spectral radius ρ1 will be greater than 0, and the corresponding eigenvector will be greater than 0. I'm sorry, this is the eigenvector corresponding to rho is also greater than 0. Now here I can apply Perron's-Frobenius theorem. Why? Because the adjacency matrix is non-negative and also it is an irreducible matrix. Further, we can also note that the rho1 will be greater than 1 and therefore the vertex with the highest eigenvector centrality in G will also be the vertex with highest eigenvector centrality in G1. That the references. Thank you.
Any questions from audience? So if no question, we thank Raksha for the nice presentation.
Thank you, ma'am.
Gyan Shekhar, have any doubts or any questions?
There is no doubt, ma'am. Just now I have seen that screen. Now only the screen is visible. That's why I raised the hand.
Okay, okay, sir. So next talk is by Sandra Ferreira, University of Beira Interior, Portugal. Title of the talk, On Confidence Intervals for Additive Model.
My work is entitled On Confidence Intervals for Additive Models. It's a joint work with Professor Dário Ferreira, Patrícia Antunes, and João Tiago Mexia. This outline of my work, I start with normality, then with cross-nesting, and then with an application. In this talk, we are focused on models with orthogonal block structure, that we call TOPS, that were introduced by Nelder in 1965 and Altman and Speed in 1983, and continue to play an important part in the theory of randomized block designs, constituting an ideal technique for estimating variance components in mixed linear models. We also have to refer to the innovative work made in this area by Kawinski and Kakayama and Mestre. We will present mixed models where the additivity of the model equation and the covariance matrix is considered. As this way, we could distinguish our additive models from other types of models that do not have this structure, but which are also designated as additive models, see for example Oder, Stuzelt, and Young. In the literature, there is little supporting theory for confidence intervals obtaining in this type of models. His work aims to improve this situation by proving an application supporting the methods employed. Next, we move to models with orthogonal block structure, OBS, that have covariance matrices given by this linear combination, where the matrices Q1, Qm are pairwise orthogonal projection matrices since V is positive semi-definite. We consider mixed models given by Y with beta 0 fixed and U1, UW independent with no mean vectors and variance covariance matrices given by this linear combination. If these matrices commute according to Fonseca et al. 2006 and 2007, they will be linear combinations given by this form. So we have this equality of these matrices and the model as OBS. In what follows, we will consider normal models with OBS that we called NOBS. For these models, we have, besides the canonical variance components, gamma 1, gamma n, the ones that usually appear in the distribution of the U1, UW. When these are normal, Y will be normal. Thus, we have knobs models. In the study of knobs, we obtain confidence intervals and test hypotheses for the gammas and the thetas. Let the GJ rule vectors of matrices HA constitute an orthogonal basis for the range space R of matrices QJ with this form and this identity matrix given by this AJ transpose, and Y as mean vector Yj with Yj that follow this normal distribution. Pj is the orthogonal projection matrix on the ranged space of matrices Xj, and the rank of Pj is equal to Pj small. So we have the sum of squares given by this expression, and the estimator of gamma j will be best quadratic ambiasing estimator in the class of the estimators derived from Yj. This estimator is given by this quotient. So we have the independent samples constituted by the UJL, and according to the reverse Glivenko-Cantelli theorem, we have the Q empirical quantiles of these samples that converge almost surely to the exact quantiles ZJQ given by this quotient. So we have the approximate 1 minus Q level confidence intervals for the gamma j given by this, which may be used to test through duality the hypothesis H0 against H1. Now let's move for section 2, cross-nesting. Let's consider L groups, K1, KL random effects factors with balanced nesting that cross, VL fixed effects, AH is the levels, CL, the HL is this product, and BL is the quotient. Now we have here the gamma R, the random sets, and gamma F, the fixed effects part of the model. Let now the set star HL, where we have WL, the number of components of KL that exceed the corresponding components of HL, and we consider the estimator of sigma square given by this difference, and we have the positive part and the negative part. So let's move to section 3, to a numerical application. This analysis refers to the results of an experiment with grapevines. In it, we had 3 factors: location with 3 levels and origin of the plants with 2 levels. For each origin, we had 3 clones. So we had 18 treatments, for each of which we had 5 replications. We assume that the factors location and origin have fixed effects, while given the great number of clones available, the third factor had random effects. We thus had a cross-nested mixed design with 2 groups of 1 and 2 factors respectively, the location, origin, and clones. Using the discussion presented, we see that the model has OBS. This experiment is described in Fonseca et al. 2003, and the analysis of these models was considered in Fonseca et al. 2006. We have here the levels. We have R equal to 5 replications, and these sets represents with F the fixed effects part of the model, and R the random effects part of the model. Since factors that nest do not interact, we had the variance component sigma square O2 for the third factor clones, sigma square 1, 2 for the interaction between the first factor, location, and third factor, and sigma square for the errors. The positive and negative parts of the estimators for these variance components were given by this expression, where we had the sums of squares for the third factor, S3, for the interaction between first and third factor, S1, 3, and for the error, S. The samples were constituted by the Zi plus for O and 2, and Zi minus for the negative part, and respectively for the interaction, we have the positive part and the negative part of the samples. So, using the math software Maple 12, we generate set GU with components that follow this chi-square with these degrees of freedom, and derived from those samples the components Zi plus for O2 variance components and 1, 2, the third factor variance components, where Zi1 are given by the quotient of SU divided by GIU. The histograms corresponding to the probability of the probability measures induced by these samples are presented in next graphs, respectively, as well as the corresponding MVU, which is represented by a black dot with coordinates given by this. We can see the location of the MVU of the third factor for the interaction, and we have the conclusions. In this application of cross-nesting random effects factor, we conducted an analysis of an experiment with grapevines to evaluate the performance of our new implementation. The histograms with the empirical joint densities induced for both parts, positive and negative, represented in previous graphs, show the nearness of the estimators and the modes, which is remarkable, validating the numerical results. There is some references of a list of a lot of references. Thank you for the wonderful opportunity and for your time.
Any questions from audience? Yeah, you can raise the hand if you have any question. Okay, so we thank Sandra for the nice presentation. The next talk is by Savita V, Manipal Academy of Higher Education, Manipal. Topic of the talk on generalized core nilpotent decomposition.
Good evening, everybody. My name is Savita V, Research Scholar, Department of Data Science, PSPH Mahe, Manipal. My title is on generalized core nilpotent decomposition. These are the contents of my presentation. These are the few notations which I use in my presentation. First, introduction. Given an m by n matrix E over a complex field, consider an n by m matrix G satisfying these four conditions. Whenever the matrix A is a square, the following matrix equations are considered in addition to the above conditions 1 to 4. Then the matrix G satisfying the condition 1 is called generalized inverse of A, denoted by A minus. Satisfying condition 2 is called outer inverse of A, denoted by A equal to. Satisfying conditions 1 and 2 is called reflexive generalized inverse of A, denoted by AR minus. Satisfying conditions 1 to 4 is called the Moore-Penrose inverse of A, and it is denoted by A plus. Satisfying conditions 1, 2 and 5 is called group inverse of A, denoted by A hash. Satisfying conditions 2, 5 and 1 power k is called Racine inverse of A, denoted by A. Before continuing, I will define the few terms. The index of A is the smallest integer k for which rank of A power k plus 1 equal to rank of A power k. And a matrix A belongs to Cn by n is said to be a core matrix if index of A equal to 1. A matrix A is said to be nilpotent if A power k equal to 0 for some integer k. A matrix A belongs to Cn by n is said to be EP if column space of A and column space of A star are equal. A square matrix P is called projection matrix if it is its square, and a square matrix P is called orthogonal projection matrix if P square equal to P equal to P star. We say that the matrix A is space equivalent to matrix B if their column space and row space are same. Now consider the definition of minus partial order. For matrices AB belongs to Cm by n, we say that A is below B under minus partial order. We denote using this notation. If A minus A equal to A minus B and A minus equal to B A minus for any generalized inverse A minus of A. Then for ABC belongs to Cm by n such that B equal to A plus C, the following statements are equivalent. So rank B equal to rank A plus rank C equivalent to A less than or equal to B under minus partial order. The class of generalized inverse of B is contained in class of generalized inverse of A minus and also the others. Now we go to the rank decomposition. The matrices A1 and A2 are said to be disjoint if their column space are disjoint as well as row space of disjoint. If A equal to A1 plus A2, where A1, A2 are as in the above, then rank E equal to rank A1 plus rank A2. In a decomposition, E equal to A1 plus A2 is called rank decomposition. So another decomposition is the co-nilpotent decomposition. Given a real square matrix A of size n by n, there exist a matrices Ca and Na such that A is equal to Ca plus Na satisfying the following condition. Rank of Ca square equal to rank Ca and Na power k equal to 0 for some positive integer k and Ca Na equal to Na Ca equal to 0. The sum A equal to Ca plus Na satisfying these conditions is called co-nilpotent decomposition of A, and such a decomposition uniquely exists. So another is a core EP decomposition that A belongs to Cn by n with index of A equal to k. Then A can be written as Ca plus Ea, where Ca is the core matrix, Ea to the power k equal to 0 and Ca star Ea equal to Ea Ca equal to 0. Okay, then the sum A equal to Ca plus Ea is called core EP decomposition. These are the some observations. Consider EP nilpotent decomposition. Let a matrix A in Cn by n with index of A equal to k, rank A equal to R and rank A power k equal to T. Then A can be written as A equal to A1 plus A2, where A1 is a EP matrix, A2 power k plus 1 equal to 0, A2 A1 equal to 0. Then the sum A equal to A1 plus A2 is called EP nilpotent decomposition, and this type of decomposition is unique and it need not be a rank decomposition. We go to the generalization of co-nilpotent decomposition. So given a matrix A such that A equal to A1 plus A2, consider the following conditions. The first condition, A1 is a core matrix. Second one, A2 power k equal to 0 for some positive integer k. Third one, A1 A2 equal to 0. Fourth one, A2 A1 equal to 0. Clearly, the A equal to A1 plus A2 is a core nilpotent decomposition if all the four conditions are satisfied, in which case A1 is nothing but Ca and A2 equal to Na. Now same way, if A equal to A1 plus A2 is said to be orthogonal co-nilpotent decomposition if A1 A2 satisfies the conditions 1, 2 and 4. In addition, A1 star A2 equal to 0. Okay. The decomposition is called OCN because column space of A1 perpendicular to column space of A2, which is same as core EP decomposition. Consider before. And A1 plus A2 is said to be EP nilpotent decomposition if A1 is an EP and A2 is nilpotent decomposition. But what we defined here is different from one introduced by Wang and Leo by relaxing the condition A2 A1 equal to 0. Now this lemma is useful in our further discussion. Let A and B be the matrices of size m by n. Then the following holds. The first one, if column space of A and B are disjoint, then rank of A plus B equal to n minus dimension of intersection of null space of A and null space of B. And if null space of A is subspace of null space of B, then rank A plus B equal to rank A. Second one, if column space of B is contained in column space of A and row space of A and row space of B are disjoint, then rank of A plus B equal to rank A. Proving this result, if column space of A and B are disjoint and A plus Bx equal to 0 implies Ax equal to 0, Bx equal to 0, then with the help of rank nullity theorem, we can get the part 1 of the lemma. If column space of B is contained in column space of A and further A is equal to L1 R1 be the rank factorization of A, we can write B as L1 R2 for some R2. Since R1 is right invertible and given columns row space of A and B are disjoint, we get row space of R1 and R2 are disjoint. Then applying part 1 for the matrices R1 transpose and R2 transpose, we get this result. And since L1 R1 plus R2 is the rank factorization of A plus B, the part 2 follows. Consider the theorem 1. Let CA be the core part in the co-nilpotent decomposition of matrix A, D be the index of A, and A equal to A1 plus A2 be such that A1 be a core matrix, A2 is nilpotent matrix. Then the following statement hold. First one, if A2 A1 equal to 0, A1 is a matrix such that column space of A1 equal to column space of A power D equal to column space of CA. And if A1 A2 equal to 0, then A1 is a matrix such that row space of A1 equal to row space of A power D equal to row space of CA. Result, consider the first one. Given A2 A1 equal to 0, A1 is a core matrix. That would imply row space of A1 and A2 are disjoint. Now for any integer k greater than the nilpotency of A2, we can write A power k as A1 power k into A1 m A2 for some m. Since A1 is a core matrix, column space of A1 power k equal to column space of A1. Further, A2 A1 equal to 0 would imply row space of A1 power k intersection row space of A2 equal to 0. Then using part 2 of lemma 1, we get rank of A1 power k A1 m A2 equal to rank of A1. That implies column space of A1 power k A1 m A2 equal to column space of A1, and A1 power k A1 m A2 is nothing but A power k. So the result 1 follows, and part 2 is proved in the similar lines. When we go to define the two types of generalized co-nilpotent decomposition, a matrix sum equal to A1 plus A2 is said to be generalized core nilpotent decomposition of type 1 if A1 is a core matrix, A2 is a nilpotent matrix, and A2 A1 equal to 0, and the sum equal to A1 plus A2 is said to be generalized core nilpotent decomposition of type 2 if A1 is a core matrix, A2 is a nilpotent matrix, and A1 A2 equal to 0. Now, given a square real matrix A, consider the class of its GCN1 type of decomposition, and it is denoted by GCN1 of A. Okay, and note that Drazen inverse of A is space equivalent to A power D is space equivalent to CA, where D is the index of A and CA is the core part of the co-nilpotent decomposition. And further, we know that in the co-nilpotent decomposition, CA is given by A power DA, and NA equal to A minus A power DA. CA, A minus CA, that can be really simplified as equal to CA for all A minus, and using rank E equal to rank CA plus rank NA, and from the properties of minus partial order, it is clear that CA less than or equal to A in the minus partial order. Now, in the process of characterizing GC1 of A, we shall consider the following class of matrix decompositions given by the class C1 equal to PA plus I minus PA, where P is any arbitrary oblique projection onto column space of CA. In fact, the class of matrices P is nothing but the class of CA minus 1. Okay, when we consider the decomposition with PA equal to A1 and satisfies the conditions 1 of the theorem 1. Okay, so that will helpful in proving the theorem 2. If A is a square matrix, then the class C1 equal to the sum A1 plus A2 is in the class of GCN1 of A with A1 less than or equal to A under minus partial order. To complete the proof of this, let A1 plus A2 is taken from the class C1. Then there exists an oblique projection P onto column space of CA satisfying A1 equal to PA. Then rank of PA square equal to becomes rank of PA. Therefore, A1 equal to PA is a core matrix. If we consider further, A2 power k will come as I minus PA NA to the power k for every integer k. That implies A2 is an nilpotent matrix with nilpotency of A2 is same as that of NA. And also it is possible to verify A2 A1 equal to 0. So all this shows that A1 plus A2 belongs to the class GCN1 of A. Now to prove the another conditions there, consider the generalized inverse A minus of A and noting column space of P equal to column space of CA, which is contained in column space of A, implies A minus P is equal to P, and therefore A1 A minus A1 becomes equal to PA, which is equal to A1. So equivalently A1 less than or equal to A under minus partial order. This completes the proof of the theorem. Now in the class C1, if we consider P as CA equal to CA hash, we obtain the co-nilpotent decomposition CA plus NA. So these are the references of my presentation. Thank you. Any questions? Okay, we thank the speaker Savita V for the nice presentation. As the other two speakers, Romeo Parakal and Saranya CR, not present online, so we'll end this session. Thank you.
Thank you, ma'am, for sharing the session. As ma'am has announced, the following contributory speakers, Romeo Parakal and Saranya CR, are not available in the lobby, so we consider them as an absentees for the conferences. However, we have their recorded talks, so we will be playing them one by one for your reference. For the first one, we have a contributory talk by Romeo Parakal.
Warm greetings to all. I am Professor P.G. Romeo from Cochin University of Science and Technology, Kochi, Kerala. At the outset, let me thank the organizers for providing me an opportunity to do a talk here. And in this talk, I am going to describe linear sandwich semigroups, and I will go to the presentation and I will briefly introduce the topic. And obviously all proofs are avoided, and only I share some ideas. the aim of my talk is to describe the Green's relations on a semigroup, which are very much important in the study of the structure of semigroups and its generalization, known as the generalized Green's relations. Then I recall the definition of an abundant semigroup and discuss some of its properties. When I describe a linear sandwich semigroup of all m by n rectangular matrices with the fixed n by n matrices. This is a class of rectangular matrices, as it is obvious that to rectangular matrix you cannot define a multiplication. Therefore, to make a multiplication possible, we fix an n by m matrix in between, and you take B and C are two matrices in rectangular matrix in m by n matrices. In between I fix an n by n matrix so that the multiplication is possible, and with respect to that multiplication, obviously it is a semigroup. So that is a linear sandwich semigroup. And to show that the set of all the rectangular matrices is a subsemigroup of the regular semigroup of square matrices. Now I go through the basic definitions. Recall the basic definitions of semigroups, Green's relation, etc. As a semigroup is a non-empty set together with an associative binary operation. All very general mathematical structure, just like any natural numbers. Obviously, all groups are semigroups, and semigroup is obviously more general than groups. And in a semigroup, I define an ideal. A semigroup as A is an element in a semigroup as, then SA union A is called the principal left ideal generated by A and is denoted as A. And we are going to define certain relations. First of all, an L relation. Two elements A and B are said to be L related if they generate the same principal left ideal. Similarly, if they generate the same principal right ideal, it is called a R relation. And intersection of L and R is denoted by H. They are joined by D, and the two-sided analog of L and R. That means if two elements generate the same two-sided ideal, then they are related. These relations are called Green's relations, and they are of paramount importance in the study of structure of structure of semigroups. Now, some more definitions. An element A in a semigroup is idempotent if A square equal to A, which is EI square. And the set of all idempotents of an element of a semigroup is denoted by E of S. Semigroup S is regular if for every element there exists an X such that X A equal to A. So this is what is generally known as von Neumann regularity. Not that a regular semigroup. So it is easy to see that in a regular semigroup, all L classes and R classes contain idempotents. So these relations characterizes the regularity of a semigroup. Now I generalize these relations and define what is called a generalized Green's relation. And they are usually denoted as L star, R star, D star, H star, etc. Okay. So to the generalized Green's relation L star or R star on a semigroup S is defined as if they are L or are related in some semigroup over semigroup, that means some semigroup of S bar containing S. Such a relation. So it's in some sense it is a generalization of the Green's relation. They are usually called the generalized Green's relations, and the semigroup is called abundant if every L star class and R star class contains idempotents. Now this is a characterization of R star relation. Element wise, A B belongs to S. A is R star related to B. if for all xy belongs to this one, xa equal to ya if and only if xb equal to yb. Similarly, we can define L star relation as ax equal to ay if and only if bx equal to by, like that. This condition is simplified, further simplified. One of the elements is an idempotent. That means A is R star related to E, where E is an idempotent, is equivalent to saying that EA equal to A, and for all XY belongs to XY, XA equal to YA implies XE equal to YE. Now I recall some more definition as a variant of a semigroup and the sandwich operation. So a semigroup is SB a semigroup. A is an element of S. Associative sandwich operation star A can be defined on AS by X star A Y equal to X A Y. So it will be so easy to verify this is associative operation, and this is star A. This star operation, which operation is called the sandwich operation. A star A is called the variant of S with respect to A and is denoted by SA. And example is the Rees matrix semigroup. Rees matrix semigroup, where S is a semigroup, I and lambda are indexing sets, and P is a sandwich matrix. Then I define the set Mi lambda, I S lambda, and two such elements are A I lambda, B J mu is A P lambda, J P I B. So your that is a well-known semigroup. Rees matrix semigroup is an example of a completely zero symbol semigroup, and one can look any book on semigroup theory to find the description of Rees matrix semigroup. There, that multiplication is an example of a sandwich operation, and this is the first natural example of a sandwich operation, and thus the Rees matrix semigroup is a matrix semigroup together with the sandwich operation. Now, I am going to the main content of the talk, the linear sandwich semigroup. So here, you take M by N rectangular matrices, and A is a fixed N by M matrix. Consider M and A with a set of all rectangular matrices with a sandwich operation star A. That means X star A Y means X A Y. So with this sandwich operation, that becomes a semigroup. And if M equal to N, obviously you have you get the semigroup of square matrices, and I is a variant of the full monoid of Mn, and this is regarding linear sandwich semigroup hold for this variance as well. Now some properties of this linear sandwich semigroups. A B belongs to Mn, and rank of A equal to rank of B, then this sandwich semigroups are isomorphic. And it is easy to, if a matrix Mn A is of rank R, we can use J as this one. That means you can get an matrix of identity matrix of order R together with some other zero matrices that will do, and it can be easily verified that this multiplication is so. Therefore, I define three important subclasses: P1, P2, P3, and P. That class determines the Green's relations on these linear sandwich semigroups. So P1, J is the sandwich matrix. P1 stands for this Xj R related to X. P2 stands for Jx R related to X, and P3 stands for Jxj some Green's relation J related to X, and P1 intersection P2 is P. And the following proposition gives the connection between these sets P1, P2, P3, P, and the rank of these, and the relation Green's relations. That means X is Rj stands for any Green's relation. X is Rj related to Y, if X equal to Y or this condition. Similarly, for other Green's relations, since M is you have the A class means any Green's relation, R class, L class, J class, or D class, Aj of class X in set of all M by N matrices respectively. This is the situation. Recall that D class Mn are sets. Mn is equal to set of all x belongs to rank of x equal to yes. This is the proposition. Xy are rectangle linear sandwich semigroup, matrix semigroup. Then, and only if the following conditions are true. And this is the connection between these sets P and D relations. In if A and B are two elements in the sandwich semigroup, then M and A is isomorphic to M and B if and only if rank of A equal to rank of B. But you note that if rank of A equal to rank of A, if rank of A equal to rank of B, then it is possible to have this Rees matrix, the sandwich semigroups. Sandwich semigroup is isomorphic. Even if this Mn not equal to K. Generally, this Mn need not be equal to K. This condition may satisfy. So the further thing is, the questions you for discussion is the structure of the linear sandwich matrix Mn(J). Is it an abundant semigroup? Obviously, this Mn(J) is contained. M is less than n, so this Mn(J) is contained in M, the square matrix Mn, square matrices. But for the linear sandwich matrices, you choose a particular A and you make the partial multiplication of matrices as a binary operation using this J. Therefore, it is interesting to look at how this Mn(J) is an abundant semigroup. And the next thing is the inverses, generalized inverse, Gaussian inverse along element and element A of the semigroup Mn(J). These inverses are useful in finding the solutions of the system of equation Ax equal to B, where A is an M by N matrix. So, the aim of this talk is just to introduce the rectangular matrices, M by N matrices, along with the sandwich operation, so that becomes a semigroup. And how we can embed that semigroup as a abundant semigroup. Okay, thank you for the listening. Once again, I thank the organizers.
I request Professor Vipin N, Assistant Professor, Department of Data Science, Mahe Manipal, to chair this session. Since our first speaker...
Okay, thank you, organizers.
Yes, sir, you are audible.
Yes.
Since our first speaker,
okay,
Navi, is not available, we will go ahead with the second speaker, Nitiraj Shetty.
Okay, yeah, thank you. So, congratulations the entire CARMS teams and Professor Manjunath Prasad sir for conducting this international conference in a very smooth and very beautiful manner. First of all, I would like to express my sincere thanks to Professor Manjunath sir for giving me the opportunity to chair this session. So as mentioned, we have 5 speakers today, and the first speaker is not present yet, and so we will start from the second speaker. The speaker is Dr. Nitiraj Shetty from the Sardar Patel University, Gujarat, and he will be delivering the talk on the topic, a frailty model approach to the design of experiment. I hope you are present. Dr. Nitiraj Shetty, over to you, sir.
Hello, everyone. I'm glad to have an opportunity to present my research work in this conference. I'm presenting frailty model approach to the design of experiments. Theory of frailty model was mainly developed in the field of server analysis. The main aim of presentation is to explore the application of frailty model in the design of experiment. In this presentation, we discuss the approach of frailty model to the completely randomized design. So this is published paper in Journal of Pure and Applied Sciences, December 2018. We have come across many cases where visual analysis of variance of data from completely randomized design fails to detect the difference in the treatment effects, which are apparent in the values or means of observation under the different treatments. This may be due to the heterogeneity in variance, may be due to the some unexplained part of variation present in the data. The purpose of this research is to identify the cause of extra variation with the help of priority variable Z incorporated in the variance of the error distribution and reducing the unexplained part of variation. The purpose and significance of the study is to provide a new ANOVA technique to resolve the problem of extraneous variation. To circumvent this difficulty, we propose a new error model in which the common variance is divided by the random variable Z, generally known as priority random variable, and for the conditional distribution of error given Z as we assume it is normal. Under this assumption, we develop the entire theory of ANOVA for completely randomized design. So this is literature review. In survival analysis, the problem of heterogeneity is dealt by incorporating priority random variable Z. The first univariate model, priority model, was suggested by the Beard in 1959. The same model was independently suggested by the Wappel and Lancaster in 1979. We observed that same concept can be incorporated in other statistical studies suitable to solve some seemingly mysterious problems. In this research paper, we provide an example where the treatment effects are apparently different, but regular analysis of the difference to detect it. So this is what the description of the example. A fast food franchisee is test marketing the 3 new menu items to find out if they are same popularity. 18 franchisee restaurants are randomly chosen for participation in study. In accordance with the completely randomized design, 6 restaurants are randomly chosen to test the market for each item. The following table represents the sales figures in ₹1,000 of 3 new menu items in the 18 restaurants after a week of test marketing. This is what the sale, this is what the average sale was recorded for the menu item 1, menu item 2, and menu item 3. Can we say that at 5% level of significance, sale volume for the 3 new menu items are same? To answer the above question, we need to carry out the ANOVA, provided the following assumptions must be valid: homogeneity of variance and error must be normally distributed. So homogeneity can be checked by using the Bartlett test, and we accept the null hypothesis of equality of variance by watching the p-value. Again, to check the normality, again we are accepting the null hypothesis that the data follows the normal distribution by watching the p-value. Again, the test for the equality of average sales. So we run the ANOVA and we can see that there is no significant difference between the mean sales volume for the new menu items. Again, here also we can see that the error sum of squares are greater than that the error sum of square due to the items. So in this example, we observe that the error sum of square contains the some other unexplained part of variation along with the random error, which cause not to detect the larger difference present in the means of the observation for the 3 items. This needs to be extracted so that the signal can be rightly detected. So traditionally, we are assuming the CRD model as the linear model, assuming the various effect to be additive becomes y is equal to mu plus alpha I plus epsilon I. Y is a yield or response, mu is a general mean effect, and alpha is the effect due to the ID treatment, and epsilon I is the effect due to the error effect due to the chance. we assume that the various effects are additive in nature. Epsilon ij are IID normal 0 sigma square. Incorporating the Friday random variable, we assume that the epsilon given Zij follows the normal with 0 upon 0 sigma square upon Zij with variance sigma square upon Zij. Consequently, Pij given Zij follows the normal with mean mu plus alpha and variance sigma square upon Zij with the density function is this one, where I is running from 1 to V and J is running from 1 to Ri. We further assume that the distribution of Zij is a standard exponential distribution. Therefore, the joint distribution of Yij and Zij is this one. After integrating the above joint distribution with respect to the Zij, we get the marginal density of Yij as this one. Using the joint density and marginal densities, we are able to find out the expected value of Zij given Yij is this one. It can be easily seen that the double expectation of Zij given Yij is equal to 1. This is what the maximum likelihood estimates for the model parameters alpha mu and sigma square. Again, algorithm to compute the expected value of Zij given Yij, stepwise algorithm. Enter the all values of the Yij, I running from 1 to V and J running from 1 to Ri. Initially, consider all Zij is equal to 1. Use the value of Yij and Zij to obtain the maximum likelihood estimates for the model parameter alpha, mu, and sigma. Use the given Yij and estimated values of model parameters mu, alpha, and sigma to find out expected value of Zij given Yij. Again, use the expected value of Zij given Yij and compute the maximum likelihood estimate of model parameters for given Yij. Repeat the process. Repeat the step 3 to 5 until the mean values of Zij becomes 1. Use this predicted values of Zij to construct the ANOVA table. Construction of ANOVA, epsilon given Zij follows the normal with 0 sigma square upon Zij. Epsilon ij Zij divided by sigma square is equal to follows the normal with 0 1 standard normal. Again, the epsilon square upon sigma square upon Zij follows the chi-square with 1. Sum over this one follows the chi-square with the n minus 1. Sum of squares, different sum of squares can be seen with the priority random variables are this one. Sum of square due to the error, sum of square due to the treatment, sum of square due to the total, where the grand mean is this one. This is what the grand mean. Zij summation over Yij into Zij divided by Z double dot. Z double dot is nothing but the is equal to the n. And if mean of the ith treatment is this one, wetted mean. So this is what the mean. Again, for the further algebraic computation of the ANOVA, we simplify the treatment sum of squares and total sum of square for the calculation of the ANOVA is this one. So from our example, expected value of Zij given Yij is this one. So using the sum of different sum of square formula, sum of square values, we can get the p-value is this one. So from the p-value, we reject the null hypothesis of equality of cell volume, mean cell volume. So we propose the one more example. This is what the example statement, the effective life of the test of insulating fluids of an accelerated load of 35 kV is being studied. The test data have been obtained for the 3 types of fluid. The results from the completely randomized experiment were as in the following table. Can we say effective life of the fluids for each fluid type is same? Effective life of fluids for each type of fluid is same. So from this we can see that there is no significant difference. I think so. So this is what the normality check, equality of variance check. We can see that there is a equal variances. You can see that the data considered under the study is normally distributed from this p-value. So again, p-value for the regular ANOVA approach, we can see that there is no significant difference between the mean life for the three fluids, since the p-value is greater than 0.05. By using the priority random variable approach, we can see find out the expected value of Zij given Yij at 66 iteration is this one. From the priority model approach, ANOVA construction, again we can get the same output. So we can say that there is no significant difference between the average lives of the fluid lives, effective fluid lives. So conclusion of the study, from the above study, we can conclude that if we observe a relatively large error sum of squares compared to the treatment sum of square, then we should verify whether there is apparent difference in the means of treatment effects. If yes, we suggest to use our approach and statistical ascertain the same. If not, our approach will also ascertain the same. Hence, we recommend to use our approach always to analyze CRD data. Thank you.
Okay, thank you, Nitiraj, Dr. Nitiraj Shite, for the nice presentation. Now the session is open for questions. So participants, if you have any questions, you can quickly ask the presenter regarding the query. So questions, please. Okay, just in case there is no question. So Dr. Nitiraj, I have one doubt. Are you there? Dr. Nitiraj, can you hear me? Hello.
Dr. Kiraj, please unmute yourself and if you can answer the queries of the chairperson. Vipin sir, seems like we lost him.
Okay.
We might go for the next.
Okay, so thank you, Nitiraj, for your nice presentation. Now, the next speaker is Dr. Naveen Chandra. He is from Contributory University, and he will be delivering the talk on the research topic called Modeling of Competing Risk Survival Data through the Parametric Proportional Hazards Model with a Bayesian Estimation. Over to you, Dr. Naveen Chandra.
Thank you, sir. Good morning. This is Dr. Naveen Chandra, Department of Statistics, Contributory University. The title of my talk is Modeling of Competing Risk Survival Data through Parametric Proportional Hazards Model with Bayesian Estimation. This is the outline of my lecture. This is the background. In present pandemic scenario, we humanities have faced a greater challenges of surviving in abnormal situation arises due to novel COVID-19 disease at global level from past 1 year. In fact, entire human population has made a big fighting against this disease for their survival of life around the world. A huge amount of people have been affected with COVID-19 virus at different age groups from newborn child to aged people. This term generally used to classify the illness are symptomatic, asymptomatic, mild, moderate, severe, critical. There is some situation where some of severe and critical COVID infected patients may be suffering with multiple diseases, cancer, cardiac, diabetic, etc. Such patients have less chance of recovery because multiple causes are competing along with prime corona cause for death of patients, where the primary cause of event is coronavirus, but there is some other competitive causes of event. Thus, competing risk may be appeared in for such analysis. For example, when a critical trial is conducted, then the individual are associated with various risks of death, such as in a bladder cancer clinical trial, individual can die due to bladder cancer and other causes. Instantly, it is difficult to identify the exact cause of event. Hence, competing risk analysis may play a greater role to overcome of such problem, and also help to hazard analysis with relationship between explanatory variable and time of events through Cox proportional hazard regression model. The analysis of lifetime data in presence of competing risk is based on two approaches: latent failure time and cause specific quantities. Okay, in latent failure approach, it is assumed that T1, TP, T2, T dot 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 TP be the P random variables according to P causes of failure, which is defined here TC in 1, and multivariate giant survival function is defined in equation 2. The fundamental problem of latent failure approach is that without independent assumption, the giant survival function is not identifiable from the observed data. The cause specific quantities get considerably attention in survival analysis since 1970. These quantities are useful for comparison of different treatments and observe the effect of other explanatory variables on survival population. The following two cause specific quantities get considerable attention in modeling of survival data. Cause specific hazard function is defined in 3, and cumulative incidence function is defined in 4 here. The well-known proportional hazard model can be extended in terms of cause-specific hazard function by considering the relationship given in 5. Commonly used method for analyzing competing risk survival data based on cause-specific hazard function are non-parametric and semi-parametric. Advantages of non and semi-parametric inferences are they are easy to implement and free from the assumption of underlying distribution. The key contribution based on non-parametric methods are given below: Prentice et al. 1978, Gray et al. 1988, Finn and Gray 1988, and G and Chen 2012. Okay, for detailed study non-parametric analysis competing risk, one could refer to Heller et al. And Baseman 2012. For literature review, however, parametric model are another available choice of modeling of cause-specific hazard function. If the parametric model select correctly, then they provide more robust and efficient estimates. Parameterization of cause-specific hazard function can be done by specifying some well-known distribution from form for H0 JT given in 5. Following are the some attempts based on parametric analysis of competing risk. Benchu and Gale 1990, Bryant and Dagam, Jeong and Finn, and Anjana and Sankaran, Lee. These are the work based on a parametric based. The aforementioned literature is based on parametric modeling of competing risks. The commonly used parametric survival model are exponential, viable, etc., in which only monotone shape of hazard function can be accommodated. In real life, the hazard rate cannot be monotone. That is, its shape can be bathtub-like curve. The hazard curve consists of 3 periods, which is given in this picture here: decreasing failure rate, constant failure rate, increasing failure rate. It covers all 3. So in light of this issue, we consider modified viable distribution is given in 6 as a baseline model, and the modified distribution is competent to modeling the failure data set which exhibit bathtub shape of the hazard rate. This is the picture, hazard plot of modified viable distribution. Overall survival function given in cause-specific hazard function is given in 7. Corresponding survival function and cumulative cause-specific hazard function is given in 8 and 9 respectively. The objective of the problem: parametric estimation of cause-specific hazard function using modified variable distribution. Cumulative cause-specific hazard function is estimated by using the maximum likelihood estimation and Bayesian estimation. For Bayesian estimation, a class of informative prior is considered under self and LLF. Numerical study is performed with simulation and real data sets for validation of the proposed methods. Finally, a comprehensive comparison between ML and Bayes estimators of cause-specific hazard function is given. Maximum likelihood estimation, it is given here. Maximum likelihood estimation, the expression, and the parameter estimates are obtained by solving these following identities, and but the estimates of alpha j, aj, and beta j are not turned in the explicit form. Therefore, we propose iterative method to obtain parameter estimate numerically. After obtaining this MLE of unknown parameters using the invariance property of MLE of cumulative cause-specific function is given in equation number 12. Bayes estimation. For Bayes estimation, a class of informative priors for the baseline parameter, which consists of gamma, variable, log normal distribution are given here, and standard normal prior is considered for regression parameters. So this is the posterior formulation. The posterior formulation under the assumed priors are termed in 14, 15, and 16. And due to the multiple integration, it is difficult to obtain the analytical expression of the corresponding marginal posteriors of the parameters. Therefore, MCMC method are utilized for drawing posterior samples from the AJ, alpha j, lambda j, and beta j. And the loss function, in this paper we consider two loss function. That is what symmetric loss function, asymmetric loss function, and that is what self and LLF, Linus loss function. So which is defined here. Bayes estimate is also given in 17 with the help of the self, and with the Linus loss function, the Bayes estimate is defined in 18. And this is the simulation study. We perform Monte Carlo simulation study to observe the finite sample behavior of the proposed estimates of cumulative cause-specific function. And for simplicity, we consider two causes of failure: j is equal to 1, 2, and one single covariate x from normal 0, 1. Let us the two parameter for both the causes are given here. The censoring time we considered impose percentage of censoring approximately 20%, and further computing the hyperparameter, utilize the empirical Bayes method by using the ML estimate and empirical variance. First, we generate 1000 samples of size 25, obtain the ML estimates and variance, and then compared with the mean and variance prior. Calculated hyperparameter gamma, variable, and log normal given in table 1. This is here. We consider 4 sample sizes: 20, 50, 100, and 200, and whole procedure is repeated 500 times. And this, and we consider 3 different time point: 0.5, 1, and 1.5. So this is the table where cause 1, cause 2, 3 different time point, and ML and Bayes estimates for different sample sizes are calculated here. Now it is observed that sample size and MSC have inverse relationship. Sample size increases, MSC decreasing, and for different sample sizes is observed that Bayes estimates under self are more precise in gamma prior for cause 1 and log number prior for cause 2, and for under LLF gamma prior work well for cause 1 and log number for cause 2. Okay, so real life application, we illustrated the proposed estimation procedure cause-specific hazard analysis bladder cancer tumor data, and for that we have the this is the real life application hazard part of the real data for other causes, and this is the real life. It is what we therefore compared the goodness of it model, variable, log normal, and gamma distribution, AIC, BIC. It is observed that modified variable distribution have least AIC, BIC among other counter distribution. These are the empirical and theoretical CTF comparison. These are the real life application, the ML and Bayes estimates with standard error, both the causes, and this is the conclusion. In this paper, we deal the part of behavior of cause-specific hazard function. Hence, modified variable distribution with covariate is assumed, where parameter estimates and cumulative cause-specific hazard function estimates are obtained through maximum likelihood and Bayesian estimate. For a comprehensive analysis of Bayes estimate cause-specific hazard function, we introduce a class of informative prior by choosing gamma, variable, log normal as a baseline, and non-normal informative prior for regression parameter under self and LLF. The selection of class of informative prior and two loss functions shows their applicability through simulation studies. The flexibility and appropriate convergence of the model are observed for ML and Bayes estimates. In real life applications, suitability of parameter model is assessed through the goodness of it and status check. These are the references. Thank you.
Okay, thank you, Dr. Naveen Chandra, for the nice presentation, and the session is open for the questions. So participants, if you have any questions, please ask. Okay, so Dr. Naveen Chandra, I have one doubt.
Yeah.
So the first doubt is regarding, you have said in that parametric estimation, like the first case, you have come across with a likelihood score equation which does not have the closed form expression. So you might have faced the initial value problem, right? While estimating the MLE.
Yeah.
So how did you address the problem of the initial value?
Initial value we have chosen, and we have for the range of the parameter we have just arbitrarily taken and try to fit, and it is observed that the value what we have selected that works very well. That's why that value is proposed here.
Okay. So it was not the moment estimators of the corresponding parameters.
No.
Okay. And the second question, you have given a plot in which the hazard rate is compared with the non-parametric alternative and the corresponding alternative. So how did you plot the non-parametric version of the hazard rate using any kernel density estimator, or what was the corresponding estimator for the non-parametric hazard?
We fitted through R.
No, the estimator. I'm talking about the corresponding non-parametric estimator. What was the corresponding estimator? Is it a kernel-based estimator or any other non-parametric version you have used?
B-spline method we used. B-spline method.
Okay, Professor Naveen Chandra. Thank you very much for your presentation. Have a good day. So that is about the presentation. Now I invite the next presenter, Dr. Shanmuga Priya. She is from the Central University of Tamil Nadu, and she will be delivering the talk on the topic copositive preserver by a special linear map. Over to you, madam. Hello.
Hello, sir. Sir, we are playing the
yes,
video.
Yes. Okay.
Hello everyone, my talk is on copositive preserver by a special linear map. Introduction and few notations. A matrix A is said to be a copositive matrix if it is a symmetric matrix and the corresponding quadratic form for a non-negative vector is non-negative. By a non-negative vector, we mean entry-wise non-negative. If the quadratic form is strictly greater than 0 for non-negative vector, then A is called a strictly copositive matrix. A linear transformation is called a preserver of a set. If A belongs to the set, then the image of A under the linear transformation again belongs to the set. Then it is called the preserver of the set. The notations means, the notations for copositive matrices denoted as Cn and strictly copositive matrices denoted as Sen. Symmetric matrices are denoted as Sn. N is the size of the matrix. And the set of all non-negative vectors are denoted as r power n, greater than, greater than or equal to 0. This is nothing but the positive orthant of r power n. A linear transformation is a copositive preserver if A belongs to Cn and image of A under the linear transformation L again belongs to Cn. Similarly, a linear transformation is also called as a strictly copositive preserver if the matrix is a strictly copositive matrix and the image also belongs to a strictly copositive matrix. A linear map is said to be into copositive preserver if the range of the copositive matrices is contained in copositive matrices, and it is if the range is exactly equal to the copositive matrix, it is called as onto copositive preserver. So the work so far which is done are by Susanna Fetterusia, Johnson, and Eulen Zhang. In the article Linear Preserver Co-positive matrices, they have studied about a linear map defined as SAS transpose. This is called as the standard form, and they had conjectured that any linear transformation is an onto co-positive preserver are exactly the fixed monomial congruence. Congruences are nothing but maps are of this forms, SAS transpose, and monomial meaning this S is a monomial matrix, where monomial matrix is nothing but can be written as a product of a permutation matrix and a positive diagonal matrix. Yaroslav Shito in his work Linear Mappings on preserving the co-positive cone has proved this conjecture. So we tried to find a linear map which preserves the co-positive matrices other than the standard form. So here we observe that the linear map defined as L of y is equal to ya plus ay is also a co-positive preserver, where A is a symmetric positive semi-definite matrix. So our future work is to find a linear preserver which is onto and into co-positive preservers. The following statements are equivalent for a positive semi-definite matrix. All the eigenvalues of A are non-negative, and there exists a n by n real symmetric matrix C such that A is equal to C squared. A matrix, this is our theorem. A is a symmetric positive semi-definite matrix with the lambda being the eigenvalue, and this is the only eigenvalue of A whose algebraic multiplicity is n. And L is a linear operator on symmetric matrices defined as L of y is equal to ya plus ay, and L is a co-positive preserver. So we need to say if y is a co-positive matrix, L of y is also a co-positive matrix. So it is enough to consider for x is a non-negative vector, x transpose L of y is equal to x. So before proving this, we just see the properties of a positive semi-definite matrix. A being a positive semi-definite matrix, we can write A is equal to C squared, where C is nothing but U root lambda U transpose. This happens because A is a positive semi-definite matrix and it is a symmetric matrix. Therefore, we know that by spectral theorem, A is orthogonally diagnosable. So orthogonally diagnosable meaning A can be written as U diagonal matrix U transpose. Since A is a positive semi-definite matrix, the eigenvalues of A are non-negative. Since the eigenvalue of A is only lambda, lambda is strictly greater than 0, greater or equal to 0. So we can take square root. Therefore, A can be written as U root lambda U transpose U root lambda U transpose. So this is what our C is. C is U root lambda U transpose. So now let's consider x transpose L of y x. So this by definition of L, it is nothing but x transpose ya plus ay x. And here we just substitute the way our A is written. So A is written to be this way. That is U root lambda U transpose U product U root lambda U transpose. Since U transpose U is identity matrix, this simplifies to this form. And we just write U transpose both the sides here as well as here. Since root lambda is a scalar matrix, that it is a diagonal matrix, that is a scalar matrix. So it commutes with yu. So just we commute yu root lambda. This is nothing but root lambda yu both sides. Here also we just commute root lambda u transpose y. Now again root lambda commutes with u transpose. Here also root lambda commutes with u. So the above matrices commute as root lambda is nothing but a non-negative scalar matrix, as y is a co-positive matrix and this vector. So we just need to say, since y is a co-positive matrix, we just need to say the vector u root lambda u transpose x is a non-negative vector, and this is true because root lambda commutes with u transpose. So we will get u transpose root lambda x. U transpose is nothing but identity, and root lambda x is greater than or equal to 0, as x is greater than or equal to 0, and root lambda has all diagonal entries non-negative. Therefore, L is a co-positive preserver. So next, what we have tried is L is we know L is a co-positive preserver, and we tried when does this becomes a onto co-positive preserver, and if our A, which is taken in the LA form, it is of this form. A is equal to alpha. That is, if A is a positive scalar matrix, then L will be a onto co-positive preserver. So A is of the form alpha I. So this is nothing but a positive semi-definite, symmetric, semi-definite matrix. And if alpha is strictly greater than 0, it is a positive definite matrix. And the theorem 1, it is clearly a co-positive preserver. Now we need to check whether L is a onto co-positive preserver. So by definition, A is a scalar matrix, therefore it commutes. Therefore we will get this is nothing but 2 times of YA. So we need to check whether L is an onto matrix, onto co-positive preserver. So let X is onto X is a co-positive matrix. We need to find its pre-image Y is a co-positive matrix. So our Y will be of the form half X A inverse. Since A is a positive definite matrix, A inverse is also a positive definite matrix with which is of the form beta I. Beta is strictly greater than 0. Now we need to verify whether Y is a co-positive matrix. So it is just simple calculation. X transpose YX is nothing but half times beta X transpose XX, where since X is a co-positive matrix, Y also is a co-positive matrix. Therefore, L is onto co-positive preserver. So next, this theorem was proved by Furtado and et al. It is nothing but a linear transformation on S2 to S2, which is an onto co-positive preserver. It is an onto co-positive preserver if and only if the images of the basis vectors of symmetric matrices, that is 1, 0, 0, 1, 0, 1, 1, 0, 0, 0, 0, 1, is of this form, or either of this form or of this form. In either case, alpha 1, 1 has to be strictly greater than 0, gamma 2, 2 should be strictly greater than 0, beta 1, 2 should be equal to root of alpha 1, 1, gamma 2, 2. To understand the linear transformation of co-positive matrices, it is enough to consider the linear transformation of symmetric matrices instead of working on general matrices. So let's consider the converse of the theorem. The converse of the theorem is A is a symmetric matrix and it is a positive definite matrix, and L is a linear transformation on Sn to Sn defined as of that in the theorem 1. And in the hypothesis, we assume that L is an onto co-positive preserver. Then this A has an eigenvalue lambda whose algebraic multiplicity is n. Now we have proved it for a 2 by 2 case. So any 2 by 2 matrix will be A, B, B, C, which is a symmetric. This is a co-positive matrix if and only if A is strictly greater than or equal to 0, C is greater than or equal to 0, B is greater than or equal to root of negative root of AC. And if this inequalities are strict, then it is called a strictly co-positive matrix. So we need to find the entries of A, B, B, C such that this hypothesis is true. That is, L of I is an onto co-positive preserver. And so we just need to understand the action of L on the basis vectors of the symmetric matrices. So when L acts on the basis vectors, we will get this. And since L is an onto co-positive preserver, this required image of a co-positive matrices are also co-positive matrices. Therefore, 2, 3, 4 are also co-positive matrices. Since by this theorem is an onto co-positive preserver if and only if the images are of either this form or this form with this condition. Therefore, we just imply those conditions here. So the required 2, 3, 4 equations will boils down to these conditions. Therefore, this simply means that our B has to be equal to 0. And we need to find entries A and C such that they satisfy this condition, which means that arithmetic mean is equal to geometric mean if and only if A is equal to C. Therefore, our A has to be of this form, A, 0, 0, A. This is nothing but the eigenvalue of A is small a with algebraic multiplicity 2. Therefore, this A can be written as a permutation matrix times diagonal matrix. Where permutation matrix is, let it be identity matrix. Thus, the linear transformation on S2 are defined to be this is an onto co-positive preserver, and if it is monomial congruence, this we have proved it on 2 by 2 case. We are working further on n by n case. So I thank Alex for giving me an opportunity to share my work. I thank Dr. Chandrasekharan for his constant support. Thank you.
Okay, thank you, madam. The session is open for the questions. So those who have any questions, please ask. Okay, just in case if you don't have any questions, you can contact the corresponding speaker through the mail. Okay, Ms. Shanmugapriya, thank you very much for your presentation. Have a nice day.
Thank you.
So the next presenter will be Umashankar Kelataya. He is from the Department of Data Science, Mahe Manipal, and he will be delivering the talk on the topic Core EP Inverse, a ring theoretic approach. Over to you, Umashankar.
Good afternoon, everyone. The title of my presentation is Core EP Inverse, a ring theoretic approach. This is a joint work with Manjunatha Prasad Karanta, Manipal. Points of my presentation are as follows. Introduction, followed by Core EP inverse in the context of associative rings, an expression for the Core EP inverse, and references. Introduction. Baksalary and Trinkler in the paper Core Inverse have defined the notion of core inverse for the real or complex matrices of index 1 and studied their interesting properties. The definition of core inverse is as follows. Let A be an n by n real or complex matrix, an n by n matrix G satisfying AG equals PA, that is orthogonal projector onto column space of A, and column space of G is contained in column space of A, is called the core inverse of A. So note that core inverse of A is defined only for matrices of index 1. But Manjunatha Prasad and Mohana in the paper Core EP inverse have extended the notion of core inverse for the matrices of arbitrary index, provided a characterization and studied their properties. The definition of core EP inverse is as given below. Let A be a square matrix over real or complex field. A matrix G is said to be a core EP inverse of A if G is an outer inverse of A with column space of G equals row space of G equals column space of A power K, where K is the index of A. A matrix G is said to be a star core EP inverse of A if G is an outer inverse of A with column space of G equals row space of G equals row space of A power K, where K is the index of A. The index of a matrix is defined as the smallest positive integer K for which rank of A power K equals rank of A power K plus 1. So we note that whenever core EP inverse exists, it is unique. So core EP inverse in the context of associative rings. Be an associative ring with involution star. The Moore-Penrose inverse of A in R denoted by A plus or A dagger is the unique solution to the following Penrose equations. So first equation is AG equals A, AG equals G, AG whole star equals AG, GA whole star equals G. An element G satisfying equation 1 is called a generalized inverse of A or simply a G inverse of A. If such a G in R exists, then A is said to be a regular element in R. If G satisfies equation 2, then it is called an outer inverse of A. If G satisfies both 1 and 2, then it is called a reflexive generalized inverse of A. If G satisfies 1 and 3, then it is called a 1-3 inverse of A denoted by A superscript 1-3. The following is the definition of core EP inverse in the context of associative ring. Element G of an associative ring R is said to be the core EP inverse of A in R if G is an outer inverse of A with GR equals G star R equals A power MR for some positive integer M. Is said to be a star core EP inverse of A if G is an outer inverse of A with GR equals G star R equals A power M whole star R for some positive integer M. We shall now state some of the important theorems as a prerequisite to our main result. So you can refer the paper by Bapat and others for the proof. So we will use this lemma in the next theorem. The lemma says that let S be a semigroup for any two elements A and B in S such that A comma B belong to AS equals BS, then A is regular if and only if B is regular. The next theorem says that for A belonging to S and regular elements B and C in S, the following statements are equivalent. There exists an outer inverse X of A This is the notation we use for outer inverses of A. So this is a class of all outer inverse of A. So X belongs to class of all outer inverse of A. So X is an outer inverse of A such that XS equals BS and SX equals SC. And CAB is regular and CS equals CABS and SB equals SCAB. So we will give the outline of the proof. From the first statement, it follows that CAX equals C and XAB equals B. So this is because note that C is regular element and SC equals SS. Since C is regular, C belongs to SC and C can be written as an element small letter s of S into X. So now CAX will be equal to SXAX, but X is an outer inverse of A, therefore this will be equal to S into X, so that is nothing but C. Similarly, XAB equals B, so that CS equals CAXS, which is equal to CABS. This is because XS equals BS, and similarly we can show that SB equals SCAB. Since CAB equals CS, as noted earlier, where C is regular, it follows from the previous lemma that CAB is regular. So for the converse part, let G be any reflexive G inverse of CAB. If CAB is regular, then there always exists a reflexive G inverse of CAB. So take X equals BGC. Then X is an outer inverse of A. This can be verified very easily. And XS equals BGCS, that is equal to BGCABS, that is because CS equal to CABS, and that will be equal to BS, that is because SB equal to SCAB, and G is the generalized inverse of CAB. Similarly, we can show that SX equals SC, which completes the proof. So the outer inverse discussed in the previous theorem is exactly the same as the BC inverse defined by Drazin. Further, it can be noted that the Corey-P inverse as defined in definition 3 is an A power M star inverse. In place of P there is A power M and in place of C there is A power M star. So now we will give an expression for the Corey-P inverse. So before that we will prove one lemma. Let R be an associative ring, let B be a regular element in R, then B star BR equals B star R if and only if B has a 1-3 inverse. So proof is very easy. B star equal to B star BR, that implies B star equal to B star BR for some element R in R. So P multiplying by R star, we get R star BR equals BR whole star into BR. So which implies BR whole star equals BR. Also B star equals B star BR, and that will be equal to B star BR whole star, that is from BR whole star equals BR. So that will be equal to B star R star B star. So taking star on both the sides, we will get B equals BRB. It shows that B is one invertible. B has a generalized inverse. Conversely, B star R equals B star R star B star R, where R is the 1-3 inverse of B. So that will be equal to B star into BR whole star R. So that is equal to B star BR R, that is contained in B star BR. So other inclusion is trivial, therefore B star BR equals B star R. So now we will come to the main theorem. Given an element A in an associative ring R, if A has the Corey-P inverse, then A power M and A power M plus 1 are 1-3 invertible. Further, A power M into 1-3 inverse of A power M plus 1, A power M into 1-3 inverse of A power M is the Corey-P inverse of A. So proof is as follows. If G is the Corey-P inverse of A, then we have GR equals A power M R and RG equals A power M star from the definition for some positive integer M. Then G is a power M star inverse as we mentioned earlier. So by theorem 5, it follows that a power m star a power m plus 1 is regular, and that a power m star a power m plus 1 r equals a power m star r, and r a power m star a power m plus 1 equals r a power m. So now a power m star r equals a power m star a power m plus 1 r. This is contained in a power m star a power m r. The other inclusion is trivial, so we have a power m star r equals a power m star a power m r. So from the previous theorem, a power m has 1 3 inverse from the previous lemma. Further, from equation 1, it follows that a power m plus 1 star into a power m plus 1 r is equal to a power m plus 1 star r. So that is by pre-multiplying by a star to equation number 1. And hence a power m plus 1 is also 1 3 inverted. Also note that r a power m equals r a power m star a power m plus 1 is contained in r a power m plus 1, and hence r a power m equals r a power m plus 1, because other inclusion is trivial. So now we will show that the expression given in the theorem is the co-repeat inverse of A. So let me take that expression as y. Then y is equal to this expression, so that will be equal to, here in the second step we note that a 1 3 inverse of a power m is, in particular, it is 1 inverse, so this term reduces to a power m and rest are all same. And in the next step, so a power m 1 3 inverse of a power m plus 1 and a power m plus 1. So note that r a power m equals r a power m plus 1. So this term reduces to a power m and rest are all same. So that will be equal to y. Therefore y equals y. So y is an outer inverse of E. Clearly yr is contained in a power m r, that follows from the expression of y. So now a power m r equals a power m 1 3 inverse of a power m plus 1 into a power m plus 1 r. That is from the observation r a power m equals r a power m plus 1. So that will be equal to a power m 1 3 inverse of a power m plus 1, a power m 1 3 inverse of a power m a r. So that is equal to y a power m plus 1 r contained in yr. So other inclusion is trivial, therefore a power m r equals yr. Also y star r equals, so we note that y star is equal to a power m 1 3 inverse of a power m 1 3 inverse of a power m plus 1. That is from the properties of 1 3 inverses of a power m and a power m plus 1. So this ideal is contained in a power m r, and a power m r is equal to a power m plus 1 1 3 inverse of a power m plus 1 into a power m plus 1 r. So that is equal to a power m 1 3 inverse of a power m 1 3 inverse of a power m plus 1 a power m plus 1 r. So that is nothing but y star a power m plus 1, which is contained in y star r. Therefore y star r is equal to a power m r. Therefore y is the co-repeat inverse of A. So these are my references. Thank you.
Okay, thank you, Mashankara, for the nice presentation. Now the session is open for the questions. So audience, you can ask the questions now. Okay, if there are no questions, we can thank the speaker. Thank you, Mashankara, for the nice presentation once again. And we will move on to the last presentation. And the speaker is Dr. Shravan Chaudhary. He is from IIM Calicut, and he will be delivering the research talk on the topic stochastic comparison on small extremes of dependent heterogeneous observations. Over to you, sir.
Hello, everyone. My name is Shravan Chaudhary. I'm Associate Professor in the Department of Quantitative Methods and Operations Management, Indian Institute of Management, Kozhikode, Kerala, India. this is my honor and privilege that I'm presenting my paper in LABS 2020, which is taking place in the honor of Professor C.R. Rao on his birth centenary year. In this context, I would like to thank the organizers for giving me this opportunity. Coming back to the presentation, as you see, the title of the topic is Stochastic Comparisons on Sample Extremes of Dependent and Heterogeneous Observations. Here, essentially, we are going to compare two systems of dependent and heterogeneous observations and derive a few results. It is needless to mention that order statistics play an important role in reliability optimization, life testing experiments, operations research, and many other areas like hydrology, atmospheric science, finance, actuarial science. In particular, in the context of reliability theory, we know that parallel and series systems are the building blocks of many complex coherent systems. And we use order statistics in reliability theory, and we consider x1n as the smallest order statistic, which represents a series system, while xnn, which is maximum order statistic, which represents a parallel system. Now, there are a number of papers available in the literature which address this particular problem of stochastic comparisons of parallel or series systems of heterogeneous independent components, and that is with respect to both unbounded and bounded support. We also have a few papers in the same area where we have assumed components to be independently distributed. But in practical situations, the components of a system may have a structural dependence, and which results in a set of statistically dependent observations. There are few papers compared this dependent setup in the context of scale family, resilient scale family, and proportional hazard rate family of distributions. And there is one paper which also considered Weibull distribution to compare two systems when the components are dependent on each other. In 2017, there is a paper we found in Journal of Multivariate Analysis where the authors compared maximum order statistics from the location scale family of distributions under independent setup. So we have taken this particular work forward. We have considered these components to be dependent and tried to derive some of the results related to system comparisons. So what is the relevance of the location parameter? Like in reliability and survival analysis, although we consider the random variable to start from 0, but it is possible that components failure do not start at time t equals to 0, but after a finite time t, especially for highly reliable products. In finance, risk or return associated to different investments always may not start from negative infinity. It always may start from a finite value. Even in supply chain, where we always model lead time with a positive random variable, again, we cannot essentially consider a lead time to be 0, but again, it can start from a threshold which is non-zero. So in that perspective, we have considered a location and scale family of distributions here, which is essentially takes this particular form where lambda is the location parameter and sigma is the scale parameter. Now, there are well-known distributions which could be considered as the baseline distributions for this particular family. It is generalized Pareto distribution, which has exponential bar, Pareto, log logistic as special cases. There is exponentiated Weibull distribution, from where also we can derive exponential Weibull and exponentiated exponential distribution. It could be power generalized Weibull distribution, generalized gamma, Frechet, half normal. So these distributions can be considered as a baseline distribution function f. So essentially our objective is to compare two systems which are distributed with location scale family of distributions, having lambda I, sigma I as heterogeneous sets of parameters for one system, and mu I and xi I as another heterogeneous system of parameters for another system y. And essentially our objective is to compare the minimum and the maximum order statistics. And before I proceed, I need to introduce you to a couple of definition and notations. We have considered increasing or decreasing arrangement of parameters, and we are using these notations. And we are comparing the systems with the help of a concept of stochastic inequality known as majorization, which is defined this way, like X will majorize Y if the sum of the components or sum of the parameters is same, but the dispersion in X will be more than dispersion in Y. Similarly, we can define weakly supermajorization as well as submajorization, and these concepts can be found in the famous book by Marshall Alkin and Arnold. Similarly, we are defining 4 sets, 2 for the positive components and the other for real components. And also defining a concept called Schar convexity and Schar concavity. It is defined as Chi is known as Schar convexity or Schar concavity. If X majorizes Y implies that Chi X will be more than equal to Chi Y if it is Schar convex, otherwise Schar concave. Now we are capturing this dependence with the help of copula, which is also very popular and useful and very much known to the fraternity. So by copula we mean a distribution function, fx, which is a mapping C, right, and which maps fx with univariate marginal distribution functions f1 up to fn. Similarly, we can define a survival copula here. We have used Archimedean copula in particular because of its convenience and it is fairly flexible, and it is appropriate for a variety of jointly distributed lifetime variables. And as you notice, C is the Archimedean copula, and there exists a generator Chi for which this result exists. And you can find this concept of Archimedean copula in these books. And finally, we are comparing the systems with the help of hazard rate order, reversed hazard rate order, as well as stochastic order. These are the definitions. And you can find out these definitions in Shaked and Shantikumar. The name of the book is Stochastic Orders. We have used a lemma proposed by Lee and Fang in Journal of Multivariate Analysis in 2015. It says that there are 2 Archimedean copulas, C Chi1 and C Chi2, with Phi2 defined. And if Phi2 and Chi1 is superadditive, then the Archimedean copula C Chi1 will be less than equal to the same for the generator Chi2. Now we are comparing 2 different systems. First, we are comparing 2 series systems. As you notice, Xi follows location scale family distributions with lambda I, sigma I as the parameters. F is the baseline distribution function, where Yi also follows LS distribution, a family of distribution with mu I and xi I as the parameters, with G as the baseline distribution function. And we are using Chi1 and Chi2 as 2 different generators. And these are the expressions for the survival functions. So first result says that we have kept the location parameters constant in both the cases. As you notice, lambda I remains same, but 1 by xi weakly majorizes 1 by sigma. If that happens, then y1n will be stochastically larger than x1n. That's the result. Similarly, we can prove the same results for submajorization as well. But most importantly, we have also proved that y1n will be stochastically larger than x1n if mu, which is nothing but the location parameter for yi, will majorize the same for xi. Then we compare the minimum order statistics. Same results can be found out for the weakly majorization as well. Then for the maximum order statistics, also we derive these distribution functions with Chi1 and Chi2 as the generators, and we are getting similar results. Here we prove that The xnn will be stochastically larger than ynn if 1 by sigma majorizes 1 by xi. And also we prove that if x is stochastically larger than y, and if lambda majorizes mu, then xnn is more than equal to ynn in stochastic order. So we have proved the 6 results, and these are some of the references. And this particular paper is recently published in OR Letters, Operations Research Letters. Thank you.
Okay, thank you very much, Dr. Shravan Chaudhary, for the nice presentation. Now the session is open for questions. So participants, if you have any queries or comments, please raise your comments and queries. Okay, I hope there are no queries from the participants end. So if you have any comments or queries, you may contact the corresponding speaker. And I thank Dr. Shravan Chaudhary for the nice presentation. Thank you very much, sir. And with this presentation, we are coming to the end of the session. Thank you, Professor, and thank you, Karams, for giving me the opportunity to chair this session. Thank you very much.
Thank you, sir. Next, we move on to the next contributory talk session. The speakers of this session are Shivangi Singh, Rajiv Gandhi Institute of Petroleum Technology, JAIS, Amethi, India; Kshitij Chetri, NBBDC, Tadong, Sikkim, India; Shivani Rai, SMIT, Sikkim, India; Subhadra Das Gupta, IITB, Monash Research Academy, India. Now I request Professor Kuncham Shyam Prasad, Department of Mathematics, MIT, Mahe, Manipal, to chair this session. Over to you, sir.
Thank you, madam. First of all, thank you for giving me this opportunity, Professor Mandana Professor and team Karams. First speaker in this session is Shivangi Singh from Rajiv Gandhi Institute of Petroleum Technology, JAIS, Amethi, India. Talk title is Some Results on Doubly Truncated Entropy of Order Alpha and Beta. So, Shivangi Singh, please proceed for the presentation.
Good morning, everyone. I am Shivangi Singh, PhD scholar from Rajiv Gandhi Institute of Petroleum Technology, working with Dr. Chanchal Kundu. Today, I am going to present one of my research work titled as Some Results on Doubly Truncated Entropy of Order Alpha and Beta. These are outlines of the presentation. First of all, I will give brief introduction about my research work. Then I'll define doubly truncated entropy of order alpha and beta, called it generalized interval entropy, and characterize it. Then I'll discuss some properties and bounds of generalized interval entropy. And finally, I'll give the simulation study of generalized interval entropy to illustrate its behavior. Moving on into introduction. As we know, entropy is originated from thermodynamics, and it is extended later to the development of statistical mechanics and information theory. In the field of information theory, Shannon was the one who firstly introduced entropy known as Shannon entropy or Shannon information measure. For continuous random variable x, Shannon entropy is defined by this. Here f of x is the probability density function. It is a measure of uncertainty or randomness associated with the physical system. In the field of information theory, Shannon entropy is the key concept, and it has wide application in various areas in science and technology. So various generalizations of Shannon entropy have been proposed in the literature, basically based on parametric and non-parametric generalization. In parametric generalization, one of the important generalization of Shannon entropy is the Rayleigh's entropy of order alpha, that is defined by this. In this entropy measure, if we take alpha 10 to 1, we get Shannon entropy from this entropy measure. Another parametric generalization is the two-parametric generalization, that is a generalized entropy of order alpha and beta, that is defined by this. And in this entropy measure, if we take beta equals to 1, we get Rayleigh's entropy from this entropy measure. And if we take beta equals to 1, alpha 10 to 1, we get Shannon entropy from this entropy measure. So due to the parameter alpha and beta, this entropy measure is much more flexible. As we know, in survival analysis and live testing, the current age of the individual is also taken into account. In that situation, the Shannon entropy or the Rayleigh's entropy or this generalized entropy measure is not suitable for the uncertainty measure. So the notion of residual entropy and past entropy had been proposed in the literature. Residual entropies measure uncertain residual entropy measures uncertainty related to the future lifetime, and past entropy measures uncertainty related to past lifetime. With this motivation, Wagner proposed generalized residual and past entropy. This is the generalized residual entropy and this is the generalized past entropy. As we know, in many practical situations, the lifetime of the individual falls between two time points only. For example, if we want to study the income distribution, inequality of the income is not computed only for the richest population or the poorest population, but it is also for the middle class of the population. So that is Foley interval. So Misha and Yari defined Shannon's entropy for doubly truncated random variable called Shannon interval entropy. And motivated by generalized entropy and Shannon's interval entropy, here we have proposed generalized interval entropy of order alpha and beta. And in this entropy measure, if we take beta equals to 1, alpha 10 to 1, we get Shannon's interval entropy from this entropy measure. And again, if we take T1 10 to 0, we get generalized past entropy, and T2 10 to infinity, we get generalized residual entropy from this entropy measure. And if we take T1 10 to 0, T2 10 to infinity, beta equals to 1, alpha 10 to 1, we get Shannon entropy from this entropy measure. So this entropy measure is much more general setup. Here we have given characterization theorem and shown that generalized interval entropy determines the distribution function uniquely under certain conditions. In this theorem, we have characterized three distributions, that is exponential, finite range and Pareto distribution under certain conditions. In this theorem, we have studied the effect of monotonic transformation on generalized interval entropy. If generalized interval entropy is increasing in T2 for fixed T1, and we have considered the increasing convex function, then the generalized interval entropy is again increasing in T2 for alpha less than 1. And similar result we have obtained if generalized interval entropy is increasing in T1, keeping T2 fixed. In this theorem, we have provided the bounds of generalized interval entropy based on the monotonicity of general failure rate function. And this relationship holds for generalized interval entropy if general failure rate function is increasing in T1, and this holds if general failure rate function is decreasing in T2. And importance of these bounds is that sometimes the closed form of our proposed measure is not known, and we know that general failure rate functions are monotonic. It is either increasing in T1 or decreasing in T2. So using this relation, we can have some idea about our proposed measure. Here we have provided the bounds of our proposed measure based on the monotonicity of probability density function. In this theorem, we have shown that the generalized interval entropy is increasing with respect to interval under certain condition, that is for alpha less plus beta less than 2, and distribution function is twice differentiable and it is log concave. Here we have given the estimator of generalized interval entropy to illustrate the behavior of the estimates of the proposed estimator. For this, we have considered the variable distribution with shape parameter P. So, for the variable distribution, generalized interval entropy is defined as this. And to obtain the estimator of the generalized interval entropy, we have used the maximum likelihood estimation method. For this, first we estimate the parameter of the variable distribution, that is P cap. Once the parameter has been estimated value of the parameter is obtained, then putting in this, we can obtain the estimator of the generalized interval entropy, that is defined by this. Here we have calculated the estimated values of the generalized interval entropy based on 1000 simulation with sample size 50, 100, 500 and 1000 or alpha plus beta greater than and less than 2 with shape parameter 2. That is shown in this table. And in this table, we have shown estimated values PAS and MSC for sample size 100 and 500 with different concentration level and alpha plus beta less than 1. And we have found that estimated values are increasing with respect to T2 and decreasing with respect to T1, and it is an increasing function with respect to interval. And here we can see that estimated BAS and MSC are decreases as we increase the sample size, and similar result we have obtained for alpha plus beta greater than 2. Concluding result. We have proposed generalized interval entropy and characterize it. Then we have provided some properties and bounds of it. And finally, we have provided the simulation study of generalized interval entropy to illustrate its behavior. These are some references. Question. Thank you.
Yeah. Thank you, Shivangi. Now the participants, if you have any questions from participant side, and raise. Any questions from participant side? Okay. If there are no questions, I thank once again Shivangi Singh for presentation on this topic, doublet truncated entropy of order alpha and beta. Thank you once again. And the next speaker is Chitish Chetri from NBBDC Tadang, Sikkim, India. And she's going to talk on two-path sine graphs of balanced and canonically consistent sine graphs. So welcome Mr. Chitish for a presentation. Can start presentation. I can present. You can start presentation.
in view of this, we can say a relationship is balanced or not, okay? Accordingly.
Dear all, seems like there was a small technical issue. We are replaying Mr. Chitish Chaudhary's video. Thank you.
Hello, namaskar. I'm Chitish Chaudhary. The title of my talk is on two-path sine graphs of balanced and canonically sine graphs. So let me give the outline of my talk. So sine graphs, balanced and consistent sine graphs, canonical consistency, two-path sine graphs, and I'll be discussing some results and then lastly the references. Okay, so let me begin with the sine graphs. So the motivation behind sine graphs is, as the picture depicts, so x and y, suppose these are two persons, then these are some of the possibilities, like x dislikes y, so which is given by this red dots, and then y likes x. And likewise, we have here y likes x and x dislikes y. Okay, and the last one is x dislikes y and y dislikes x. Now, in view of this, we can say a relationship is balanced or not. Okay, accordingly, for example, here, there is a disbalance in the sense that x dislikes y, however, y likes x. And likewise, here it is the other way around. However, here we can see that x dislikes y as well as y dislikes x. And in this case, x likes y as well as y likes x. So the last two examples in this can be said to be balanced. Now, a few more examples here. So here x and y. So x dislikes y and x likes y, which all can be taken to be balanced. Okay, so I have a few more instances here, as you all can see here. Okay, so now let me come to the formal definition. As we know, a sine graph, the notation that I'm using is sigma, is a graph G together with a function, okay, from EG, that is EG is the set of all edges, and Z to 1 minus, means what does this function does is to each edge it assigns a sign. For example, between 1 and 5, it assigns sign minus 1, between 1 and 2, minus 1, 1 and 4, 1, and so on. Okay, so this sign function assigns every edge a sign. Now, G comma sigma, so this is the notation here, represents sine graph with underlying graph G and signature sigma. Now, for any edge, sigma E is known as sine of E. Now, for any subgraph, sigma 1 of sigma, so we have sine of sigma 1 is actually the product of the edges, okay? Product of the sine of the edges, beg your pardon, in that subgraph. Okay, so then we all say that the resultant, because you see here these are products of either 1 minus 1, and so the value will either be 1 or minus 1. So depending on that, so this is the final value that we get, plus 1 or minus 1, is the sign of the subgraph. Okay, so some standard results here, and then a bit of the genesis of the sine graph. So it was first introduced by Frank Harari. So in one of his earliest problem, interestingly, actually, it was introduced to model a social problem. So balanced sine graphs are also introduced in the same paper. So now a balanced sine graph is a sine graph in which every cycle has sine plus 1. So I'm assuming that the cycle is well known. So So balanced and consistent by so these are some of the classical characterizations of sign. Now there are various standard marking functions available. One of the simplest and most read is what is known as the canonical marking. So as you can see here, for example, this vertex has been assigned a sign -1. And this I mean this is one of the marking here, of course, where by some assignment of signs to the vertices, so this has been given us a mark -1. So this is what we call as the mark. There's a mark, these are all marks. Now as I said, it can be defined, mark graphs can be defined in various ways. Various markings can be defined. So I'll come back later with the canonical marking. Now for any vertex V, we take as a sigma, so this implies that the product is balanced but not canonically consistent, and vice versa. Okay. So likewise, we define the collection as C means, F subscript C means, these are all consistent sign graphs. Okay. So each of these sets are non-empty. So some more results for any graph G, the product G plus, with G plus is actually is an SPC. Okay, if sigma is equal to C and sigma, then underlying graph of this product will consist of either a cycle or a period-disjoint cycle. So this product will be canonically consistent, and hence sigma belongs to S of has. Okay, so this is a cycle of length 2n plus 1, okay, consisting of all negative edges. So this is not in SBC, but if you take a negative cycle of even length, so this is in SBC. Okay, so likewise here this is true if and only if n is even, and this is in SC plus if and only if n is odd. Okay, so if we have a sigma, so Cn means cycle of n. So this is in SPC if and only if it has even number of negative edges. If there are even number of consecutive negative edges in a cycle other than this, in C4 it is in SC plus. Okay, so likewise these are some of the results. Now in the following results, it is assumed that the vertices in Cn are level with 1, 2, and in counterclockwise. Okay, so we have a result if sigma equals to C2 and sigma has k even length paths with negative edges starting at even vertices. Okay, so even length paths with negative edges starting at odd vertices, type 2 and M, odd length paths with negative edges, then sigma is in SPC. For non-leaf, so I have this summation of I from 1 to k and I e by 2 plus j from 1 to l, so and z naught by 2 minus 1 plus summation r from 1 to m and r minus 1 by 2, and this are even, and otherwise it belongs to SC has, where ni is the length of the ith type of path, and j naught is the length of the jth type 2 path, and r is the length of the rth type 3 path. Okay, so likewise we have more results here. If sigma is kn comma 1 comma sigma, then this will consist of two components with underlying graphs as kn and k1. Further, the component k1 will consist of the center of kn1. Okay, so we have further results here. Now these are the references. Okay, so okay, so and some of these are some of the recent works.
Thanks the speaker for a wonderful talk. And if there are any questions, then participants can mail the speaker to clarify due to time constraint. So I'm going for the next speaker, Shivani Roy, Sikkim Manipal Institute of Technology, Sikkim. The title of the talk is on multiplicative y-index of product graphs. Please proceed, Ms. Shivani Roy.
Hello everyone, my name is Shivani Rai and I am a research scholar in the Department of Mathematics, Sikkim Manipal Institute of Technology, Majidar, Sikkim. The topic of my presentation today is on the multiplicative y-index of product graphs. So before I get to the topic, I'd like to give a brief overview of my talk. I'll be dealing with the following points. Firstly, I'll be talking about the background, then the introduction, the motivation behind my topic, the main results, and finally the conclusion and references. Firstly, the background. With the rapid advancement of medication, nanotechnology, bioinformatics, and cheminformatics, various new drugs and chemical compounds need to be synthesized. So for that, increased expenditure to acquire equipment and reagents to test the properties, activity, and toxicity of new drugs and chemical compounds is important. Furthermore, the use of topological indices is an effective alternative to predict their properties because these indices encode the structure of various chemical compounds in the form of real numbers. These indices are graph invariants which are related or associated with the molecular graph of chemical compounds. By molecular graphs, I mean where the vertices represent the atoms and the chemical bonds represent the edges between the atoms. The analysis of various compounds can be done effectively with less cost, so there are enormous savings if topological indices are used to compute the properties and analyze and predict their activities. Several software like the MathChem, the Dragon, the Python package like the SageMath also provide algorithms to simplify the ease of computation of these indices. Now the introduction. By topological index, we mean numerical parameters associated with the graphs, which are highly correlated with the topology of a network. I'd like to elaborate on this point for a few minutes. As I said earlier, the topological index can be derived from the molecular graphs of chemical compounds. It helps in the characterization and analysis of various structures. Not only that, these are useful tools in the quantitative structure-property relationship and structure-activity relationship studies. The topological indices are broadly classified under three heads. Firstly, we have the distance-based topological index. As their name suggests, these are based on the distance between the two vertices, example, the Wiener index and the Harari index. The second being the degree-based topological indices, which are based on the degrees of the vertices, example, the Zagreb indices and the Forgotten index. Lastly, we have spectral-based topological indices, which are based on the spectrum or the eigenvalues of the adjacency matrix, the Laplacian matrix or the normalized Laplacian matrix. Examples include the graph energy, the quasi-Wiener index, and so on. Now getting back to the main topic. The Yemen index is defined as the summation of the fourth powers of the degree over all the vertices of the graph. So we can see that the Yemen index is a type of a degree-based topological index, which is highly correlated with the eccentric factor, and the coefficient of correlation is equal to 0.95. With the entropy, the correlation coefficient is equal to 0.945, and with the enthalpy of vaporization of the octane isomers, the correlation coefficient is 0.85. So as we know, any correlation coefficient which is greater than 0.8 shows a very good correlation. So out here, the measure between the properties and the structure on the measure between the properties and the topological indices, which is given by the correlation coefficient, is greater than 0.8. So this is a very good topological index. So motivated by the multiplicative versions of indices like the Zagreb indices and the Forgotten index, we define a multiplicative version of the y-index as follows, which is a product of the fourth powers of the degrees over all the vertices of the edge of the graph. Now coming to the product graphs, operations on networks play a very important role to develop new molecular networks from the old ones. So there are many chemically significant graphs which are obtained by means of different graph operations, like the Cartesian product of the path on m vertices and the path on 2 vertices gives us a polynomial chain. Similarly, the Cartesian product of the cycle on m vertices and a path on 2 vertices, it gives us the nanotube, which is nothing but the carbon nanotube. And also the alkanes and cycloalkanes are also obtained from the various other products like the corona products or the lexicographic product of the cycles and the Cartesian product of the cycles and the null graphs on 2 vertices. So the product graphs, it helps us to understand how the topological indices can relate to the values of the corresponding topological indices of the factor graphs. It's also used to explore the relationships between the topological index of a product graph and that of its building blocks. So product graphs, let G1 and G2 be two graphs with vertex set G1, which is a collection of the vertices ui, where I goes from 1 to n1, and vertex set G2, vj, where j goes from 1 to n2, and size m1 and m2 respectively. Then a graph product of G1 and G2 is a graph H, such that the vertex set of H is equal to the Cartesian product of the vertex set of G1 and the vertex set of G2, and the adjacency is defined using some rules. So depending on these rules, various graph products are obtained. So we'll look at a few graph products. The first being the tensor product of G1 and G2, where the two vertices U and V are adjacent if and only if there is an edge between the first component and there is an edge between the second component. The degree of every vertex in the tensor product can be computed as the product of the individual degrees. And also the multiplicative y-index of the tensor product of G1 and G2 is given by the expression here, as we can see. Moving on, the Cartesian product G1 cross G2. The two vertices U and V are adjacent if and only if there is an edge between the first component and the second components are equal, or the first components are equal and there is an edge between the second components in the graph G2. So degree of every vertex of the Cartesian product can be computed as the sum of their individual degrees. And the upper bound for the multiplicative y-index of the Cartesian product is given by this expression, which is expressed in the terms of the number of vertices and the number of edges, also the number of also the other degree-based indices like the y-index, which is yg1. m1g1 here denotes the Zagreb index of G1, and m1g2 represents the Zagreb index of G2, and fg1 and fg represent the forgotten index. So this inequality becomes equality if and only if both G1 and G2 are regular graphs. So the composition or lexicographic product. So the two vertices U and V are adjacent if and only if there's an edge between the first component, or the first component is equal and the second components belong to the edge of G2. The degree of every vertex of the lexicographic product can be computed as n2 times the degree of ui plus the degree of vj. So the upper bound for the multiplicative y-index of the lexicographic product is also given by this expression, as we can see. And the equality holds if and only if both G1 and G2 are regular graphs. The strong product of G1 and G2, which is denoted by G1 star G2, wherein the two vertices U and V are adjacent if and only if the first component are adjacent in G1 and the second components are equal, or the first components are equal and the second components are adjacent, or there is an edge between the first components in G1 and edge between the second components in G2. So the degree of every vertex of G1 star G2 can be computed as the sum of their individual degrees plus the product of their degrees. So the upper bound for the multiplicative y-index of G1 star G2 is given by this expression. Here too we can see the strong product is expressed. The multiplicative y-index of strong product is expressed in the form of number of vertices and also in terms of the other degree-based indices. So the equality holds if and only if both G1 and G2 are regular graphs. The disjunction of G1 and G2, which is denoted by G1 VG2, where U and V are adjacent if and only if U and V1 belong to the edge of G1 or U2 V2 belong to the edge of G2. The degree of every vertex of G1 VG2 can be computed as n2 times the degree of UI plus n1 times the degree of Vj minus the product of their individual degrees. Again, the upper bound for the multiplicative y-index of the disjunction of the two graphs is given by this expression. And the equality holds if and only if both G1 and G2 are regular graphs. Lastly, we have the symmetric difference of G1 and G2, wherein the two vertices U and V are adjacent if and only if there is an edge between the first component of G1 or there's an edge between the second components, but not both. So the degree of every vertex of G1 and G2 can be computed as n2 times the degree of Ui plus n1 times the degree of Vj minus twice the product of their degrees. So the upper bound for the multiplicative Y index of the symmetric difference of G1 and G2 is given by this expression, which is also expressed in the form of the number of vertices and also in the terms of the number of edges and other degree-based indices. The equality holds if and only if both G1 and G2 are regular graphs. So now this brings me to the end of my presentation, to which I would like to sum up. Here we have discussed about the multiplicative Y index as it has been defined, and its upper bounds have been obtained for product graphs. And also we have characterized the maximal graphs with respect to this index, which are the regular graphs. The possible future directions include development of a very general polynomial that can generate topological indices for various classes of graphs. So instead of computing the degree-based indices one by one, we can generate one general polynomial, which in turn can generate degree-based indices or distance-based indices. For example, in literature, a polynomial called Hosoya polynomial, it generates distance-based indices, and a polynomial called the M polynomial generates degree-based indices. So along similar lines, we can generate some other polynomials which helps us to generate other class of topological indices. Also, finding the upper bounds and lower bounds of the topological index is also a very active research it's also a very active field of research, and here we characterize extremal graphs with respect to the. Also, the computation of variance of topological indices for chemical compounds is another interesting field of research. So these are my references. Thank you for your time.
Yeah. Nice presentation, Ms. Shivani Rai, on the multiplicative Y index of product graphs. Congratulations.
Thank you, sir.
If you have any questions, you please, participants can mail the speaker get clarifications. Okay, the next speaker is Subhadra Dasgupta from IIT Bombay, Monash Research Academy. Talk of the presentation, G-optimal designs for reduced copying models. So I welcome to the presentation, Dasgupta, Subhadra Dasgupta. Please start presentation.
Good morning, everyone. I am Subhadra Dasgupta, and I am a PhD student at IIT Monash Research Academy. Today, I'm going to talk about G-optimal designs for reduced co-creaking models. This project was motivated by an attempt to find an optimal arrangement of monitoring stations over a river to monitor the health of the river. We had the water quality data for River Nayar, which is marked in blue here, collected over 26 monitoring stations in marked in red. Various parameters like pH, dissolved oxygen, etc. were measured at each of these monitoring points. However, primary response that we were interested in was pH levels over the surface of the river. This kind of data is geostatistical data, and hence we decided to study co-creaking and creaking techniques and find optimal designs for these experiments. In next few slides, I would be discussing only the co-creaking estimation because creaking is a univariate version of co-creaking. Well, co-creaking technique is a method of making predictions of the primary variable using the observations of the secondary variable as well. So more formally, we consider two simultaneous random functions, Z1 to be the primary variable and Z2 the secondary variable defined over a region D, a subset of R. We consider a collocated sample, which means that we consider a set S of n points, and both the responses are collected over all the points in S. These variables are characterized by their mean and their variances. The mean given by the function mi and the covariance of zi, zj is given by the function zij. We consider the problem of predicting z1, the primary variable, at x0 at some point over on D, and we denote this zi x0 by z0 for the further discussion. We consider the random vectors z1 and z2, which is the vectors of observation of all the observation of z1 and z2 over the points. And the Cockring estimator is essentially the weighted sum of all these observations. The Cockring estimation is the minimum variance unbiased estimation. Some of the notations: the vector of all observations given by Z, the covariance of vector Z1, Zi and Zj is given by the matrix Cij. Sigma is the covariance of vector Z. Sigma naught is the covariance of Z with the point Z1 x0. Sigma I naught is the covariance of Zi with point Z0, and sigma naught net is the variance at Zi x0. Depending upon the mean of the primary and the secondary response, the Cockring could be classified in two categories. Whenever the mean mi is known and is a constant, we call the estimation procedure as the simple Cockring process. And when the mean is constant but unknown, we call that process as ordinary Cockring. In this slide, we will just go over how the Cockring estimator and the variance looks like. So we just talk about the simple Cockring estimation. The Cockring estimator is given by this sigma naught transpose sigma inverse Z, where these are the variance of the vectors. This is the random variable of all the observations Z1 and Z2, and the variance at x0 is given by this expression. Note that earlier we said that simple kriging is a univariate version of Cockring. So the kriging estimator of x0, Z1 at x0 is a linear sum of only the primary variable Z1, and the estimators are only given similar to the Cockring estimators, but are given only by the primary variables. We consider only the isotropic covariance functions. That is, the covariance depends only upon the distances. So the first result is regarding the model reduction. That is the condition under which the Cockring estimation reduces to Kriging estimation. For a collocated bivariate Cockring problem with isotropic covariance structures, if the covariance functions C11 and C12, they are linearly dependent, then the simple and the ordinary Cockring estimation reduces to Kriging. Note that here the C11 was the covariance of Z1 with Z1, and C12 is the covariance of the vector Z1 and Z2. And since the Cockring estimation reduces to Kriging, so even the estimators and both the variance, also the Cockring variance reduces to the Kriging variance. This is not very obvious because the C12 is a non-zero function. We will see also that we considered 8 types of covariance structures, and for the first 6, the generalized Markov type, proportional, and the Mettern, and one of the non-separable types. For all these 6 types, the reduction from co-kriging to kriging takes place. The second finding is regarding the optimal design. So formally, optimal design is defined as the arrangement of sampling points for primary and secondary random functions. The optimization criteria that we take here is SMSP, which is the supremum of the mean squared prediction error at x0 over all the points D. And our optimal design minimizes this SMSP. The setup that we consider here is the same. That is, Z1 and Z2 are observed over D and a bounded and a connected set. Z1 is considered again the primary variable. And additionally, what we assume is that Z1 has an exponential covariance type. That is, the covariance of Z1 is given by this particular expression. So for a co-kriging problem, if we make this assumption, please note, we can note that it satisfies the generalized Markov type, proportional type, Mettern 0.5, and one of the non-separable structures. So which shows that this assumption holds for some of the commonly used covariance structures. So under these assumptions, so note that additionally, for these 4 structures we have seen earlier, a co-kriging problem reduces to kriging estimation. So now on, if we talk about design of experiment for co-kriging, it would be same as saying design of experiment for kriging or reduced co-kriging. So essentially, our next results say that for simple and ordinary co-kriging models, the reduced simple and ordinary co-kriging models, or the kriging models, as described above, an equispaced design minimizes the SMSP, which means that an equispaced design is G-optimal design for simple and ordinary kriging or simple and ordinary reduced kriging. We try to see in practice how good this optimal design is. So we take only one branch of the river marked in this green and give it a transformation to make the one-dimensional region. We consider pH as our primary variable, and we consider phosphate as our secondary variable. We fit a generalized Markov model to this data, and when we see the ratio of SMSP, the SMSP corresponding to the equispaced design, here the equispaced design given by the xi star, to the SMSP corresponding to the existing river design on that particular branch, the ratio is 0.5, which means there is a considerable reduction in SMSP if the equispaced design is used, which also supports the theory. So this is what I wanted to discuss today. Thank you very much for your time.
Yeah. Okay. Presentation, Subhadra Dasgupta. If participants have any questions, they can contact the speaker. Congratulations once again. Thank you,
sir.
And I take this opportunity to thank the organizers of this conference. Once again, thank you all. We'll go for the next session.
Over. The session is over.
Thank you, sir. Now we move on to the next contributory session. The speakers of this session are Azadeh Cesare Fard, Stockholm University, Sweden; Kondam Ravinder Reddy, Kakatiya University, Warangal, India; Lintu MK, Manipal Academy of Higher Education, Manipal, India. I request Professor Srimati Maya, Department of Data Science, Mahe, Manipal, to chair this session. Over to you, ma'am. Ma'am, please.
Ma'am, your phone is on mute, ma'am. Actually, could you please unmute?
Yeah. Good evening. First of all, let me thank the organizer for giving an opportunity to chair this session. Thank you, Dr. Prasad. Now I welcome Azadeh Cesare Fard, Stockholm University, Sweden, to present the topic. The topic is on blues under two multivariate mixed linear model. I request the presenter, Azadeh, please come online with your video on.
Madam, sorry, we made you to wait.
Okay. What happened? She's not there?
No, she's there.
Okay. Yeah.
Ma'am, she is online. We will be playing her video talk.
Yeah.
After that, the session will be open for question and answer. Is that okay, ma'am?
Yes.
Thank you, ma'am.
Hello everyone, I'm Azadeh Cesare. I'm PhD student at the Statistics Department of Stockholm University, and let me share with you my slide. Today I'm gonna talk about the blues under two multivariate mixed linear model. These are the topics that I'm gonna talk about them. Consider the general multivariate mixed linear model. As in this form, B and lambda matrices are the fixed and random parts of the model that we want to estimate them. Under the multivariate mixed linear model, the best linear unbiased estimator of XB and the best linear unbiased predictor of lambda are defined in this way. The invariance of blue of fixed effects under linear fixed and mixed effects models have been noticed in practical application, since data collected in empirical studies commonly consist of many various variables. And practitioners are often unsure about the nature of the specific variables, which means they don't know whether to treat such variables fixed or random, whereas some set of variables could be clearly identified as fixed effects. So it would be useful to get the blues of a set of fixed effects which would be invariant to the nature of the other set of effects. Let us consider the following fixed effect model with two sets of factors whose effects are represented by beta 1 and beta 2. In some situations, the vector of fixed effects beta 2 could alternatively be considered as a random. Then the following linear effects model could be of interest. Here, the vector lambda represents the effect in beta 2 treated as random. Since here the focus is on the blue of the fixed effects for beta 1 under the partitioned fixed effects model F and the mixed effects model M, we have to note that according to Groth and Puntanen 2000 in Lima 1, if the estimation of all estimable linear parametric function of the fixed effects beta 1 is considered under the model F, then it is equivalent to consider the estimation of the parametric function m2 x1 beta 1. Here m2 is the orthogonal complement of column space of x2. Isotala, Mohs, and Puntanen in 2006 in Theorem 1, they have shown that if there exists solution with respect to L for the following equation, they could prove the equality of blue under the fixed and mixed models. The general solution to the system of matrix equation can be found by He and Wang in 2015. Using that result, I could find the solution for this specific case. In this case, we have these three matrix equations, system of matrix equations, and for our particular case, with R are considered as identity and compound symmetry matrices, I could find the least square solution, and also L1 and L2 are the solutions to this equation. By applying rank cancellation rule, we get the equivalency between all these three solutions. We shall return to this issue in the numerical example. Now I illustrate the general results in the following numerical example. Here it's the Popov and Roy dataset, which is a very famous dataset. And the following mixed linear model has been used for analyzing this dataset. And here, as you can see, the structure of covariance matrix is compound symmetry. In our model, this is the cross individual design matrix X and the matrix A, which represent the gender groups, and the matrix of unknown mean parameter B that we want to estimate it, and the maximum likelihood estimate of B is represented in this way, and these are the estimated mean growth trajectories in two different gender. The plot shows the group means and 27 individual growth trajectories at 4 different ages. There seems to be a linear trend in both mean profiles as well as different slopes indicating faster growth rate for boys and slower for girls. We can see that a profile tends to be high or low as a whole, which points to a random intercept. In this example, the covariance matrix of the model and also the loop are represented here. For the data in the numerical example, the model too can be rewritten as in this form. Let us explore the model tree and check whether the blue for beta is affected depending on whether we treat lambda as fixed or random. If lambda is treated as fixed, we get a fixed effects model similar to F with this covariance structure, and if lambda is treated as random, we get a mixed effects model similar to M with such a covariance matrix. In model 3, these are X, the partitioned matrix X, and in model 3, we can find the solution to the mentioned equation for the equivalent blues under the fixed and mixed model. So assuming independent error terms, which can be shown in R matrix. And also according to Theorem 1 in Isotalo 2006, the blue of the fixed effects in model 3 is not affected by how we treat lambda, which means that in our specific model and given matrix R, there is a solution to equation 1. And so which means that it doesn't matter if we consider lambda as fixed or random. We can get the equivalent blue for fixed part. In the next slide, I put some current research questions that I'm working on them. And also in the multivariate mixed linear model, we can express the general solution of the fundamental blue equation and the fundamental blue equation as in this form. And at the end, I put some references that I refer to them during my research. And at the end, thank you for your interest and for your attention.
Okay, that's a very nice presentation. Thank you. Now let us take up one or two questions, if any. Any questions? Please raise your hand if you have any questions. Participants, any questions? If you have any questions or comments, please raise your hand. I think there are no more questions. Thank you, Azadeh. Very nice presentation. Thank you very much. We shall move on to the next presenter. The next presenter is Kondam Ravindra Reddy, Kakatiya University, Warangal, India. I welcome Ravindra Reddy for the presentation of the topic Convergence Analysis of State Probability Vector and State Vector Stochastic Matrices.
I am thankful to the organizer for
please
for the international conference.
Yeah, video, you have to put on the video.
And applied linear algebra, probability and statistics 2020 in the memory of Professor C.R. Rao on his centenary birth year, organized by Center for Advanced Research in Applied Mathematics and Statistics, Manipal Academy of Higher Education. I am K. Ravindra Reddy, pursuing my PhD in the area of network traffic and stochastic process under the supervision of Dr. L.P. Rajkumar at Kakatiya University, Warangal. Here I am to present my research paper titled Steady State Probability Vector of Stochastic Matrices Convergent Analysis with the permission of the chair. Here I am present my work. Contents: Introduction, Methodology, Problem, Numerical Example I have taken, Conclusion, and the references. Introduction is: the design and control of networks can be carried out using a set of parameters of internet traffic. It is important to capture packet arrival flows and describe them with suitable stochastic matrices. Hence, the use of stochastic matrices is of interest in the performance analysis of queuing systems such as internet switch or router. In most cases, the network nodes are modeled as queuing systems. The problem of computation of performance measures is reduced to that of steady-state probability distribution vector of transient rate matrix or transient probability matrix. The transient analysis of analytical solution of stochastic models are not widely available as that of steady-state analysis. The vast literature and solution techniques are available only for the steady-state probability distributions. But in many applications of queuing theory, it is important to know how the system will operate up to some instant time t and how the solution behaves as t tends to infinity. Moreover, the investigation of transient analysis of queuing process is highly essential from the theory point of view and its applications. Here the methodology I follows. This diagram or figure shows that the traffic flow into the internet router, the traffic can be modeled as queuing systems using mathematical model And using a matrix geometric techniques, we find out a steady state vector or state probability vector, which gives performance measures like mean waiting time, packet loss probability, and so on. Using this, we dimension the internet router. Problem. The comparison between the state probability vector and the steady state vector of stochastic rate matrix. Stochastic process. A stochastic or random process is a mathematical object usually defined as associated with or indexed by a set of numbers usually viewed as a points in time. Markov chain. The stochastic process Xn is called a Markov chain if for j comma k comma j1 comma j2 comma so on jn minus 1 which are belongs to capital N, probability of xn equal k such that xn minus 1 equal j comma xn minus 2 equal to j1 and so on x naught equal to jn minus 1 which is equal probability of xn equal to k such that xn minus 1 equal to j which is equal p jk. This equation is defined whenever the first member is defined. Here the outcomes are called the states of the Markov chain, and this equation represents that the probability of future events is depends only on the present event but not on all the past events. Here the pjk refers that the two successive trials of transitions from j to k, and this transition is called as a one-step transition probability. And similarly, we can define the transition probability of m step, and it is denoted by pjkm, and it can be defined as a pjkm equal to probability of x of n plus m equal to k such that xn equal to j. Transition matrix. The next definition. The transition probability is pjk satisfies pjk greater than or equal to 0 and sum over k pjk equal to 1 for all j. That means sum of each and every row in the transition matrix is equal to 1. The next definition is Markov process. A stochastic process x of t is called a Markov process if for every n and t1 less than t2 less than so on tn satisfies the probability of x of tn less than or equal to x is that x of tn minus 1 and so on x of tn which is equal probability of x of tn less than or equal to x is that x of tn minus 1. This equation states that the evaluation of Markov process of future time conditioned on the present and past values depends only on the present value. Now the next definition is stochastic matrix. Square matrix P is said to be a stochastic matrix if all the elements in the matrix are non-negative and sum of each row is unity. And the example as given. In the doubly stochastic matrix, a square matrix P is said to be a doubly stochastic matrix if all the elements in the matrix are non-negative and sum of each row and column is unity. And the transition rate matrix, the next definition. In the probability theory, a transition rate matrix is an array of numbers describing the instantaneous rate at which a continuous time Markov chain transition between the states. And the transition rate matrix here we can denote it by a Q. In the transition matrix, in the transition rate matrix, element Q ij for I not equal to j denotes the rate departing from I and arriving into the state j. Here the diagonal elements qii are defined such that qi equal to minus the sum of all the elements in that row. Now this shows that the sum of each and every row in the transition rate matrix is equal to 0. The next definition is circulant matrix. A circulant matrix is a square matrix in which each row a cyclic shift of the row above it. A circulant matrix is of the form is given and C equal to simply we can represent as C1, C2, so on Cn. And the matrix C1, C2, so on Cn is said to be a circulant stochastic matrix if sum of the each and every row equal to 1 and circulant stochastic matrix and the matrix is said to be a circulant stochastic rate matrix if sum of each and every row is equal to 0 and in this case it is denoted by Q. If it is a stochastic circulant stochastic matrix, it can be denoted by capital P. And the properties of some of the properties of a stochastic and a stochastic rate matrices. Now the property 1. Every stochastic matrix has an eigenvalue equal to unity. In the property 2. The eigenvalues of a stochastic matrix must have a modulus less than or equal to 1. In the property 3. Every infinitesimal generated matrix Q has at least a 1, 0 eigenvalue. The next most important is a Chapman-Kolmogorov differential equation. The Chapman-Kolmogorov first order differential equation is d pi by dt equal to pi q for t greater than or equal to 0 and pi of 0 equal to I. Here pi of t is the state probability vector and q is the stochastic rate matrix. In the paper, stability criteria of the state probability vector of circular Markov chains Chapman-Kolmogorov differential equations, Professor Mallareddy-Peretti et al. Solved for circulant stochastic matrix and compare the result of free state vector and a state probability vector. In this paper, we generalize the result circulant stochastic matrix into the stochastic matrix with an appropriate example. Here, now from the Chapman-Kolmogorov differential equation, if the system is in the steady state, that remains as same as t tends to infinity. That is, pi of t is constant as t tends to infinity. That implies d pi by dt equal to 0. That is, for the steady state, the equation 1 reduces to d pi by dt equal to 0. This equation represents the system of homogeneous linear equations. You know that the system of homogeneous linear equations are always consistent because it always has a solution. That is, trivial solution is always a solution, and it may also have infinitely many solutions. If it has infinitely many solutions, the system is not stable. Our aim is to find out a unique solution that is not a zero solution. For that, we can apply some perturbation epsilon to the d pi by dt equal to 0. Then the system is converted into a non-homogeneous system of equations Ax equal to b, where x equal to pi transpose. Here, the solution is obtained by direct or iterative methods. Here, we use a Jacobi. Moreover, we have developed a TSS method for finding the solution of non-homogeneous system of equations. Here, in the TSS method, the quotient matrix is split into the form triangular and skew symmetric matrices. Quotient matrix is the sum of T and S, where T equal to L transpose plus D plus U and S equal to L minus L transpose, where L, D and U are lower triangular, diagonal and upper triangular matrices. Here, the iterative scheme of the TSS method can be written as xk plus 1 equal to m alpha into xk plus n alpha into b, where k equal to 1, 2, 3 and so on, and m alpha equal to alpha I plus s whole inverse alpha I minus t into alpha I plus t whole inverse into alpha I plus s, and similarly n alpha equal to 2 alpha into alpha I plus s whole inverse and alpha I plus t whole inverse, where alpha is a contraction factor. Here, numerical example we have taken is and here we compute the steady state vector using a power method by choosing an arbitrary stochastic matrix of order 4 by 4. A stochastic rate matrix Q is given by Q equal to I minus P. If P is the stochastic matrix, and it can be converted into stochastic rate matrix by taking Q equal to I minus P, where I is the identity matrix of designated dimension. And now we compute the steady state vector using the triangular and skew symmetric iterative method for the particular values of epsilon. The state probability vector of stochastic rate matrix can be computed by choosing initial probability vector x naught for the first order Chapman-Kolmogorov differential equation. The relative error is computed while computing the steady state probability vector and state probability vectors of the pertinent system. All the iterations are terminated when the residual error is 10 power minus 12, and the results are presented in the figure 1 and 2. Here, the error of the TSS method for the contraction factor of alpha equals 0.1 for the various values of epsilon. Here, this figure illustrates that the result for the relative error of the steady state probability vector of different values of epsilon by using triangular symmetric method, triangular skew symmetric method. Here, from the figure we observe that as epsilon is decreases, the approximate solution is approaches to a actual solution. As epsilon is increases, the solution is deviates from the exact solution. And this figure, Jacobi method, power method and TSS method for the contraction factor alpha equals 0.1 and epsilon equal to 0.1. Now this figure shows that now than the two methods, the Jacobi method and power method, the TSS method is converges rapidly compared to the existing methods, but the method we developed, TSS method, is more rapidly converges to the exact solution than the already developed methods, power method and the Jacobi methods. Here the conclusions. In general, the transient analysis and behavior of the analytical solution of queuing theory in a stochastic models are not widely available as steady state results. Hence, we examine the behavior of the state probability vector of the Kolmogorov first order differential equation whose quotient matrix is stochastic matrix. Then we find solution as t tends to infinity. Now, this kind of analysis is useful for finding the stability criteria of the pertinent system and performance measures of the network nodes to provide the quality of service. In this problem, we present a novel TSS splitting method and conclude that the method unconditionally converges to a unique solution and the convergence rate is rapid compared to the existing methods. Now, these are some of the references I have taken. And once again, thank you for giving me this opportunity.
Okay, thank you, Mr. Ravindra Reddy, for the interesting presentation. Thank you. Now let us take up 1 or 2 questions from the participants, if any questions or comments. Participants, please raise your hand if you have any questions or comments on this topic. Any questions? I think there are no more questions. Thank you, Mr. Reddy, for the nice presentation. We will be moving towards the next presenter. Yeah, the next presenter is Lintu MK, Manipal Academy of Higher Education, Manipal, India. Lintu, welcome to the presentation. That is, your topic is competing risk between in-hospital mortality and recovery, an application of deep hit on COVID-19 clinical data. Yeah, you can switch on your video and yeah, come online.
Very good morning to one and all. I'm Lintu MK, a research scholar of Department of Data Science, PSPH, Mahe, Manipal. And I'm going to present on the topic competing risk between in-hospital mortality and recovery, an application of deep hit on COVID-19 clinical data. These are the contents of my presentation. Coming to the introduction, as we all know, the novel coronavirus disease 2019 has spread all around the globe rapidly, and it has become a threat to global health, and WHO has already recognized it as a pandemic. And the healthcare system is under record-breaking pressure to provide optimal treatment and save lives. Coming to the survival analysis, survival analysis is a technique that is used to build the relationship between time to occurrence of an event of interest and the covariates that influence it. And modeling the time to death or any other event in the presence of clinical and prognostic factors has the potential to improve clinical care. A lot of studies is being carried out using various statistical and mathematical models to predict the probable evolution of COVID-19. And most of them are focusing on building predictive models and to assess the mortality rates and risk. Apart from this, concentrating on the length of hospital stay can improve decision making and treatment plans. So while modeling the length of stay, possible outcomes observed are either discharge or mortality, especially in case of COVID-19 patients. Actually, the two most commonly seen outcomes are either discharge or mortality. So competing risk setting is very common in epidemiological studies and clinical trials since the subjects are likely to experience multiple possible adverse events. So competing event modeling is done on COVID-19 patients using a state-of-the-art model, deep hit, which is a discrete survival model basically. And the raw data of 2,877 patients is obtained from an open access COVID-19 epidemiological data website. And in the time to event data of COVID-19 patients, discharge and death being two events, we framed the competing risk setup. And the covariates which we considered are age, gender, and a binary variable indicating any presence of chronic disease history. This is a schematic plot for competing risk time to event data for five hypothetical subjects. Here, 2 of them got censored at the end of the study period, and 2 of them got discharged, and 1 patient died. So this is the event-wise summary measures of the patients. So number of subjects, frequency and percentages are reported for each event, I mean both for discharge and death. And the median time in days until the event 1 or event 2 is given in the second row. It is 15 for discharge people and it is 8.5 for those who died. And median age in years was 38 years for discharged patients, and it was 70 for those who died. So coming to the model, a deep neural network model named DeepHit that learns the distribution of survival time directly without making any assumption on the underlying stochastic process was used in this study. And the model trains a multitask network to learn the estimate of the joint distribution of the first hitting time and competing events. The network consists of 4 layers. The 4 layers comes actually like this. The first layer is a fully connected layer for the shared subnetwork, followed by 2 subnetworks. So since we have considered 2 competing events, it is the second layer consists of 2 separate subnetworks. If it was 3, we would have got like 3 different subnetworks in the second layer. And the output layer is a softmax layer. And ReLU activations are used in all 3 layers. The network is trained using backpropagation via Adam optimizer with a batch size of 50 and a learning rate of 10 to the power minus 4. Actually, we have used all the network architecture as given in the original article. The dropout probability of 0.1 and severe initialization also was applied for all the. So we splitted the entire data to 60, 20, 20 for validation testing, for training, testing and validation. And for evaluation, 5-fold cross validation is being applied similar to the original work. So the time dependent concordance index was used to evaluate the discrimination ability of the model, which was used as the evaluation metric. So coming to the results, the time to event data of 2,877 COVID-19 patients were analyzed. Among these, 184 discharges and 63 deaths were reported, and the estimated joint distribution of survival time with 2 competing events is trained with DeepHit while incorporating right censoring. So mortality was marginally higher among the males, higher among the elderly, and among the patients with pre-existing chronic diseases. The plots are as follows. So this is the estimated survival curves of 2 patients generated by DeepHit. The x-axis shows the number of days from hospital admission and y-axis is the survival probability. So this is the result in which we have shown the concordance index we got from DeepHit. So we basically get 2 separate concordance index for both the events. So for discharge, it was 0.872, which is not bad. Actually, it's really good with a confidence interval, with a narrow confidence interval. And for event 2, it is 0.80 with a comparatively wider confidence interval. So this wider confidence interval indicates the variability and which could be due to the small number of events occurred. Death was comparatively less in the whole patients. So elders and patients with chronic diseases are more prone to die than other age groups. And it is important to consider all the competing events if a primary event of interest gets precluded by the others. With the availability of large data with more clinically significant covariates, this problem can be addressed with a new data-driven approach. And these are the references. Thank you.
Thank you, Miss Lintu. Very nice presentation, very interesting topic. You can take up questions, if any, from the participants. Participants, if you have any questions, please raise your hand. You can ask 1 or 2 questions. Any questions? I think there are no questions. Thank you, Lintu, for the nice presentation.
Thank you, ma'am. Thank you for giving this opportunity.
Thank you all. Thank you, Dr. Prasad, for the opportunity.
Thank you, madam. We made you to wait for one day.
No problem. It's okay.
Sorry
In
for
Manipal
that.
only, right? Okay. Thank you all.
Thank you very much, ma'am. In the next contributory session, we have the following speakers: Vaibhav Shekhar from NIT Raipur, India; Sunil Das from Indian Institute of Technology, Guwahati, India; Nitish Kumar R from Purna Prajna Postgraduate Center, Udupi; B. Gautam Shenoy from Purna Prajna College, Udupi.
Are they there in the lobby? Please check the lobby. No.
Am I audible, sir?
Yes, sir. You are audible, sir.
Okay.
Vijit, there.
So who is there?
Sir, from Department of Mathematics, SMIT Sikkim, to chair this session. Welcome, sir.
Thank you, madam. I'm very privileged to be to chair this session. I'm thankful to Karams as well as Prasad sir for giving me this honor. So let's start the session. So we have first speaker Vaibhav Shekhar, who will be talking about convergence of two-stage iterative scheme for k-week regular splitting of type 2 with application to COVID-19 pandemic model. He is from NIT Raipur.
I am
So Vaibhav, you can start.
My talk is on convergence of two-stage iterative scheme for k-week regular splittings of type 2 with application to COVID-19 pandemic model. This is the outline of my presentation. I start introduction with an important class of matrices called Z matrix. So given a square matrix over a real field R, this is called a Z matrix if all of its off-diagonal entries are non-positive. And a Z matrix is called an M matrix whenever A can be expressed in this form is I minus P, where S is a positive scalar, P is a non-negative matrix, and the scalar S is greater than equals to the spectral radius of matrix D. The matrix representation A is equal to U minus P is called a splitting of A whenever U is non-singular. So with the help of this matrix splitting, we can solve a large and sparse linear system by forming an iterative scheme which is computationally more efficient than the direct methods. So suppose we have a linear system Ax is equal to B, and where A is a non-singular matrix, then it simply use this expression A is equal to U minus P. We will get iterative scheme given by equation number 2, and here T is called the iteration matrix of this iterative scheme. Varga proved that this iterative scheme converges if and only if this vector radius of T is less than 1. Now we have definition of a monotone matrix which contains a matrix class of A matrices. So given a square matrix or real field R, then A is said to be monotone if X is non-negative whenever Ax is non-negative. Next result is about the characterization of this monotone matrix. So A is monotone if and only if its inverse exists and its inverse is non-negative. In this table, we have a characterization of monotone matrices in terms of different types of splitting. So given a splitting A is equal to U minus V is called a regular splitting whenever U inverse and V both are non-negative. It is called weak regular splitting of type 1 whenever U inverse and U inverse V both are non-negative. It is called weak regular splitting of type 2 whenever U inverse and V U inverse both are non-negative. And in each case of these three matrix splitting, the corresponding iterative scheme will converge if and only if the coefficient matrix A is monotone. Now we discuss about two-stage iterative scheme. Suppose we have a system X is equal to B, then simply using this expression A is equal to U minus V, we will get equation number 3, which is called the outer expression. And at each step of this outer expression, we apply another matrix splitting to solve an inner iteration. That is U is equal to F minus G, and if we combine these two together, inner and outer equation, we will get equation number 5, which is given by this. This is called the iterative scheme corresponding to a two-stage iterative method. However, if we put together the coefficient of xk, we will get equation number 6, where tsk is called the coefficient matrix of this iterative scheme, and this iterative scheme is called stationary whenever xk is constant for all k and non-stationary otherwise. So Omar and Susan proved this important result. So let A equal to U minus B be a convergent regular splitting, and U equal to F minus G be a convergent weak regular splittings of type 1. Then the stationary two-stage iterative scheme will always converge for any number of inner iterations. Next result is an important one. The first one is monotone convergence theorem, which guarantees the convergence of two-stage iterative scheme converges monotonically under certain sufficient condition, while the second one is helpful for us in such a way that we can, if we have two different splitting of the matrix U, then we can always choose such splitting so that our iterative scheme converges faster. So the sufficient condition for the faster convergence of the corresponding iterative scheme is provided here. Now we have some important notations. A non-empty subset K in Rn is called cone. When, if lambda K is contained in K for all non-negative lambda, and a cone is called a convex cone if it is closed under addition. Pointed cone if the intersection of K and minus K is singleton zero vector. A solid cone if interior of K is not non-empty, and a closed pointed convex solid convex cone is called a proper cone. Next, we have a few examples of proper cones. Simply, we have R2 plus, which is non-negative orthant of R2, and it is a proper cone. Similarly, K given by this set is also a proper cone. It is actually an ice cream cone. R2 is not a proper cone because R2 is not pointed. Singleton zero vector is not a solid, so it is not a proper cone. Similarly, the last set is also not a proper cone as it is not closed. Now we have a few definitions. A vector x in Rn is called k non-negative if x belongs to k, and it is called k positive whenever x belongs to interior of k. And the notation is given here: x is greater than equals to 0 with respect to this proper cone k. Similarly, in case of matrices, matrix A is called K non-negative whenever AK is contained in K, and K positive whenever A K minus 0 is contained in interior of K. And we don't denote this notation as x greater than equals to 0 with respect to K. And simply, in case of positive K positive, we denote A is greater than 0 with respect to K. For comparison purpose, x minus b is greater than equals to 0 with respect to k. We actually mean that the matrix A is increase of matrix A is greater than equals to b with respect to the proper cone k. And we, in this case, is said to be a k monotone if its inverse is non-negative with respect to proper cone k. Next, we have an important result proved by Marek and Sissel, which will help us to prove our main result. So, before going to the main result, we must have some formulation, some tools so that we can form our main result. So, our problem is that in literature we have U equal to F minus G as weak regular splitting of type 1. However, type 2 splitting has not been yet established in the literature. So our main aim is to solve this problem and to obtain convergence criteria in case of the second matrix splitting into stage splitting scheme is of type 2, weak regular type 2 splitting. So we just recall this iterative scheme by equation number 8, where TSK was given by this and P inverse SK is given by this. Now, when U is equal to F minus J is a weak regular splitting of type 2, then this matrix T cap Sk is non-negative. However, whenever it is type 2, we cannot guarantee the matrix non-negativity of the matrix Tsk. So, first we will we have proved this lemma. So, suppose Tsk is as defined in equation number 10, and Tsk is given by equation number 9. Then the spectral radius of Tsk and T cap Sk is equal. Actually, we are trying to obtain the convergence criteria of this iterative scheme in case of weak regular type 2 using this non-negative matrix T cap Sk. This is a convergence result. So let A equal to U minus B be a convergent K regular splitting, and U is equal to S minus G be a convergent K weak regular splitting of type 2, such that this condition holds. Then the stationary two-stage iterative method is convergent for any initial vector x0. And we have a small proof of this. Suppose we have already seen that in case of weak regular type 2 splitting, this T cap Sk is non-negative. So T cap Sk can be written as this form. Here we can use the expression or relation between F inverse and U inverse to write F inverse as U inverse into I minus G F inverse, and we use the commutative property here, and the condition, this condition V F inverse G is equal to G F inverse G to get this relation. And finally, if we simply add and subtract identity matrix and use this expression, we will easily get this expression. Finally, we will suppose that y is a positive with respect to proper count k, then x is given by this expression is also a k positive. Now, post multiplying this t cap sk by x, we will get t cap x is non-negative with respect to k, since t cap and x both are non-negative with respect to k. Now, one can easily verify that this x is k positive to the t cap xk, and again by theorem star that we have given above, we can easily show that the spectral radius of this T cap is actually less than 1. And using the lemma that we have proved that the spectral radius of T cap sk and T sk is same, we can conclude that the spectral radius of T sk is less than 1. We have provided an example. We have considered an ice-cream cone given by this set, and we have considered this matrix splitting, and we can see here that we have considered a convergent K3 weak regular splitting of type 2, where sk is equal to 2, and this sufficient condition V F inverse G is equal to G F inverse G is satisfied here. Hence, we can say that this iterative scheme, corresponding iterative scheme, will converge. And in fact, we can check that the spectral radius is 0.625, which is actually less than 1. Next result is about comparison result. We have matrix splitting A is equal to U minus B, which is a K regular splitting of a K monotone matrix A, and we have two different splitting. U is equal to F minus G is equal to F bar minus G bar, and both are K weak regular splitting of type 2. So our problem is which splitting should we choose so that the splitting that we have chosen yields a faster convergence of the iterative scheme. So this result actually provides a sufficient criteria for this problem. Next, we have SAI UQR pandemic model. We have simply considered 6 compartmental of population given by Khajantri and Sarkar, and we have considered this model where the matrix associated with the transition terms in the model is given by this form, and we can easily observe that this matrix is an M matrix. Also, the B matrix corresponding to the new instruction is given by this. And for simplicity, we have assumed that only 4 cross 4 matrices. However, the size of these matrices can be even bigger than 10,000 for larger sets of data. However, for simplicity, we have considered small sets of data. Now, just as data experimented by Khajanchi and Sarkar, we have simply used that data, and we can see that the matrix B and A is given by this, where this matrix A is actually is an M matrix. So to calculate the basic production number R0, which is actually given by this vector radius of BA inverse, we have to compute this inverse of A. So as I said that in general this matrix may be very large. So inverting an M matrix is computationally not so efficient directly. So we can apply here iterative scheme. And to solve this, we actually solve this linear system A is equal to B. So our solution, we will get A inverse B, and using the iterative methods, and then we can compute that its spectral radius, which is actually same as the spectral radius of BA inverse. So our aim is just to simplify this problem of invertibility of this matrix A. And this is the comparison of the two-stage iterative scheme. We have considered here SOR type of splitting and of A and as well as of U. However, we have considered two parameters, omega equal to 1 and omega equal to 1.7, and we can see we have applied these computations for different values of phi, which is actually the patients who are getting infected again after recovery. And the matrix sizes are given here, and number of iterations. We can see that as the matrix size increases, two-stage iterative scheme is quite efficient in case of the parameter omega is equal to 1.7. So finally we have conclusion. So we have established the convergence theory for the two-stage iterative scheme when the second iterating is weak regular splittings of type 2. And also we have shown that in COVID-19 pandemic model, M matrices appear where we have to calculate A inverse. So here we can apply this two-stage iterative scheme for this purpose, and we can easily not going with the direct method, but we can iteratively solve this scheme to get the reproduction number. Finally, we have references. Thank you.
Thank you, Vaibhav. If there is any question from the audience, quick questions, one or two. Okay, if no questions is there, let's thank Vaibhav for his wonderful presentation. Thank you, Vaibhav.
Thank you.
Our next talk is by presentation by Sunil Das from IIT Guwahati. He will be talking on some sign patterns of algebraically positive matrices.
I would like to thank the organizers for giving me an opportunity to present this talk. Title of my talk is On Some Sign Patterns of Algebraically Positive Matrices. This is a joint work with my supervisor, Siparna Bandyopadhyay. First, we go through some basic definitions. A sign pattern matrix is a matrix with entries from plus minus 0. These are two examples of sign pattern matrices. If A is a sign pattern matrix of order n, then the quadratic class of A is the set of all n by n matrices having same sign pattern as A, and this set is denoted by QA. Here M is in QA and n is in QB. M is obtained from A by replacing plus by a positive number, minus by a negative number. A sign pattern matrix A allows a property P if at least one matrix in QA has the property P, and requires property P if all matrices in QA have the property P. Here M is diagonalizable and it is in QA, so A allows diagonalizability. Every matrix in QB has a positive eigenvalue and a negative eigenvalue, therefore B requires diagonalizability. A sign pattern matrix A is commutatorily symmetric if both Aij and Aj are 0 or non-zero together for all Ij. Here A is commutatorily symmetric but B is not. The graph of a matrix A of order n is denoted by J and is defined to be an unrelated graph with vertices 1, 2 up to n, and it has the edge Ij if and only Aij is non-zero or Aj is non-zero. This is an example of a matrix with its graph. Here 2, 3 is edge is not available because both 2, 3 entry and 3, 2 entry are 0. If a sign pattern matrix is commutatorily symmetric and its graph is a tree, then it is called a tree sign pattern matrix. In particular, if this tree is a star or a path, then it is called a star sign pattern matrix or a path sign pattern matrix. This sign pattern matrix is commutatorily symmetric and its graph is a star, therefore it is a star sign pattern matrix. Now, this sign pattern matrix is commutatorily symmetric and its graph is a path, so this is an example of a path sign pattern matrix. Let T be the set of these 6 symbols plus, minus 0, plus 0, minus 0 has any matrix with entries from T is said to be a T pattern matrix. The qualitative class of a T pattern matrix A is denoted by QA, and each element of this set is obtained from A by replacing plus by a positive number, minus by a negative number, 0 by the 0 real number, plus 0 by a non-negative number, minus 0 by a non-positive number, and hash by a real number. A T pattern matrix A allows a property P if at least one matrix in QA has the property P, and requires a property P if all matrices in QA have the property P. If A is a T pattern matrix, then some entries may be plus 0, minus 0 hash. If we fix sign of each entry, then we get a sign pattern matrix. The set of all sign pattern matrix obtained from A is denoted by f of A. Thus, if a T pattern matrix A requires a property P, then all sign pattern matrices in f of A requires the property P. A real square matrix A is said to be irreducible if it is not permutationally similar to a matrix of the form x0 zy, where xy are square matrices of order at least 1. Algebraically positive matrices was introduced by Kirkland, Zhao and Zhan in 2016. A square real matrix A is said to be algebraically positive if there exists a real polynomial f, either f of A is a positive matrix. Here positive means entry Y is positive. They also give the following characterization. A real square matrix A is algebraically positive if and only it has a simple real eigenvalue and corresponding left and right positive eigenvectors. They also give some necessary or sufficient conditions. If A is algebraically positive, then A is irreducible. If there is a positive integer k, such that a to the power k is algebraically positive, then A is also algebraically positive. If A is irreducible and all of its of diagonal entries are non-negative or non-positive, then A is also algebraically positive. Now, if we look at this theorem, above theorem, if we consider the simple real eigenvalue as lambda, the right eigenvector as x and the left eigenvector as y, then ax equal to lambda x and y transpose A equal to lambda y transpose. Then A commutes with xy transpose. This xy transpose is a rank 1 positive matrix. We prove that A commutes with only this xy transpose and its scalar multiples. Here is the result. A real square matrix is algebraically positive if and only if it commutes with a unique rank 1 positive matrix. Now, adjugate of a square matrix A is a polynomial in A. Therefore, if adjugate of A is algebraically positive, then A is also algebraically positive. However, the converse is not true. For example, if we take A equal to this matrix, then for the polynomial f x equal to s, f of A is a positive matrix, so A is algebraically positive. but adjugate of A is the zero matrix. So any polynomial in adjugate of A is a scalar multiple of the 3 by 3 identity matrix. Thus, adjugate of A is not algebraically positive. Now we look for the three sign patterns that allow algebraic positivity. Kalkulen, Jhayo and Jan give the following sufficient condition for a sign pattern matrix to allow algebraic positivity. If a sign pattern matrix allows algebraic positivity, then every row and column contains a plus, or every row and column contains a minus. They given the following characterization for allowing algebraic positivity for a certain class. If A is an n by n irreducible symmetric tridiagonal sign pattern matrix, then A allows algebraic positivity when only every row and column contains a plus, or every row and column contains a minus. Now, irreducible tridiagonal sign pattern matrix is nothing but a path sign pattern matrix. We strengthen this result by showing that this result is not only true for path sign pattern matrix, but in fact it is true for all three sign pattern matrices. Further, we can omit the assumption symmetric from here. So here is the result. Let A be a T sign pattern matrix, then A allows algebraic positivity if and only A is a symmetric sign pattern matrix and every row of A contains a plus, or every row of A contains a minus. Now we look for T sign patterns that require algebraic positivity. First, we show for star sign pattern matrices. A symmetric T pattern matrix whose graph is star is permutation similar to a matrix of the form this. We have defined three T pattern matrices of this form: XPQR, YPQ, and ZPQ. This result classify the star sign patterns that require algebraic positivity. If A is a star sign pattern matrix, then A requires algebraic positivity if and only one of the following conditions hold: all non-zero of diagonal integer plus, all non-zero of diagonal integer are minus, A or minus A is permutationally similar to some sign pattern matrix from Fs, where S is the one of these three T pattern matrices: XPQ, YPQ, ZPQ. Now we look for path sign pattern matrices that require algebraic positivity. A symmetric T pattern matrix whose graph is a path is permutation similar to a matrix of the form this. We defined 7 T pattern matrices of this form: M1, M2, N1, N2, N3, N4P, and 5P. This result classifies path sign patterns that require algebraic positivity. If A is a path sign pattern matrix of order at least 4, then A requires algebraic positivity if and only one of the following conditions holds: all non-zero of diagonal integer plus, all non-zero of diagonal integer minus, A or minus A is permutational similar to some sign pattern matrix from Fs, where S is one of these 7 T pattern matrices. Now here we assume that order of A is at least 4, because if order is almost 3, then the sign pattern matrix is a star sign pattern matrix, and this case is covered by the previous result. There is only one tree which is neither a star nor a path. The sign pattern matrices of that form require algebraic positivity if they belong to one of these classes. These are the references. Thank you.
Thank you, Sunil, for your presentation. If there is any question, quickly one or two. Yeah, somebody is there.
I thank you for the interesting talk. Have you considered patterns beyond trees?
No, actually, I did not find any nice form. That's why I could not go for it.
Yeah, trees are nice because of the acyclic structure. I just wonder, maybe even just a cycle or something more circulant.
Yeah, I have not tried for it, but I will.
Okay, thank you. Very nice talk.
Thank you.
Okay, thank you, Sunil, for a wonderful presentation. So now we have our next presentation by Nitish Kumar R from Purna Pranja Postgraduate Center, Udupi. He will be talking on matrix dimension of a graph corona with K1, a two regular graph.
Good morning. Today I am going to present
Nitish,
metric dimension of a graph corona with K1, a two regular graph. So in this discussion, we are considering G as a finite, simple, connected and undirected graph. The distance d of u, v between two vertices u and v in G is the length of a shortest uv path in G. For an ordered set W, W1, W2, so on up to Wk of V of G, vertex set of G, we refer the K vector d of V, W1, d of V, W2, d of so on up to d of V, Wk. That is, we are considering the distance from V to every vector of W in a order, and we are representing it R of V bar W and reading it as R of V with respect to W, or representation of V with respect to W. The set W is called resolving set for G if R of U with respect to W is equal to R of V with respect to W, implies U is equal to V for all vertex U, V belongs to V of G. That means this W is said to be a resolving set if every vertex of G has a distinct representation. For example, consider this graph. So it is nothing but P5. So if I take W1, if I take Wn as V2, and if I calculate the distance of all the vectors with W1, that is nothing but V2. V1 to V2 is the distance is 1. V2 to V2 distance is 0. V3 to V2 is distance is 1. V4 to V2 is distance is 2. V5 to V2 is distance is 3. But using this table, we can observe that V1 to V2 and V3 to V2 have same distance. So this W1 is not a resolving set, So if I consider W2 as V1 and V2, then if I calculate the distance, V1 to V1 is 0, V1 to V2 is 1, and V2 to V1 is 1, V2 to V2 is 0, V3 to V1 is 2, V3 to V2 is 1, V4 to V1 is 3, V4 to V2 is 2. Similarly, V5 to V4 is 4, V1 is 4, V5 to V2 is 3. So if we observe in this table, all the representation are distinct. Hence, this W2 is a resolving set for this graph. Okay. Now, a resolving set of minimum cardinality for graph G is called a minimum resolving set for or basis of G. The cardinality of minimum resolving set is called metric dimension or simply the dimension of G. So for example, again if I consider this P5, if I take W1 is just V1, then V1 to V1 is 0, V1 to V2, V2 to V1 is 1, V3 to V2 is 2, V4 to V1 is 3, V5 to V1 is 4. Hence, all the representations are distinct. Hence, dimension basis this V1 is a basis for this graph. Hence, its dimension is 1. Similarly, if you observe in this cycle C4, we can observe V1 and V2. This is the representation. All the representation are distinct. Hence, this W is a basis. Hence, the dimension is 2. Okay, now the corona product. The corona product G1 corona G2. This representation is reading as corona. So G1 corona G2 of two graphs G1 and G2 is the graph obtained by taking one copy of G1 and P1 copies of G2, where this P1 is nothing but number of vertices in G1, and then joining the ith point of G1 to every point in the ith copy of G2. So since there are two points vertices in G1, we need to take two copies of G2. See, this is the two copies of G2 and join ith point of G1 to every ith copy of G2. So this is the first copy of G1. If I say this is the second copy of G1 and it's the first point and it is the second point, I should join this point to first copy of every point in the first copy of G2, second point to every point in the second copy of G2. This is G1 corona G2. If I take G1 corona G2 in a reverse format, that is, if I in the previous year I take it is P2 corona P3. If I take P3 corona P2, then the graph is like this. I should take G2 three copies of G2, since G1 has three vertices, and the graph will be this. And from this we can observe this one thing. Observe this: G1 corona G2 is not equal to G2 corona G1. And this is one more example. If I take a graph like this, and if I take corona with every vertices, single vertices, every vertex will be added with the pendant vertices. Okay. Now in this paper, the result is for any two regular graph G, 2 is less than or equal to metric dimension of G, less than or equal to metric dimension of G corona K1, less than or equal to 3. This beta is represented for metric dimension of G, or resolving number of G of graph. So this is, we know that this is always true. That is, metric dimension of cycle is always 2. So I'm going to prove this using in the case wise, that is, if n is odd and n is even. For suppose n is odd, the first thing is for n is equal to 3, that is C3 corona K1, beta of C3 corona K1, that is metric dimension of C3 corona K1 is 2. Suppose now n is greater than or equal to 5, and n is odd. So if I take two vertices u and v with the distance d is nothing but the diameter. Now then I'm going to find, is there any two vertices have same representation? Because if no two vertices have same representation, then these two vertices will become a resolving set. Hence, and with the minimum cardinality, because for any graph, if the resolving number is 1, if and only if, or metric dimension is 1, if and only if it's a path. But since it is not a path, so its metric dimension has to be greater than or equal to 2. But in this case, when I take u and v, u comma v, their distance is diameter of this g, then it will become a resolving set. So I'm interested to find whether there are two vertices with the same representation. So if I consider the vertices in Cn, it will be so I'm going with case whether their vertices are in the Cn. It is not possible. Now again asking whether those two vertices are in end vertices or have same representation. Again, it is not possible, because if end vertices have same representation, then their corresponding vertices in Cn will have same representation. Now, next, suppose my one vertices is in this Cn, and another vertices is an end vertex. In this case also, I'm getting it is not possible to have same representation. Hence, for this graph, that is Cn corona K1 with n odd, that metric dimension will be always 2. Metric dimension is always 2. Now the next case is, suppose n is even. Again, as we seen in the beginning, it is not possible to have a metric dimension 1. So I'm checking whether metric dimension is 2. So the first observation I made is any two vector vertices cannot be the basis, because if I consider those vertices in this Cn, it will not a basis, because I can have two vertices. They have same representation in all the form. And if then I'm taking three vertices which are with this condition. I'm taking three vertices u, v, w, with u and v are adjacent, and distance between u and w is equal to d. D is nothing but here diameter of Cn. This will resolve this Cn corona K1 when n is even. Hence, this metric dimension of this will be 3. Hence.
Thank you, Nitish. If there is any questions from the audience. If not, let's thank Nitish for nice presentation. Thank you, Nitish.
Thank you.
So we have our next presentation by B. Gautam Shenai from Purna Pranja College, Udupi. He will be talking on rational winner index and rational sculch index of graphs.
Good afternoon, everyone. I, B. Gautam Shane, would like to present on the topic rational Wiener index and rational Schultz index of graphs. To begin with, we shall see what is rational distance and why it's important. Considering these facts of giving importance to vertex by its proximity along with its related factors. Since edge represents the relation between the vertices and degree represents the number of influencing factors. Therefore, the number of ways of reaching a vertex increases the proximity of the vertex. Also, the number of ways of leaving a vertex decreases the proximity. The special distance, rational distance, was introduced. Rational distance can be defined as d of u bar v is equal to summation ui belongs to closed neighborhood of u, distance between ui and v, divided by degree of u plus 1 if u is not equal to v, and 0 if u is equal to v. From this, we can observe that the rational distance takes the neighborhood vertices into account along with the vertex. This will have better reflection in case of biological and sociological application. Further, we shall see what we mean by rational distance matrices. A square matrix of order n with rational distance as its entries is called rational distance matrices. Further, based on rational distances, we can define topological indices. We will discuss two of such. Those are rational Wiener index of graph G and rational Schultz index of graph G. Rational Wiener index of graph G can be defined as half into summation over all the entries of rational distance matrices, and rational Schultz index can be defined as half into summation u belongs to v of G summation V belongs to V of G, degree of U plus degree of V into rational distance between U and V. Further, we shall observe the expression for the rational Wiener index and rational Schurz index of different types of graphs such as star, wheel, friendship, and crown. Firstly, we shall observe the expression for the rational Wiener index of star graphs. The theorem 1 states the rational expression for rational Wiener index of star graph. The proof of the theorem can be obtained by classifying the vertex of star graph into two types, that is the central vertex and external vertices or pendant vertices. And we can observe that the rational distance between the central vertex and any external vertex would be of the form 2n minus 3 by n, and the rational distance between any external vertex and the central vertex would be of the form 1 by 2, and the rational distance between any two external vertex would be of the form 3 by 2. Summing up all this along with the repetition and multiplying it by half, we obtain the expression for rational Wiener index of star graph. Similarly, since the central vertex is of degree n minus 1 and external vertex is of degree 1, we obtain the expression for rational Schurz index by multiplying the sum of degree of the vertex between which the rational distance is considered by respective rational distance, and summing it all and multiplying it by half, we obtain the rational Schurz index of the star graph, which the expression of which is given by the theorem 2. Next, the expression for the rational Wiener index of wheel graph is given by theorem 3, which can be proved by considering the classification of vertices of wheel graph into 4 types. That is, one is the central vertex and the external vertices, and the further external vertices can be divided by considering the spanning cycle of the vertex set as external vertices and specifying certain external vertices and classifying based on distances, that is the vertices which is at distance 1, distance 2 and distance greater than 2. We can observe that the distance between the central vertex and any other external vertex would be of the form 2n minus 5 by n, and the external vertex, specified external vertex, and the external vertex which is at distance 1 from the specified external vertex would be of the form 1, and the external vertex and the external vertex which is at the degree distance 2 from the specified external vertex would be of the form 3 by 2, and the external vertex and the external vertex which is at the distance greater than 2 would be of the form 7 by 4. Summing up all this along with the repetition and multiplying it by half, we obtain the rational Wiener index of wheel. Since the central vertex is of the degree n minus 1 and the external vertex is of the degree 3, we will obtain the rational surge index of wheel in the following manner, which is explained by theorem 4. In similar way, we'll obtain the rational Wiener index of friendship graph, which is given by the expression in theorem 5, and rational surge index of friendship graph, which is given by theorem 6, and the rational Wiener index of crown graph, which is given by theorem 7, and rational surge index of crown graph, which is given by theorem 8. Thank you.
Dev sir, you are muted, sir. You might have to unmute your.
Okay. Thank you, Gautam. Is there any question from audience? If not, let's thank Gautam for his wonderful presentation. With this, we come to the end of this session. I congratulate every participant for presenting their work in this session. I'm also very much thankful to Manjunath Prasad sir and Karams for giving me opportunity to chair this session. Thank you.
We thank Dr. Biswajit Dev for chairing this session. Thank you, sir.
Thank you, Dev.
Thank you, sir.